Good morning, everybody. Welcome to HardHaQ. I'd like to wait for about 4 or 5 more minutes just for a few people to trickle in before we officially start the event. So at 9:05 or maybe 9:10, we'll get started and we'll kick things off. It's great to see you all today. Thanks for waking up early on Saturday. I just want to confirm you can all see my slides right now. And if I go into presenter view, and I changed slides. It's all good. You guys can see this, okay? Okay, awesome. Okay, it is now 9:05, so I'm gonna get started. So, welcome everyone today to HardHaQ. I am so excited to kick off this event and show you guys all of the hard work that we've been working on over the past 9 months. This is a very unique experience that you guys are going to have this year, or sorry, this week. As far as we are aware, this is the first of its kind quantum hardware hackathon. So, what is HardHaQ? HardHaQ is a 1 week long hybrid hackathon that is going to give all of you guys across North America the opportunity to engage with industry grade quantum hardware and challenges. You're going to be using Ansys HFSS, Ansys Numerical, and COMSOL to solve one of three challenges over the course of this week. When I was talking about this event to some of the undergraduate students over here at McMaster at our quantum club, I brought up Ansys HFSS, and he said, "Oh, that's so cool. That's the software my brother uses at his work." And I said, "That's the point. What we're trying to do here is we're trying to give you guys skills that are industry relevant and things that you can take and use in your future on your resumes to help you out in the field of quantum hardware." Unlike most quantum competitions, we are going to focus specifically on hardware this week, which is a really rare chance for you to gain hands-on experience with tools, problems, and thinking that drive today's quantum technologies. Guys, you really blew us away. We're pleased to welcome 313 participants across both Canada and the United States. It's awesome that we got so much interest, and it just really goes to show that we're filling a niche gap here that not many other hackathons can say they do. So, first, I would like to introduce the team. Who are we? So, the North American Quantum Consortium is a student-led alliance connecting undergraduate quantum computing clubs across both the US and Canada. So, we have representatives from 14 universities across North America, and our mission is to empower the next generation of quantum innovators through hands-on experience, collaborative events, and a strong cross-campus network. So, we just formed this year. This is our premier event, and I would really like to thank a few people from both University of Toronto, University of Western, and over here at McMaster. I would like to specifically shout out Clarissa White. I'd like to shout out Will Haynes. I would like to shout out Emily Berlinghoff, and I would like to shout out Michael Silver. Without these four students, exceptional students, this event would not be able to run the way that it is today. So, I want to give you guys a little bit of a walkthrough how normal quantum hackathons go and how we're different. And hopefully this will give you a little bit of an idea of what the motivation behind this event is. So if you've ever participated in a hackathon in the field of quantum before, this is usually the way that it goes. You'll have some sort of quantum algorithms challenge that you'll start with, usually in a software like Qiskit or PennyLane. What you're going to do then is you're going to write some Python code, which is essentially going to be a simulated quantum circuit. That Python code is going to demonstrate some kind of quantum advantage, which you can then go on to show, and you can simulate your solution. And IBM or Google might give you some runtime to actually to actually test and run your hardware. But as I said, you test and run it on what? So usually when you create your solution, if you get runtime, you'll run it on a few quantum chips that IBM has. Two of them of note I've listed here. So Eagle, which has 127 qubits and 1.98 E-2 error per logic gate. Heron, which has 133 to 156 qubits with 3.7 times 10 to the minus 3 error per logic gate. Or Google's Willow chip, which I'm not sure if it's available to the public to actually run quantum algorithms on it. But Google's Willow chip has 105 qubits. They also have their Sycamore chip, which I think was the generation before this one. So, why are people interested in quantum at all? Well, it was shown in 1994 with Shor's algorithm that you could actually get an exponential speedup. So I think you could do in O(n) time on a classical computer. You could do that in O log n time on a quantum computer. Um, Grover's algorithm showed a brute force speedup, which was very, very similar. And essentially, what it's showing is that there's a specific amount of um, quantum qubits that you can have that is going to essentially beat out a classical computer on some tasks. However, these were found over 25 years ago, and we still use the same encryption methods. We still use RSA encryption, and we still don't really see quantum computers in the mainstream in general. So why is this the case? Why does it seem like this? People are always talking about these quantum challenges, and oh my gosh, quantum is going to break RSA encryption. But it doesn't seem to really be affecting our day-to-day life. How many qubits does it take in order for this to be a real challenge? So here, this big number on the left, this is a very popular number, which was posted by RSA, or I forgot exactly which institution posted it. But this number is a RSA 2048 key, and there's a $200,000 cash prize if you can crack this number, if you can find the prime factors of this number. Um, this would take a classical computer uh, millions, not even millions, like billions, orders of magnitude longer than the universe has been around for to crack. But it has been shown that it will take 8 hours for 20 million noisy qubits to crack. Now remember what I showed you before. Right now we're sitting at 133 to 156 qubits with Heron, 105 qubits with Google, and 127 qubits with Eagle. Um, I believe that IBM has one quantum computer where they have 1,000 qubits. But either way, that is still a very, very far cry from the millions of qubits which are needed to be useful. So, what's the holdup? What I have here, for example, is just a showcase of what you would argue is the classical analog of the qubit, just the transistor. Apple's M2 chip, which launched in 2023, has 134 billion transistors on it. So, fun fact, there are more transistors on Earth today than there are stars in the Milky Way galaxy. But for comparison, uh, the record right now for qubits, so this is actually September 24th, 2025, Hannah Monetch from Caltech um, launched this quantum computer, which hasn't actually had anything run on it yet, but it set the record for the highest number of qubits at 6,100 qubits. So why is there such a big gap between what we're able to do with classical computing and what we're able to do with quantum computing? What's the holdup? Well, the holdup really comes from the fact that quantum computers are noisy, quantum computers are not scalable, and quantum computers have gate imperfections. Not all platforms have these issues. There are also many more issues which I'm brushing under the rug, which are platform specific, but it really, really boils down to most of the implementations of quantum computers having issues in a few of these areas when it needs to be perfect or close to perfect in all of them. For example, what I've shown here is one of IBM's 5-qubit processors. So the reason I'm illustrating this is because you can see that there's complicated circuitry that needs to go in between each one of the qubits to address them correctly. On top of each qubit, you need to have resonators to address each one of the qubits. You also need to have charge lines and readout lines. And you can imagine that scaling such a device to thousands and tens of thousands of qubits, when you need interconnectivity between every cross term. So for example, what I mean by that is qubit 1 to qubit 2, qubit 1 to qubit 3, qubit 2 to qubit 3. That will become very, very, very difficult. And the more that you add, the more noise that you have in between them. Oh, sorry. And here, this is just illustrating that. So this is something that none of the quantum algorithm challenges that you might have participated in before are going to talk about. What I have here is a screenshot from the Penny Lane website, which is one of the sample problems that they have. So it's making this quantum algorithm to compute the Hessian, which is like the second order derivative of a certain function. And you can see here that in the general solution template, they have this long chain of qubits that you're going to use to run this algorithm. Now, when you would compete in a problem like this, you would just worry about the code. You would generate the correct schematic. Each one of these blocks would be some kind of functional code, and you would have some kind of gates that act between them. But you will always have to remember, in order for this to be actually feasible, it's going to have to run on some kind of hardware. So each one of these lines that you see is going to be one of these qubits. Each one of these gates that you see is going to need to be some kind of resonator that's coupling one of the qubits to the other. And you can see already from here, like there's no resonator coupling qubit 3 to qubit 1, right? So you can't just arbitrarily um, choose to do operations on whatever qubits you want to, the same way that you can in this space. There's some kind of physical topological limitation to how you can actually do your algorithms. And that's something that you need to think about. Now, each one of these platforms comes with their own challenges. Everything that I've mentioned here has been in the context of superconducting qubits, which um, is not the only way you can do quantum computing. There are many other ways that we will be discussing throughout this meeting or this event. There are trapped ion qubits, there are photonic qubits, not mentioned here, but there are also spin qubits. And they're all ways that people are trying to realize quantum computings to address all of these challenges. Some of them are very scalable. For example, photonic quantum computing is great for scalability. But photonic quantum computing has a lot of noisiness, and it also doesn't have nonlinearity, which is a topic that will be discussed in the next lecture. Um, Trapped ion qubits are very coherent. They have low noise, but the problem with them is that they're very slow, and it's hard to get multiple of them to talk to each other. So each one of these different hardware platforms has their own challenges to them. Not only that, some researchers and companies are already looking ahead. So you can't just use the laws of quantum technology only for quantum computing. You can also use it to protect against itself. You can fight fire with fire. So there are some algorithms. For example, one popular one, which is going to be discussed this week, is the BB84 protocol with quantum key distribution, which is a way to protect against quantum computers breaking RSA encryption using quantum mechanics. I shouldn't say that it protects against them breaking RSA encryption. What I actually mean is it's an alternative to RSA encryption, which is resistant to quantum computers. And people are thinking about doing this in free space. So just using lasers, a bunch of mirrors, and a bunch of photon detectors. But then there are also people, this is quite a new field, thinking of doing this BB84 protocol on chip. And over here, I have a Nature paper that you can take a look at, which is just a realization of the BB84 protocol on chip. Actually, sorry, I believe this one is a different protocol, but it's QKD on chip. So this stuff is really awesome, right? Um, it's a really cool field. It has a lot of problems, and it's clear that there's a gap that needs to be addressed. So, obviously, for an aspiring undergrad, this would be something that is like amazing, and it would be great to get into. So what I have here is actually the most recent example that I pulled straight out of my inbox. You can see this is dated November 12th at 7:34 p.m. I got this email to my inbox about a quantum hardware position. Hello, Kieran, and I've bleeped out the company, obviously, for confidentiality purposes. I'm recruiting for a position at blank at a junior role, and I believe your skills and experience could be a good match. You should really consider joining our team. Here, your opportunity to make an impact is endless. We can't provide you any money to relocate to our role. This role cannot be done remotely, and we will only review candidates who apply with the following qualifications. You need to have a PhD, you need to have practical experience, you need to have research experience in quantum algorithms, a proven record of publications, and expertise in hybrid classical quantum variational algorithms for a junior role. So what this means is if you're an undergrad, you see these kinds of things, you think they're awesome, they're so cool, you want to get experience, you want to learn about them. At minimum, what these companies are expecting you to do is they're expecting you to go through your entire undergrad. They're expecting you to do your master's, do your PhD. Once you do your PhD, have experience in all of these softwares, which you can really only get at the master's or PhD level. And then after that, you can just start to break into the field where you're able to address these problems. Now, what we're trying to do is we're trying to bring this barrier down. We're trying to say that you don't need to have a PhD to be able to understand or at least get an idea of the problems that are plaguing this industry today. So we've worked really, really hard with both Ansys and COMSOL to get you guys the licenses that you would be using to solve these kinds of problems, to give you a taste of what the field is like. So obviously, over the course of this week, we are not going to be expecting you to solve the problem of qubit scalability. We're not going to be expecting you to come up with some novel platform that is going to be like a Nobel Prize winning thing, or crack this 2048 bit long key and win the $200,000 prize. But the goal of this week is going to get you guys thinking about these problems. It's going to give you guys a small bite-sized piece of the real problems that are facing the quantum hardware industry. And it'll give you the tools that you need to understand where you want to go and what you want to tackle in the field. So that is the motivation behind this event. And what I'd like to do is right now, I'd like to give a shout out to CMC and Fabric, because personally, this is where I found out about all of this stuff. They give a lot of very, very affordable workshops in this field. I mean, relative to a lot of other places where you can get this technology. So I would highly recommend that you guys look at the CMC events page and the Fabric Innovation training page. This is a Canadian service which is working on this exact problem, except it's more targeted towards graduate students, although I would argue that it is very accessible for undergraduate students. So what I have here is a workshop that they actually just ran last month, October 20th to 24th, called Build Your Own Superconducting Quantum Device Workshop. It just took place at University of Waterloo, but they run this one every year. They also run another one every year, which I think is fantastic, called the Quantum Photonics Workshop. The prices are $300 if you're a student for this workshop specifically, but they're in the same ballpark for anywhere else. And they will give you a week full of that's packed full of lectures, and they'll also handle all of the licenses and sort all of that for you. So I have the links here. I'll post these slides after. I would highly recommend that you check this out. So now let's talk about what you're actually going to be doing this week. So at a glance, today and tomorrow are going to be packed full of workshops, because obviously we're not coming in with the assumption that you understand and you're already an expert in all of these softwares. The goal of this is to teach you these softwares and how they're used and how you can actually build qubits, how you can actually build these things in the space of QKD. So today and tomorrow are going to be packed full of lectures in 3 different fields of quantum computing. Sorry, not quantum computing, of just quantum physics and different applications of quantum hardware. What we're going to do is we're going to start with a theory workshop, which is going to give you a crash course in the field, the motivations behind why people are taking that approach, a little bit of the math behind like what you're looking for, what kind of things are relevant for that specific application or that specific realization of a qubit. Um, then we're going to give you a workshop in the software. So that's one workshop in COMSOL, one workshop in Numerical, and one workshop in Ansys HFSS. And then we're going to give you a problem-specific workshop. So the problem-specific workshop is going to be um, a example problem, which we'll give you, which is very related to the problem that you'll be solving off of the week. And it'll be a problem that you can use as a base template to start your problem for the week and something you can build off of. Because obviously, for such problems, a week is very, very tight to be able to create something entirely from scratch. So after the 16th, we're going to have a week-long asynchronous work period. So November 17th to 21st, there's nothing that's going to be going on. There are not going to be any Zoom calls like is happening now. You'll just have time to work on your problem, and you can ask questions in the Discord. Although we're not going to be having any kind of office hours, you guys are mostly going to be on your own, and we'll just try and help with general questions regarding um, clarification for what is expected of the problems. Finally, we're ending the event with a bang at McMaster. So we have a hybrid weekend on November 22nd and 23rd, where we are having industry talk. We're having networking, facility tours, judging, and we're really excited to show you guys all of the cool facilities that we have here at McMaster. One of the things that we're doing are CEDT tours for um, a few of the participants is going to be first come, first serve, but you'll be able to see things like our clean room where we fabricate our semiconductors. You'll be able to see our MOCVD machine where we can grow quantum dots. So that's going to be really, really exciting. All the food is going to be provided for you that weekend. We are not doing accommodations though. So you guys will have to find your own place to stay from Saturday to Sunday, um, or you'll have to book a hotel. So let's talk about what's going to happen today. We're quite ahead of schedule. So this block is supposed to take from 9 to 10, which is what going on, an introduction to the hackathon, a brief overview of the challenges that are faced in quantum hardware. After this, CMC, who runs the fabric workshops that I mentioned before, are going to come and give you a lecture about superconducting qubits from 10 to 11. From 11 to 12, there's going to be a workshop given by University of Sherbrooke by Dr. Juan that's going to teach you how to use Ansys HFSS. After that, there's going to be a lunch break where we're going to take a break from Zoom. Nothing's going to be happening here, but we're going to have some icebreakers that are going to be running in the Discord. So you might have noticed in the Discord, there are a few team formation channels. There are also some channels that are specific to the university that you're from. Um, During this time, this is a time for you to hop in those channels and meet your peers and network and form your teams. Um, After 1 p.m., we're going to be hopping back on the same Zoom call, and we're going to continue the rest of the workshops. So the second one that's going to be given by Dr. Juan is going to be an Ansys HFSS specific superconducting qubit or superconducting circuit challenge that's going to help aid your design challenge over the week. Then we're going to shift focus to trapped ions. So you're going to get a lecture from IonQ or Michael Silver from UofT. You're then going to get a workshop from a professor here at McMaster University named Dr. Welland on how to use COMSOL. And then a similar idea where you're going to get, you're going to get a workshop on trapped ions inside of COMSOL to give you that initial template that we're talking about that you can work off of for your week. So a couple final notes that I want to address. Due to the nature of this event, it's unfair for graduate or PhD students to be put on the same playing field as undergraduate students. Many graduate or PhD students are already going to be proficient in these softwares and have some experience doing the kinds of things that we're going to talk about in this workshop. So it's not fair to pit them against first years, second years, third years, fourth years that are going to be competing in this event. As such, we're saying that if you have a graduate student on your team we did get some signups for graduate students and PhDs. The graduate students and the PhDs are not allowed to win. So you are more than free to compete. You're more than free to present your challenges, but we cannot give you a cash prize. You are not allowed to win the event at the end of the thing. It has to be an entire undergraduate only team. Now, when I say graduate, I want to be careful because if you finished your bachelor's, that's okay. As long as you're not doing a master's degree or you hold a master's degree, this will apply to you. Um, as I mentioned, we aren't going to be doing accommodations on the Saturday evening. Um, and I think that is pretty much all of the notes that I have for now. Um, there is about half an hour before we start our next talk, so I'll open the floor for questions now. So you guys can unmute or you can just drop them in the chat. Um, okay, Mila asks, if we can't make a lecture, will there be a recording posted? Thanks. Yes, Mila. Our lectures will be recorded and posted. So this lecture is being recorded. It's going to run the whole day. And then we'll post them probably either on a Google Drive or on a YouTube at the end of the day, just because the size of the lectures are going to be, or the size of the recording is going to be very, very large. Does anybody else have any more questions? How can we assign the team if we didn't specify it uh, during registration? So, um, what we're going to do is we are going to provide a form. So keep your eyes on announcements. We're going to provide a form to you that's going to be open until 10 p.m. on Sunday. So 10 p.m. on Sunday, you have to get your form in with a team. I know that in the sign up for this event, it said that you could have teams of up to three. We have since changed that to be teams of up to four. So over the course of this event, you can find your team, you can make them, and then you can fill out that form and close that form. Now, the thing is, you have to fill out that form by the end of Sunday because we are doing our judging based on the teams for that form. And I will say, even if you have already filled out the form in the registration with the team, please fill out the form that we're going to send out again by Sunday. Um, Will Haynes is the person to contact about that. The next question, can you please tell me which specific sub apps or features we need to have for Ansys HFSS? Um, Mazen, I'm not entirely sure what you mean by sub apps or features. Um, I can maybe tell you about like for my installation process when I was beta testing the Ansys HFSS problems. I didn't install any extra modules, if that's what you're talking about, directly from the download link. I just installed the software and then I just like clicked through all the pages. I didn't need to install any extra modules or sub apps. Just the base Ansys HFSS was fine to open the files. Yeah. William asks, are we going to get help with downloading and using our software? William, unfortunately, you will not get help with downloading and using our software. We don't have the bandwidth for that this weekend. We did post about that over the course of the last 2 weeks because um, it is difficult to get some of the software working, and the intent was that you had everything working by now. That being said, we'll still try to help. So in our Discord, we have these channels for HFSS issues, numerical issues, and COMSOL issues. Um, I don't think that HFSS or COMSOL should give you too many problems to install. Numerical is the one that is the most difficult to get working. But anyway, sorry. My point is that our priority this weekend is not going to be helping out with software related problems, um, but still try and install them. If you haven't seen already, we do have a software installation package. So if you go to Discord, and then you go to HardHaQ, and then um, software installation package. Sorry, I actually think my Zoom screen isn't sharing this, but there's a channel inside of the Discord called Software Installation Package. And at the top of that channel, there's an installation guide which will help you install everything. And I would recommend reading all of the messages in that channel. One thing I want to say now is I got a lot of questions about Ansys Numerical, and when you went to install it, needing something called an account number. I will say I have downloaded the installer and I posted it to a drive in a future message inside of that same software installation channel. Download the installer from there because you don't need to use the account number, and you can proceed with the rest of the installation as normal. Sharvesh asks, will I be able to present my solution online for the hackathon if none of my team members can be in person? Yes, you will be able to present your solution online for the hackathon. So actually, I think maybe that's one thing I'll go over now just to clear things up about how exactly the judging is going to run. There will be more details on the judging also talked about at the end of this weekend. So at the final talk, when we reveal the problems on Sunday, we'll talk a little bit more about the judging. But I will share my screen to discuss exactly how we're planning on doing the judging. Just making sure you guys can see my screen. Okay, it says you guys can see my screen. So the in-person component of our event is taking place in MDCL. What we're planning on doing is we have 3 rooms that are booked out. I believe they're either these 3 up here or 11:15, 11:13, and 10:09. Um, each room is reserved for one of the 3 particular challenges that you're going to be working on this weekend. We're going to have someone in there for AV. So each one of those people are going to be in their own separate Zoom call, very similar to this Zoom call now, but the Zoom calls are going to be specific to the problem. We're going to have a form that goes out next Saturday, which is going to be like your submission form. And on that form, you're going to indicate whether you're attending in person or online for the judging. Once you indicate whether you're in person or online for the judging, we're going to have runners. So you guys are going to be in these 2 lecture halls, 11:02 and 11:05, during this time period. We're going to have people walking you in person from the lecture hall to the corresponding room to be judged if you're in person. If you're online, Emily is going to be pinging you and telling you to join the online Zoom room. So in essence, it's going to be the same judges that are marking you, like whether you're online or in person, but it's going to be a hybrid aspect where like you can just attend virtually for your problem in a Zoom call, and then you'll be up on a screen where our judges will mark you like in person, but like they'll be able to see and hear you because you'll be up on the screen. And if you're in person, you can just go in and present normally. Um, that's how we're planning on doing the judging next weekend. So it is totally fine if you come if you need to present online. That being said, uh, we'll ask that either your whole team comes in person or your whole team presents online just to make things simple on our end. Um, any other questions? Where is the attached Ansys for Ansys numerical posted? I don't see attached to the message in the software channel. Yes, so the here, sorry, stop sharing my screen. The installer is just posted here. Um, One more thing I will say, which I think is an important point for this event, is you will be presenting on one of the three challenges. So, although we are giving you workshops in all three of them, you're free to try all three of them, but your presentation will only be on one challenge. So if there's one software that you can't get working over the course of the weekend, it's okay. It doesn't mean that you can't participate in this event at all. You can just choose to participate in one of the challenges for which you did get the software working. So for example, like if numerical isn't working or COMSOL isn't working, you can then just do the Ansys HFSS challenge, or you can then just do whichever challenge is working for you. Does anybody else have any more questions? And I sent that link to Mila in the DM, but I'll just paste it here for everybody to see. So this link will just take you to the Ansys installer. This is just to make sure you don't have issues with the account number as detailed in the hackathon guide. Which software are going to be used to solve the specific challenges you talked about? So, um, the software that's going to be used are the same ones that are in the corresponding lecture block for the challenge. So, without saying too much about what the challenges actually are going to be, the superconducting problem is going to be solved with Ansys HFSS. The trapped ion challenge is going to be solved with COMSOL. And then our QKD challenge is going to be solved with Ansys Numerical. So today you're going to get workshops and lectures on Ansys HFSS and COMSOL, and the entirety of tomorrow is going to be dedicated to Ansys Numerical. Is MEEP also an option among the three other softwares? Yes, that is a very good question because we did have MEEP as one of the things in the installation guide. So MEEP is not a standalone alternative to Ansys Numerical, and it will not be sufficient to solve the challenge over the week. The reason why we had to install MEEP in the guide is because it is also a finite difference time domain solver that's free and open source. So um, we thought it would be interesting to discuss it and discuss its use cases because it's something that you can just use whenever. And also its pros and cons and limitations when compared against a nicely bundled package thing like Ansys Numerical. So Meep in and of itself is not going to be sufficient to solve one of the problems of the week. But it's more of something that will complement Ansys Numerical. One thing I will say about Meep also is Meep doesn't have a Windows native installation. I think I talked about this in the install guide, but you're going to need to install WSL, which is basically like a Linux shell for Windows in order to get that working. I put all of the commands that you need in order to get it working in a LaTeX document in the install guide, but that LaTeX document, for some reason, when you copy and paste from it, it changes the spacing inside of the command so they look different. So what I will say is if you are trying to install Meep, make sure that your commands look the same as they do in the document, as in spacing wise, because it might just add a few or add a tab, which will make the installation not run. Okay, if there are no more other questions, I do see that Charles and Matthew are also already here in the call. So if you guys would like, we could start the next section a little bit early. Um, Also, if you want, one of the things that I talked about, Charles, was I brought up the CMC workshops and I brought up Fabric. So if you'd like to take this time to talk a little bit more about that as well, you're more than welcome to.
Thanks, Kieran. Thank you for mentioning this our event as well. So as Kieran was saying, every year CMC has been running workshops for the last 5 or so years with the quantum team. And then with Fabric, which is a federal government program, we've also expanded our training activities and we've received support for all of those trainings. So we have quantum workshops on quantum hardware, like the one Kieran presented. We also have a similar quantum workshop for software applications. And then we also run softwares for photonics, microelectronics, nanofabs, MEMS, and other technologies that CMC supports. So we run this workshop every year, and then typically alongside the workshop, there's a fabrication run that CMC supports that you can take part in and get some fabricated chips. And then you're able to receive those chips and then test them in your labs or in some facilities like the Sherbrooke Ansys Quantic Fab Lab, which is able to rent some equipment and lab space for you to measure your devices in. So we're very happy to support this hackathon uh, and help Kieran and his team with such an event. Our goal at CMC is really to facilitate adoption of technology across Canada. So our activities are mostly geared for students, graduate students, but we also support startups and companies across Canada as well. So I'm happy to take part in this event, and I could always start early if it's okay with everyone.
Yeah, I think it should be completely fine if you want to start
Okay,
now.
perfect.
Do you
So
have
this lecture, yep,
screen
sorry.
share permissions?
Uh, Let me see. It should begin to come up. Are you able to see some slides?
Yes.
Perfect. Yeah, so my lecture today will be sort of split into two parts, and then I'll leave some time after the first part if we have some questions before we dive into the second one. So welcome everyone. So I'd like to begin this lecture on sort of the theory of superconducting qubit circuits and devices by mentioning some of the recent news and advances in the field. So we've had for a few years now, IBM and Google has been two of the companies leading the development of superconducting qubit platforms. And IBM has had multiple quantum computers that are accessible by the general public. And Google has also been publishing some quantum supremacy or quantum advantage work and results that they've been doing. So as you can see, these are devices that have a fair number of qubits on them. IBM is in the hundreds range, and they're planning to get to a few thousands in the coming years. And then Google are also in the 50 to 100 range in those results. So they typically use a superconducting qubits that are inspired from a so-called transpond qubit, which is a device that we'll talk about today in this lecture. And within the family of superconducting devices, there's qubits, of course, but we also have other circuit elements like microwave resonators, parametric amplifiers, that have some use outside of quantum information only, but they're also part of a full quantum chip. So as you can see, both of these systems, they are made of a network of qubits coupled to other qubits. There's not all-to-all connectivity, but it's typically nearest neighbor connectivity or some sort of subunits that has a higher connectivity levels, and those subunits are joined to other subunits in sort of this lattice fashion. But we've had in the recent years some very promising results with regards to eventually scaling up those systems to more useful levels. So, as Kieran was mentioning, one of the problems with qubits is that they're fairly noisy at the moment. And so the lifetime and the performance of physical qubits is limited by the various sources of noise and error channels. And one of the ways that we can mitigate this effect is by using quantum error corrections, which is more at the software level or algorithmic level. And one of the well-known error correction code is so-called the surface code. In the past, so the way this works is we're using a set of physical qubits to encode one logical qubit, and the goal is to have this logical qubit have better performance and a longer lifetime than the physical qubits that are used to create this logical qubits. And so this surface code is based on a parameter called the distance, which is related to how many physical qubits we are using to encode the logical qubits. So as you can see, the little colored outline in red, orange, and black are associated with a specific value of this distance parameter. And the graph here in the bottom shows some results from improvements in this error correcting code. So in the past years, if we look at the gray and the black lines and dots here, we see that the error probability, as we do more and more cycles of error correction, increases faster than the performance of the dashed lines, which represents the performance of our physical qubits. But what this paper showed from last year is that they've managed to achieve what we called going below threshold, so that the logical qubits, the error on the logical qubits, actually scales slower than the errors on a physical qubit. So this is an important step in scaling our qubit, our qubit systems, because this means that we can actually improve the performance as we scale up of our logical qubits relative to our physical qubits. So the better our physical qubits are, this will also be reflected in an improvement in the logical qubits, but it's also possible using software to sort of deal with some of the errors that we can have in our physical hardware circuits. So this is a very good news, and it's encouraging in our pursuit of fault-tolerant quantum computing. We're not there yet, but we're slowly moving towards it, and that's very good news. Another thing for which those quantum devices are useful for is what we call quantum parametric amplifiers. And these are comprised of a device, a Josephson junctions, that I'll present today. And this is these amplifier types are actually very useful because they can be quantum limited. So that means that they had as little noise as physically possible. And so they're mostly useful for quantum circuits where the noise intensity is, where the signal intensity, forgive me, is very, very small. And it's also useful to improve, for example, the readout capability, where you can do single shot readout and differentiate the states of our qubit fairly well. And it can also be used in other applications, such as for improving magnetic resonance and other applications. So how do we do quantum information processing with superconducting qubits? Well, a qubit is, in essence, a two-level system. So it's the equivalent of having our classical bits. So we have a 0 state and a 1 state. And because we are quantum, we can do some more interesting states, such as superposition states, but we'll get into that a little later. So we'll have a series of qubits. So we have qubit control for each of these, which can be done with microwave signals, typically RF signals in the frequency of gigahertz. We have what we call qubit entangling gates to make use to encode information and process it, and to interact multiple qubits together. And then at the end, we'll have a readout that is going to give us the classical result of 0 or 1. So this is going to give us the final state of our qubit, and the result of our computation we have if we've just run an algorithm on it. We can also have multiple qubits connected to a quantum bus, on which these qubits are multiplexed. So we can do readout on this quantum bus, and then read out all of these qubits. So let's see how it looks in practice and how we describe this system mathematically. So the formalism that we're using is called circuit quantum electrodynamics, or circuit QED. And it's basically making an analogy with an atom in a cavity, but having our qubit be the artificial atom and having our resonators and other circuit elements be our cavity. So the cavity is typically composed of a superconducting resonator. So it can be a coplanar waveguide transmission line section of a certain length, and that length is proportional to the wavelength of the target frequency of our resonator. Either we have a half wavelength resonator with two open ends, so with little gaps at the end. This would be an example of a lambda over 2 resonators, or you can have lambda over 4 resonators, where one of the ends is shorted to ground. And these are used to perform readout and also to couple qubits together. So the typical frequency range of these devices tend to be between 4 and 10 gigahertz. And that's also a typical range of control electronics frequency signal generators that we have. And then the equivalent of the atom in this formalism would be our qubit. So our qubit has a transition frequency, which is similar to the frequency you need to excite an electron on an atom to have it jump to another orbital. So this is a specific frequency that we can engineer. This will be our qubit frequency. And ideally, we want this qubit to have a coherence time as long as possible so that we can run more and more operations before having to reset the whole system. So the way we can manipulate, control, and read out the system is that we're going to send a microwave pulse at the frequency of transition of our qubit, omega q, and this will allow us to control and change the state of the qubit between 0 and 1. And then if we want to do a readout instead, what we're going to do is we're going to send a pulse at the resonance frequency of our resonator instead, and then we'll measure the transmission profile at this frequency, and this is going to tell us indirectly what's the state of the qubit. And I'm going to show you mathematically how do we arrive to this result and which kind of frequency regime we want to operate the system. So it's also possible to use multiple qubits in a system like this, and each of these qubits will have its own transition frequency so that we can address each of them individually. And then we can also have resonant coupling sections between qubit pairs. So the way we would do is we would excite a photon or an excitation in our qubit. As the qubit is coupled to the resonator, this photon or excitation can go into the resonator. It can travel alongside it, and then we can measure what happened with our circuits, or we can have this photon interact with another qubits if we're doing 2 qubit gates. So this chip image here represents a recent design of a 4 qubit chips. And as you can see, we only have 4 qubits with couplers between each pair of qubits. Each has their own control control line. So in blue is the flux line because we have tunable couplers and tunable qubits. Then we also have other control lines and readout lines. And then you can see here that we have squiggly lines which form a resonator. And you can see that these are all doubled. And this is related to a concept that we call per-cell filters. So per-cell filters are a way we can improve the response of our system at the resonator frequency, but also suppress the coupling at the qubit frequencies in order to avoid information leaking out from our qubit into the resonator. And so this tends to improve performance of our systems. And I believe Mathieu will talk a bit more about per-cell filters in detail later today. So for today's lecture, the main content of it is I'll begin by describing an LC circuit, which is our resonators. And then I'll show that what formalism we can use it to describe it in terms of quantum mechanics. Next, I'll introduce the Josephson junction, which is a key part of our qubits. And the Josephson junction is a nonlinear device that acts as the inductance in a nonlinear LC circuit. And this basically is what our transmon qubit is. It's a nonlinear inductance coupled with a capacitance in parallel. And with this, we can form a two-level systems, a qubit. So I'll show you a bit how we describe this. And then after this, the important part of today is reaching the interaction level. So the resonant regime and then the dispersive interaction or dispersive regime that we use for readout. And how we can basically ensure that we properly control our two levels of our qubits and that our readout does not destroy our quantum states when we want to measure the qubit. And if I have some time at the end, I'll try to get into a little bit of qubit-qubit interaction and how this can be mediated. And if you're looking for some article references, one great paper on this is Circuit Quantum Electrodynamics by Alexandre Blais, who's also a professor at the University of Sherbrooke. And Alexandre Blais has a couple papers on this formalism, on this description, and then on transmon qubit as well. So it's a very good reference to look for. So an LC circuit is basically the electrical equivalent of a mass of a system of a mass on a spring, and then we'll see how these two systems actually map out from one to another. So the LC circuit is characterized by two main parameters of control, so the inductance and the capacitance. These are parameters you can design when you're creating a circuit. And from these two parameters, from the inductance and the capacitance, you can obtain the resonance frequency of the system, which is given by 1 over the square root of LC, and also the impedance of this circuit components. So the impedance is given by the square root of the ratio of the inductance over the capacitance. And the reason why the impedance is important to us is that all the electrical control elements, so the control electronics, they're all standardized the 50 ohm impedance. And if the impedance of your circuit or the impedance seen by the cables from your circuit is different than 50 ohm, what you're going to have is you're going to have reflection and those interfaces of contacts. And that reflections will cause interference, and thus it will introduce more noise, and you'll have signal loss as well. So this impacts negatively your performance. Yeah. So the impedance is determined mostly by the ratio of L over C, while the frequency itself is impacted by the absolute values of those values. So typical value range for these parameters in our circuits will be a few nanohenries for the inductance and then some picofarads for the capacitance. And this gives us a frequency range in the gigahertz and an impedance of 50 ohm. So at these frequencies, the wavelength for 5 gigahertz is around 6 centimeters, whereas we can have lumped element circuits with circuit dimensions on the orders of a few hundred microns. So we can treat these components in the circuits as point-like structures, and we can use the lumped element circuit model for the following equations that we're going to have. And then instead of having, let's say, the the position and the mass, as we would have with a spring, with a mass on a spring. The variables in our systems that we're going to be using here are the flux and the charge. So having this, we can start to define how we, by convention, what's the voltage and the current, and then the charge and the flux in this circuit as well. And then we're going to look at the definitions of the energy stored in the system. So the flux is defined as the integral over time of the voltage. So the derivative of the flux is equal to the voltage, and then the derivative over time of the charge is equal to the current. So we're going to use those definitions later on. And then the energy is simply, in an electrical system, is simply the integral of the voltage times the current over time. So if we look at the energy stored in the capacitor, we can use these definitions and the equations that we have and some equivalents to obtain simply that we have C over 2 times the square of the voltage with this definition above. And doing the same from the inductance, we can reach this value here, where we have 1 over 2L times the flux squared. So if we look at the total energy, we can see that this is actually very similar to the equations for a mechanical oscillator. And knowing the definition of the resonance frequency that I was just shown prior, we can rewrite 1 over L by C omega R squared. And we have exactly the same form of the equations. So we can map the mass to the capacitance and then the positions to the flux. So this energy gives us a kinetic energy associated with the capacitor and then a potential energy that's related to our inductance. Next, in physics, we would do the Lagrangian and then the Hamiltonian in order to obtain the equations of motions and then the energy of the system. So using the same mapping, what we can find is that we have the same form as if we had a classical harmonic oscillator with the frequency of omega r here, and then the solution is also a sinusoidal or cosine in this case of the flux for time. Having this, we can write the electric and magnetic energy, and then if we sum the energy in the system, what we find is that we have a constant. And because we're using superconducting elements, there's no resistance, so there's no dissipation. And so this oscillation between the electric and magnetic energy can go on basically forever. Next, we would do the Hamiltonian. So by definitions, the Hamiltonian is written like this, with this stylized L being a Lagrangian. And in other words, it's the summation of the kinetic and potential energy. Having this, we can promote the variables to quantum operators with the canonical commutation relations that they obey. And then this gives us basically the quantized energy levels as a function of the excitations in our systems. So each of our energy levels in this harmonic oscillator potential are separated by h bar omega r, which is the resonance frequency in of our system. And to note is that if these the width, so basically the vertical width of these energy levels is much smaller than the separations, then our levels are well defined. They don't mix with one another. And then if the temperature of the system is low enough that the thermal energy is lower than this separation between our levels, we don't have constant excitations from the noise, so we can have we can see quantum effects that are dominant rather than being drowned out by the noise. So one thing to note is that for the typical frequency range of these systems, the thermal energy has to be smaller than 240 millikelvin. So this is also one of the reasons we need to use dilution refrigerator to operate those superconducting circuits. We also need the dilution refrigerator to be below the critical current of our superconductors. But even if we have higher TC superconducting circuits, it's always for quantum chips in particular, we want to operate them at the temperature as low as possible for better performances. And then with resonant circuits, one other metric that we use is the quality factor, which is also represented by Q. And this one is basically the frequency divided by the photon loss rate, kappa. And the idea is the energy stored in the system has to be much higher than the loss rate of this system. And we can routinely get quality factors in a range of, thousands to a million. 10 to the 6, 10 to the 7s are fairly common and easy to obtain. And then if you really push it, you can reach 10 to the 8 quality factors, which are pretty decent. And kappa is something that will come back later on, so the loss rate, but it's going to be important in evaluating our performance of our qubits and then how easy it is to read out later on. So one thing that we can do with this Hamiltonian is that we like to rewrite it in terms of the creation and annihilation operators. And this is useful in order to get a simplified form of the Hamiltonian that simply depends on the number of photons or excitations present in our system. And then we have an easily, basically just an easy multiplication factor for the energy associated with each of these excitations. So I'm going a little bit fast on the math, but if you need the slides, you can find them all in the Alexandre Blaise paper, all these mathematical developments. Otherwise, you can always ask us and we can get you the references that you need to find it. So the importance here is not necessarily to redo all the math in this lecture, but it's mostly to find out where it leads to in some of the definitions of important parameters that we can simulate with the tools that we'll present later on, and also the parameters that we control as a circuit design. So we can see that in this circuit we can have fairly decently large voltage fluctuations. And then we'll see one of the ways that the transformed qubit deals with these charge noise effects by design later on. So an LC circuit can take many forms. So we can have 2D resonators. In a coplanar waveguide architecture, what we have is we have a central conducting line of a certain width W, space with a spacing to ground planes on each side, S. So the ratio of the W and the S dictates the impedance of this line. And then the length of this section gives us the resonant frequency. So you can see how the electric fields and the magnetic fields sort of take shape around this structure here. And what we have is we have basically a fundamental mode, which would be our first peak, and then we have the harmonics of this mode. So you repeat each omega r. So 1 omega r, 2 omega r, 3 omega r. You'll have a peak in a transmission. This will be the resonance of this system. We can also have 3D cavities that are used by some academic teams and some companies trying to develop new types of qubits. Some people have moved into 3D resonators in order to get, I think, higher quality factors. And this is the basically the energy levels and the potential. So the next part is, while it's good to have an LC resonator is completely linear, and the absence of nonlinearity means that we cannot use it as a qubit because we need the nonlinearity to encode and process quantum information. So what do we have access in the superconducting circuits? We have the Josephson junction, which is a nonlinear, non-dissipative element. It's fairly unique of its kind to have both of these characteristics. And so while we can use normal LC circuits for readout, control, and to couple qubits, and as you can see in qubit chips, there's a fair amount of resonators. For the qubit itself, we need nonlinearity. So, and we also need nonlinearity for quantum parametric amplifiers. And the building blocks that we use to realize those devices is the Josephson junction. So Josephson junction, what it is, it's very similar to a tunnel junction. So it's composed of two superconducting electrodes separated by an extremely thin insulator barrier. Typically, if you're using, say, aluminum as your superconductor, you'll have aluminum electrode, you'll have aluminum oxide, and then another aluminum electrode to form your junction. And then this element has a few unique behaviors. So you can have a current circulating between the electrodes through the barrier. without any applied voltage. So that's the zero bias current. And this current is driven by the phase difference between the electrodes on the left and the electrodes on the right. And this current goes as the critical current value, which is the current value after which you lose your superconductivity. And then you break basically the electron pairs that are formed when you become superconductor, the Cooper pairs. And instead, you're left with normal electron currents. So you'll have a relation between the current and the voltage that's the normal state resistance times the current gives you the voltage. Just like it is with normal electrical current. So the critical current is related to this normal state resistance, and it's typically limited by the size of your junction, so the area of the different electrodes that overlap, and also the thickness of this insulator barrier. So in our adjacent junctions, we have our current is driven by the phase difference, and then the voltage applied can also change the phase difference between these two. And also, if you apply too high a voltage, so if your voltage is bigger than the superconducting gap, you can also break the superconductivity. So typically, we'd operate these qubits within a fairly limited window where we remain as a superconductor. Otherwise, we lose the nonlinear effect that we're looking for. So the current is related to the flux here by this relation. And typically for a normal inductor, the inductance is simply is given by this relation here. So if we want to keep a similar formulation, we can simply use this relation here to define the relation between the current and the flux to obtain a nonlinear inductance, which is going to be our Josephson inductance. And we define it this way. So as you can see, it has a cosine term dependence, so it behaves nonlinearly with the flux. So you can think of it as the junction simply as a nonlinear inductor that we're going to slot instead of our normal inductance in the circuit. So we can have similar definitions that we had before, but instead we have our current is nonlinear. And so we can define Josephson in energy with a critical current, and then phi 0 is the quantum of flux, which is just a quantity that I think we have the definition in some of those slides, but it's just basically it gives us the periodicity of our response. Of our current. So we have similar definitions as before. So we just replaced basically with this equation here, and then the capacitance now is not just the parallel capacitance, but it's the total capacitance, because the junction in itself, being made of two metal electrodes separated by a dielectric or an insulator, also has an intrinsic geometrical capacitance. So we can follow the same formalism to quantize this circuit as we did before, and then we'll get basically to this result for the Hamiltonian. So we can define a charging energy, which depends on the total capacitance. We have now our charge that is a multiple of 2e, because our charge carriers in these systems are the electron pairs, the Cooper pairs, which are basically two electrons, so they have twice the charge. And then we have a charge offset as well, which can be coming from trapped charges in our systems, or also charge noise that can affect our system. So if we look at the potential for the system, what we can observe is, instead of having our in dashed line the typical harmonic oscillator potential, what we have is as we go up in levels, where the separation between the level is reduced by a factor of EC, which we call our anharmonicity. So this is an anharmonic oscillator. And we can basically focus on the ground state and the first excited state and use these at our qubits. So this one is separated by h bar omega q, and the other one would be separated by h bar omega q minus EC. And then the energy spectrum of the circuit is going to depend on the ratio between EC and EJ. And then we're going to look at what happens with different values of this ratio and then how it behaves. So in practice, in experimental realizations, we started first with the charge qubit, where EC was much bigger than EJ. Then followed a few years later the quantronium, where these two were fairly equal. And then after that, the transmon, which is something that's been used widely afterwards, is when EJ, so the inductive section of our potential, is much bigger than the capacitance, than the capacitive energy. So if we look at a few energy spectrums for different values of this ratio, we can see a few notable things happen. So first, we can see that the values of the energy, the separation between the levels seems to increase as we increase EJ over EC. And also you can see that they flatten a lot more when EJ is greater. And on the x-axis here, we're looking at basically variations in the charge noise. So in the charge offset, NG. So one important thing to note is that if you take this regime where they're both equal, and you want to operate your qubit at, say, one of those minimums of your derivative, to sort of be in a stable regime, you can see here that small charge offset changes basically this potential a whole lot. So this is going to affect the operation and performance of a qubit a lot more than if you're totally flat, like here. And what this means by being in a transmon regime, which is closer to D, is that you're fairly insensitive to charge noise. And this is good for us because it eliminates one of the noise sources in our systems, because we are not very sensitive to it. So this charge degree of freedom is not going to impact too much the performance of our qubit. And typically these days, to be in what we call the transmon regime, the ratio between EJ and EC is between 20 and to 80. So while the fluctuation of charge can be large for the transmon, we do have small flux fluctuation. And this is one condition that we're going to have in the transmon regime and in the results I'll present later on. So this is important to keep in mind, that when you're tweaking different parameters of your system, if you want to operate it as a transmon, you want to remain in this transmon regime, and you want small flux fluctuations. So we can do an approximation in powers of the flux. And we have the transmon notably as a weak enharmonic oscillator. And then we can use, once again, our creation and annihilation operators to diagonalize the Hamiltonian. And the idea is we want to look at what are the different terms in our Hamiltonians that are most important, and then how they behave and how they scale, and eventually how they interact with the resonators that we're going to add to this system to get the real circuit. So importantly, with this approximation, what we obtain for the frequency of a qubit is this definition here. So it scales proportional to EC and EJ, and then there's also anharmonicity here with the minus EC that gives us the frequency of our qubits. And then this minus EC here is basically the difference from the harmonic oscillator. And as if we had another energy level, you would see that the difference between F and then the next one would be reduced from E to F by another times EC. So as you go up, the levels are closer and closer together. But we really focus only on the base two levels here, J and E, which are the ones we use for our qubit. There are some more exotic types of quantum circuits called QDITs or QTRITs and other, which try to encode information in more than two levels. But for now, we'll just focus on the qubit and the two-level systems. So we want to investigate what happens when we place the qubit and we couple it to a resonator. So what we have in our circuit representation is we have our qubits, and then we have our LC circuits that we've described before. So we want to derive the Hamiltonian for the interaction between the two qubits. So we want to see what's the chance that excitations in the resonator or in the photon, or that excitations or photons in the resonator can exchange with the ones present in the qubit. And so we want to derive the strength of this interaction, so the coupling strength between these two circuits. So we can quantize electromagnetic circuits. We can use electrical Kirchhoff's law with the flux. So what we're going to have is we're going to define the flux around this loop, so the different phases of flux. And then we can also have the current going in and out of the node. And then we can basically use those definitions and then see what happens with this. And then we want to derive the equation of motion. So we can derive the same equation of motions from the earlier Lagrange equations, just like we did when we derived our Hamiltonian. But we can also use this method to get the equations that we're looking for. So then we can do, basically we have our kinetic and potential energies that we can define as function of these different fluxes. And the potential from the inductive energy, we can do the Lagrangian, then the Hamiltonian, and then we can get our equations of motions. We can neglect constants as they don't evolve in time. And then I'll get to the second part. So the important part of all this basically calculations, and we can do the full derivation and the rewriting of the capacitance, but the final result that we want to get to is this Hamiltonian here, where we have one term for the qubit with the B operators that refer to photons created and destroyed in a qubit. We have this term of second order in this. Then we have the resonator terms, and we have this last term here, which is the interaction term. So the interaction term describes the basically exchange of photons in a qubit and photons in the resonator. And then we have the definitions that we've found below for the qubit frequency and the resonator frequency. And importantly here, we have definitions for our coupling strength, which is a little obscure, but then we're going to work on how to find this more easily. And then if you're looking here, so C would be the coupling capacitance, and then C sigma would be the sum capacitance. And so this coupling strength scales as the ratio of Vj over Ec to the power 1/4. And then there's also an influence of the impedance and the resistance quantity. But importantly, in our experimental relevant limit, we typically have a coupling J that is much smaller than the frequency of our qubits. So while our qubits frequency is in the gigahertz, J is typically in a couple hundreds of megahertz. So we can perform a rotating wave approximation. So this is basically to say that if we have terms where we have sum of frequencies in this last terms due to the different products, those terms that rotate much faster than the other ones will tend to average out to zero, so we can neglect them. And we're going to keep basically the slow rotating terms, so these two central terms. And these terms are basically the destruction of a photon in a qubit and the creation of one in the resonator, and the opposite. So these are terms that refer to so basically to the transmission of an excitation from the qubit to the resonator and vice versa. And then we're gonna look a bit more at how this happens and what's the effect of it on the results we can find in practice. So we want to restrict ourselves to the first two levels of our system to make a qubit. And then we can also have a definition with the sigma, so the Pauli matrices here, to give us values depending on the state of our qubits. And what we have, this simplified form of the Hamiltonian, is the Jaynes-Cummings Hamiltonian. And this last term here describes the current exchange of excitations between the LC circuits and our transmon qubit. And we're going to look a bit further into how it works and what this means. So we have our so these are three terms. Here there would be some animations that don't translate well to PDF, but basically, if we're sending microwave excitations at the frequency of the qubit, the photon here will go from the ground state to the excited states, and then it can also exchange through this term here into the cavity, and then we can measure it out. So there's two main regimes that we'll want to cover. So there's the light matter interaction, So in the resonant interaction. So the resonant regime is when the frequency of a resonator and the frequency of a qubit are identical or very close. And in this regime, we're well coupled between the two. So what happens is that if we don't have any, or if the coupling between the two would be 0, and then the frequencies are the same, we have degenerated states. So one excitation is a qubit has the same energy as 0 excitations in the resonators, and vice versa. So what we can try to do with this Hamiltonian is we can try to diagonalize it with these blocks, J and then number of excitation in there, and then E and N minus 1. And then we want to see basically where it leads us. And then we'll introduce a definition, which is going to be this triangle here, delta, the detuning. So the detuning will be the difference between the qubit frequency and the resonator frequency. And when we do this diagonalization of the Hamiltonian, we can see here that there's this term that depends on the detuning that doesn't have the same size. And we have also this terms related here with the coupling. So what we have with this little matrix is that with a non-zero coupling, what we have is that our energy levels are no longer degenerated. Instead, they would split. So this one here would shift down by a matter of J. And then this one would shift, the one in the resonator would shift up by J itself. So we have a gap between the two that's related to this factor here of 2J, H bar, and then square root of the number of excitations. So we call this vacuum Rabi splitting, and this is something that was observed in practice in the what we call the strong coupling regime, where the qubit and the resonator are maximally coupled. And what we see if you look at the transmission of a signal based on the frequency of the signal you're sending through the resonator, what you're going to see is you're going to see two peaks. So the separation between the peaks is based on the coupling strength value. And then the width of each of those peaks is related to the photon loss. And then gamma here is related to the coherence time of your qubit. And in order to observe this splitting of the levels, so the lifting of the degeneracy, you need a coupling strength to be larger than the photon loss and the qubit decoherence. And you can see in this paper in 2004 that in dashed line would be the single peak if the levels were degenerated. But in practice, you can see the lift in the degeneracy, so you can see the separations between the two energy levels. The only problem with this, while it's useful to directly measure the qubit, is that because we're strongly coupled to the qubit, we can have excitations or in our qubit leak out into the resonator, and we can sort of lose our quantum states in our qubit. So we want to see, so for quantum information processing, that's not exactly the best. So is there another regime or another way we can set up ourselves to have a frequency of the resonator that would be dependent on the qubit, but we would not have the interaction term in our Hamiltonian, so that we wouldn't lose excitations, or we wouldn't have excitations in the resonators coming into our qubit and affected states. Well, there's actually a regime where we can achieve this that we call the dispersive regime, and it's where the detuning is large compared to the coupling strength. And then so in this case, the interactions between these two are due to virtual photons. So what we're trying to see is, if we have a high detuning, can we have can we have a transformation of our Hamiltonian that can eliminate this interaction term? So because J here is small, we can do a second order perturbation theory on this Hamiltonian. And we want to find a transformation U that would make this term sort of disappear. So there is such a transformation that'll be described here, and then we can do an expansion, and all the math is explained in the reference paper by Alexandre. But what we can get to basically is that we can show at the end that we have a term here that is solely of the resonator. this term here only involves the qubit, and then this term only involves the resonator operators, but it's dependent by sigma z here on the state of our qubit. So in this dispersive regime, what we have, importantly, is that we have a term for our resonator excitations that is dependent on the state of the qubit, as sigma z here is equal to either 1 or -1, depending on the state of the qubit. And then the frequency of a qubit is slightly shifted by this term here, J2 over the detuning. But as J is small, this is a small shift. So what this gives us, and we're happy to find, is that the frequency of our resonator is dependent on the state of the qubit. And what you actually see is that if the qubit is in, say, the up state, is in the ground state, then our qubit is shifted to the left by a negative value. The resonator frequency is shifted to a negative value. And instead, if the qubit is prepared in the other state, the frequency shifts in the other direction. So this way we can basically set excitations to measure the transmission across our resonator to see which state of the qubit is without transferring excitations into the qubit and doing and affecting it. So we can do what we call a non-quantum demolition measurement of our qubit. And then the next step would be, well, what happens? How can I make qubit-qubit interactions? Well, so if we had a second qubit in our system, what we can see is that we have two terms connecting each qubits to our resonator. So this is the summation of this term here. And what we can see in this graph is that for the first qubit, or qubit to resonator, you have this anti-crossing. But then you also have a second smaller anti-crossing here, and this one will be associated to our qubit-qubit interaction. So if we go into dispersive regime with transformation, just like we did, what we find is the effective Hamiltonian here. There is a term here that involves qubit 1 and qubit 2 to shift excitations from qubit 1 to qubit 2 and vice versa. And this one here, this term here, does not actually involve excitation in the resonator itself. But we have, so this term here is the term that shifts our resonator's frequency based on each of those qubits. So we have two terms here because we have two qubits. So we have this interaction J here that depends on the coupling of both qubits to the resonator and also the relative detuning. So between the qubits. But if we have, so if we have, as the qubits are far detuned, we can neglect the resonator term, and then our effective Hamiltonian, we can neglect this term here. So the effective Hamiltonian that we have, that's for the two qubit Hamiltonian, that interests us is really this term's for the qubits, and then this term here. So if we bring the frequency of the qubits to the same value, so this detuning here goes to basically is the same. So we have what we have is we get this value here for this coefficient J, and then if you wanted to do an entangling gate, what you could do would be to do a time evolution of this Hamiltonian for a time a given time pi over 4j, which would perform the 2 qubit square root of complex swap gates, which would entangle our 2 qubits together. And this was something that was done in practice, and we can see basically the two little anti-crossing between these two configurations. So this was a little primer, and then if you wanted to, you could basically do the derivation, but this is the same procedure as we've done multiple times this, just with the slightly different starting points. And then you can find all those papers as well in the in the references that are provided. So at this point, we have a little bit of time for any questions from the audience, and I'll be happy to try to answer them as best as I can. And thank you for listening. So as I don't see if there's any question in the chat, if one of the moderators or organizers could either point me those questions or read them to me, that'd be greatly appreciated.
If anybody has any questions, please feel free to write them in the chat so that either I can see it, Alicia can see it, or everyone can see it, and we'd be happy to read them out.
Okay, we've got one in the chat. It says, can you explain more on what the J term is toward the last slides?
Yeah, so the J term is the coupling between the resonator and the qubit. So the larger J is, the more strongly these two are coupled. So the easier it is for an excitations between in either one of them to transfer to the other ones. And the reason this is bad for a qubit is that for a qubit, every way you can couple to it is also a lost channel. And basically, anytime the environment or we interact with the qubit, there's a risk of causing a collapse of the superposition or of the quantum states. And so to get the best coherence time that we want to ensure that we have as little lost channels as possible. So this is one of the reasons where we want a detuning. So we want J to be small, but there's also a trade-off, because if J is too small, then it's very difficult to actually interact with the qubit. And as you can see here, to be able to really read out which state the qubit is in, if J is too small, or if J over the tuning is too small compared to our photon loss rate, then these two peaks can actually overlap. And so it's going to be difficult to properly read out which state the qubit is in. So J is sort of a critical parameter. It's one that you want to optimize when you're designing your circuits. So you want to really optimize J with respect to the detuning. So the difference between your resonator frequency and qubit frequency, which are parameters you can more easily sort of choose or design for. And then also kappa, the photon loss rate. It's important to ensure J is greater than kappa.
Thank you for the talk so far. It's been really interesting. Could you explain kappa, the photon loss rate again, and what that primarily is a function of?
Yeah, so the photon loss rate is basically the rate at which, if you have a photon in your qubit, it can leak out into the environment. So it can be to the resonator. It could be also to ground, or to in physical chips, we can have what we call two-level systems that can be sort of embedded in the material or in the substrate. And then these can sometimes enter in resonance with our qubit, and then you can have leakage this way as well. So the photon loss rate has, I would say, multiple potential sources. And typically that's something you'll find experimentally. You can sort of try to reduce the photon loss rate by having good quality materials, and then trying to make sure that your parasitic capacitance and inductance are as small as possible. And I guess one thing I could say is that we've mentioned capacitances and then inductance, but the parasitics values that you can extract when simulating your circuit, they also tend to account into the total capacitance and total inductance in our systems. So the greater these are, then those parasitics typically are negative, in that they negatively affect the performance of our systems. They're you can't entirely avoid parasitics, but it's important to get an idea of how important or what kind of range of values or how big they are relative to the designed inductance and capacitance values that you've engineered. So really the challenge with qubit is that in an ideal world, for the best performance qubit, it would be completely isolated from the environment and connected to nothing. But then the problem is if it doesn't interact with anything, that you can't actually control and read it out. Or at least you can do, or if you can do it, it's going to be extremely slow. So for practical quantum hardware, you want to trade off between how well it's isolated from inside environment, so the coherence time that you get from this, and also the coupling is basically tells you how fast you can execute your gates. So there's some trade-off there. You want basically your operations, your gates, to be much faster to execute than the lifetime of your qubit. Otherwise, you're limited to very few computations you can do with the qubits that you have access to. So there's a lot of efforts in the field to improve the coherence times of qubits by optimizing the design and the engineering and the fabrication. And then on the design circuits, there's also you can play on the coupling to see basically how fast you can apply your gates. So this is, one of the trade-off between different qubit architecture. It tends to be on which one has, a long coherence time, but then the gate speeds are very low, or vice versa, depending on which architecture you have.
There's another one in the chat. It says, could you also explain why qubits operate better at lower temperatures?
Yes, so this is this relative to the something I presented at the start, but basically every system has thermal noise. Right, let me just get. So basically, in every system, the thermal noise is given by the Boltzmann constant times the temperature, and this has a certain sort of energy value. And then the other energy sort of range in your system is h bar omega r, so it's the energy of your photons or your excitations in your system. And then if the energy of the thermal excitations in your system has an energy that's greater than your qubit, then they can excite photons. They can create excitations in your qubit. And this is bad because these are unwanted, uncontrolled, undesired excitations introduced in your system. And because the product of the constant Boltzmann time to temperature, when we compare it to excitations in the gigahertz range, which is the frequencies we operate our qubits in, to get an equivalent value, so for this equations to be equal, if the temperature is 200 millikelvin, and then I have a 5 gigahertz qubit, then the thermal noise can just naturally excite my qubits, and this is very bad. If we're at 10 millikelvin instead, then there's very little thermal excitations that have enough energy to excite my qubit. So my qubit is much better protected against this thermal noise than if I was operating it at a higher energy level. So, there's some photonics quantum computing that can operate at room temperature, and the reason for this is that in the wavelengths or the frequencies that they use, which are much, much higher than our microwave frequencies, then the corresponding energy of the photonic or laser excitations is much, much higher than the ones we're dealing with. So they're not. So basically, they respect this condition even if they're at room temperature. So ion traps and other systems like this, well, they do actually laser cooling, so they have similar actual operating temperatures on the ions that they trap. But yeah, so basically, it's if you're comparing against the noise in your system versus your signal, and if the noise is too close to your signal, then you have very bad performance. So by cooling down, we can suppress this thermal noise, and then we have our system where this transition here is not going to be excited by any random thermal fluctuations in our chip. That's really the key point here. So that's why even if we have critical temperatures with niobium that can be 9 Kelvin, we still want to operate them at very low temperature, as that tends to be better for our performance of our systems.
Great. Another one.
Yep.
Is the J term and the G term the same?
So the answer to that is no. So the J term is between a qubit and a resonator, and then the G term is actually between qubits and qubits. So what we have at the end is that the J term, is relative to it's with operators, creations of excitations in the resonator, but the G term only multiplies operators in each qubit. So the J term is really a qubit-qubit interaction, whereas the the French version of those letters is the other pronunciation. So the J term, this one here, is qubit-qubit, and then the G term is qubit to resonator coupling.
Awesome, thank you. And then we've got, you talked about parametric amplifiers operating near the quantum limit, but how do these amplifiers avoid adding a lot of noise to the qubit during readout?
Yeah, so parametric amplifiers, they do add a little bit of noise, but if it's well made, what they had basically is the Heisenberg uncertainty value. So this is the best theoretical performance you can hope for, and in practice is to add just basically half a photon of noise from your amplifier. And then, so if you're using, HAMT amplifiers or high electron mobility, I think transistors amplifier, it stands for, typically you're adding more noise than this, more multiples of half a photon of noise. And then so these devices, because I think we're making use of the nonlinearity of the Josephson junction and some of its characteristics to really create basically amplification. So the amplification factor might not be as high as other amplifiers, but as the first amplifier in a chain, this is so if you have multiple amplifiers in series, the dominant sort of noise addition to your systems will be given by the first amplifier in this chain. So if your first amplifier adds very, very little noise, then the noise added by the other amplifiers next in the chain has to compete with the amplified signal. So it's relative, in comparison, it's much smaller than if that was the first amplifier in the chain. So there are some references to find on the parametric amplifiers, but basically they're doing down conversions or spontaneous parametric down conversion. So they'll take, let's say, photons at a higher energy and then down convert to 2 photons at a lower frequency. But we can basically design them to have a first amplifier in our chain that adds very little noise. So the bandwidth of these tends to be fairly limited. So we're mostly focusing on our qubit frequency here, but then we have a fairly decent gain and we had very little noise. And we're basically, so I don't have a full in detail explanation just for you right now, but I can probably send you some references if you want to dive deeper into this. But there's been some research on parametric amplifiers. There's a few ways to realize them, but one of the I guess widely used these days is the Josephson traveling wave parametric amplifier, or the TUPA that we call it. That has shown pretty decent performances, and it can be incorporated into on our qubit chips to improve readout.
Thank you very much. I'm seeing now that we have about 5 minutes until the scheduled end of this talk, so I think we have time for one more question, if anybody has it. If not, I see that Dr. Juan is in the call. So I would like to extend a huge thank you to Charles for this wonderful talk. That was amazing, very, very informative. Thank you very much, and we appreciate it quite a lot. And I would now like to extend a warm welcome to Dr. Juan from University of Sherbrooke. And if you wouldn't mind just giving us a small introduction about yourself and your work before you start your presentation. Thank you very much. We're looking forward to it.
Yeah. Hi, everyone. Welcome. I'm really happy to be here. I'm Mathieu. I hope you can hear me well. Please let me know if the sound is not very clear. I sometimes have issues with this headset. Is it right? Yeah.
You're all right. You're good.
Okay. So I'm Mathieu. I started here in Sherbrooke like a bit more than 5 years ago now. And the research activities in our group are mostly focused on what we call hybrid quantum systems. So we're really interested in coupling different quantum degrees of freedom. And if I were to give one example of things that are really keen on developing is this notion of quantum interconnect. So if tomorrow you want to connect like a quantum computer that's based on superconducting qubits with one that's based on photonic qubits or neutral atoms, for example, then there is this issue that the superconducting computer will run on microwave signals and the other one on optical signals. So then you have to find this way to connect like quantum signals from microwave to optics. And one way to do it is to engineer those fairly complicated hybrid system where you have microwave, mechanics in our case, and then optics. And then you make sure that all those quantum degrees of freedom, they talk with each other and they can actually transfer information from the microwave all the way to the optics. So to basically like another way to see that is we somehow trying to develop a quantum modem so we can transfer and manipulate quantum information to be able to develop like a quantum internet. Why is it relevant? It would be hard to imagine that we will have quantum computer one day that are like just one gigantic quantum computer that can do it all. When with classical computers, after 100 years of development, we still have computers that are connected with each other in those high performance clusters. So even with classical computers, we need to connect them with fibers and we need to distribute calculation to be able to calculate very, very complicated problems. So this notion of connecting quantum computers is something very important and technologically relevant. So this is one of the things that we're really interested in. I won't go to mention the details of the other things that we look into in the group, but anything that has to do with hybrid quantum system where we play with different quantum degrees of freedom, this is kind of our jam, and we really like to do these kind of things. Maybe to finish my introduction, it's a bit lengthy, but sorry. My background is also fairly broad. I started in nano-optics, so I didn't start from the quantum fields. And then I moved to photonics and then quantum optics and now circuit quantum electrodynamics. So if you have questions about any of those things, I'd be happy to talk about them. That's it for my introduction. So today I will do something I find always very dangerous to do is I will try to guide you through using software to simulate a system. We'll be focusing on a high frequency system. So basically like a circuit. This is the tool that we typically will be using to develop our qubit circuits, for example. And as always, if you try to use a computer program live in front of an audience, for sure, some things are going to go wrong and it's going to be hard to find a solution. So I do what I can. I prepared some backup program that are already running. But yeah, that's it. The other thing also that's important for me to mention is please don't hesitate to stop me if you have a question or if you want to have clarification on something. I'm not an expert in simulation. I'm a lab rat. I like to be working with equipment and gizmos and technological things. Simulation is not my strong suit, but I'll do my best to actually guide you through what I know how to do and what is relevant for superconducting circuits. So now let me try this. I will share my other screen because I have the other computer where I do my simulation. Can I do this? I'll show the whole screen. Yeah, I can even check if it works. So if you're not familiar with HFSS, this is what you will see as you open Ansys Electronic Desktop. This is just the core program of HFSS. HFSS is high frequency simulation system. And the idea is that you can solve pretty much for any circuit with many different types of materials. So this is very suited for any type of microwave design or radio frequency design. Antennas is the typical application in the industry standards, or in our case, for superconducting circuits, right? So superconducting systems. One of the limitation I have to put forward immediately is it's not well suited to really simulate superconducting system and like really simulating superconducting properties by themselves. So we just use some shortcuts in the materials that we're using for the superconducting part of the system. So what I thought of doing today is to give you a short introduction about how to use this sort of software, is to show you how to design a simple system, a more typical system from the industry, and that will be basically a filter, right? So how would you go around to design your own microwave filter if, let's say, you want to have one specific frequency that goes into your system and nothing else? So if you open the program, you basically come in with this kind of empty window. So the first thing you have to do is you have to go in project and insert HFSS design. Takes a bit of time, but it will basically open up the whole modelization panel, for example. And this is where you start. So in designing a system, you really have to think of your system and building it up from the ground up, from the actual device you want to make, right? You can go arbitrarily high in complexity. So you could just simulate the chip and what you have on top of the chip. So for example, the tracks of your printed circuit board, but you could also go like much deeper and simulate the casing, the connectors themselves, depending on how much precision you want to have in your system. So if you were to simulate the box, for example, you would also have some information about the microwave box mode, as we call them, into your system. And if this is something relevant for you, or if you think you might have an issue with box mode in your system, I mean, HFSS will allow you to do that. Of course, the price to pay would be that it will be very long to actually simulate a very large system with many different modes and many different materials and the likes. So that's it. So there is many things that this software can do. So we're going to focus on a few key examples because I cannot cover everything in an hour. It will be way too much material, and it will be hard for you to remember all the tricks and tips in like an hour. So we're going to focus on what's called like modal wave port excitation. So it's like if you have a port, a connector that can carry pretty much any wavelength, how would your circuit behave if you connect it to this connector? The idea is that this is very relevant. If you just take a microwave cable and you connect it to your device, this will behave as a waveguide, so wave port. So the microwave cable can carry pretty much any frequency. There is some limit, but for the frequency range that we're using, it's very wide. So that's the approach we're going to be using. If you take up this challenge with the qubit design, superconducting qubit design, you will see some example of other ways to deal with the excitation of your system and other aspects of this HFSS simulation platform, where you can also use eigenmode solving, retrieving capacitance matrices, and this kind of things. So as always, in everything you do on a software, there is different level of knowledge in the software. I will put myself on the lower ones. I'm not an expert at using the software, so there's probably some much more efficient way of doing it, but the first thing you would typically do is you first design the box. That will be your sample. So you have, okay, sorry, and I'll start again. So you have those tools on the top here. You have 3D shape and 2D shape. We use both of them today. So the first thing you would do would be to draw a box, and then it's the first corner, second corner on a plane, and then you extend it on a Z direction. And you could either proceed like this and hand draw most of your things. The hard part would be that if you have to refine your design, it will make it super hard for you to change something, because you have to go in, type in new values and this sort of thing. So one thing that we typically prefer to do is, if you go on the box that you just created, you can double click on it, and now we have this property panel, as it is usual in most softwares. But the one thing that's nice with this software, or in other softwares too, is you can define some variables. So if you define variables right now in this sort of box, what it allows you to do is that you can change the variables of your project, and it will actually reshape everything. Okay. So for example, for the box, yes, there's a question. No. So for the box, I would call it WB. for the X and Y size. So as soon as you type in letters and you press enter, it will actually prompt a panel where you will have this value, so this parameter, the value for this parameter. So let's say we're going to make a 30mm by 30mm chip. Same thing for the Y direction. And then for the thickness, I will call it TB. So that will be the thickness of our box. And this is a bit more arbitrary. I think FF4 PCB, so circuit board are typically 1.6mm thick. You can have different thickness, but we'll pick 1.6mm for now. You have this, so this is your box. As you see, there is always some funky thing happening where the box is not fully joined. To solve this, you just have to click fit all. It took me like half an hour yesterday evening when I was trying to do a rehearsal of this thing to figure this one out. But if you have an issue of a 3D model not properly plotting, just click fit all, in the draw tab, fit all. So that's your box. So for now, we didn't do much. There's another important part is that now you see that my reference is kind of this weird corner. So every time I would add a new element in there, it will be a kind of a headache to place these new elements on my sample, knowing that my reference is kind of an arbitrary point. So the next thing you want to do is you want to redefine the position of this box, which is that defines the center of the box. So because my box is WB by WB by TB, one thing I like to do is having my reference at the center. So it's WB over 2 minus WB over 2. And for the Z direction, I like to have the plane on which I will work, the plane on which I will design my circuit. I like to have that at 0. So I would put the box and I will offset it by TB so that my reference is on the surface of this box and it's at the center of this box, right? So I feel a bit happier. I have my reference XYZ on the top of my box, and that box, in this case, as you draw a first box in HFSS, it will be defined as a vacuum bus. So you can see here in your model that you have the nature of each of your components, and for now it's just a vacuum box. So one thing you can do is you can click on the box, not on the component of the box, but on the box directly. And here you can see on the bottom left panel, you have the properties of this thing, and now it's called material vacuum, right? So you can click on vacuum, go on edit, and then that will open up all the materials that are already pre-coded in HFSS. I think you can also add your own materials, but the list is quite long. In general, you won't have much issues finding the materials you want. But this will work with a typical printed circuit board epoxy, which is called FF4. So why is it important? All the microwave properties of your system will be dependent on the width of the track, the exact structure of your track on top of your substrate, but also on the nature of the substrate. So the substrate, depending on its nature, will have a different dielectric index. So the penetration of the field will be different in there. Okay, I thought that was a very long question from Charles, but it's more like an answer. So now my box is now FF4. So you can go fancy. If you want to be able to navigate on your sample a bit more easily, you can also attribute some colors. Let's say for me, FF4, I like to have it like a cyan color, and I put a bit of transparency. So that will be my FF4 box is this thing, right? Or just a tip to navigate and to rotate. You can click on the wheel of your mouse and then rotate and move your sample around, right? So far I didn't do much. I just built my FF4 system. So now the next step is if you want to make a filter. So the filter will design as an example. I mean, it's just an example. We could have designed many things, but it will allow me to show you some of the tricks and some of the ways you can somehow programmatically design your system, connectors, strip lines, and this sort of things. So the system will be composed of 2 planes. So the back plane, which will be one of our ground plane. So what we'll do is we'll actually build, in this case, again, a box that will be the same size, but a very thin one, right? So this new box will be also WB. I want to use the same parameters. So that way if I change the size of my box, I can have the same, everything that moves the same way, right? For the thickness here, what I'm designing now is not the substrate anymore, but that will be the thin layer of copper that will be on the substrate, that will be on the FF4 for my tracks and for my microwave signal to travel through, and my ground plane. So what I'll do is I'll call that TCU for copper, thickness copper. And this is typically 35 here, the unit is there in micrometer, 35 micrometer copper thickness. So there's different industry standards, but 35 microns is the typical one. Same thing, minus W over 2, WB over 2, sorry. W over 2, and there, this layer, I want this layer to be the backplane. So I want this layer to be at the back of my FF4 substrate. So that will be minus T box. Hopefully I didn't make a mistake. No, that's right. So now we have the bottom plane and the top plane. Again, we can now attribute a new material to this guy. So vacuum, in this case, it's copper. So we attribute the copper material to this. And just so that we're consistent, we can decide that this is orange for copper, and copper is not transparent at those thickness. Ah, yes, I recolored my box. I was wrong. Orange for copper and not transparent. So now we have the first step for our system where we have the back ground plane, and now we have to do this again. So we can copy the first layer we did. Oh no, sorry, we don't do that. Sorry. So the thing that we're going to do now is to realize half-wave resonator to realize this sort of filters. So it's a filter that's going to be able to pass one frequency only. So what we'll do is we just rely on the resonance. The reason why I picked this example, it will be a fairly typical or not super useful. Do I have the DRA option? You don't have the DRA option in your HFSS. What do you mean DRA? Yeah, I'll keep an eye on the question. If you can explain a bit more about what DRA option is. Because I don't see any DRA option for me either. Oh, draw, okay. Oh, that depends on the version, right? So I know that depending on the version, this kind of top tab where you have the different element varies a lot. But you should always have on the top part here, the top navigation of the software, you should have a drawer, and then you should be able to find all the 2D shape, like 1D, 2D, and 3D shapes. If you don't have this kind of top panel, there's probably a way to show it depending on the version of your HFSS. So please have a look and let me know if you can find it. So the example I picked is this half length resonator. The reason I picked that, it's a typical microwave filter approach, but that also relies on a resonance, and that's exactly what you use for qubit readout, right? So you need a resonator for the qubit readout. So you look into some similar system later on if you do the qubit superconducting qubit design. So to do this, I need a resonator, and I need two connection from the input and the output. So what we'll have is three parallel slivers of copper. One is for the input, the central one will be the resonator, and the top one will be the output port. So the first thing we can do is I can draw my resonator. So the resonator will be again TCU for the copper thickness, and that will be the width. We'll pick I'll write it CW for the width. Oh, is it the width? No, that's not the width. I will call that L for the length of my half-wave. No, I will call it half-wave resonator, HWR. So that's my half-wave resonator. And the length, I noted it somewhere so that I can have a resonant frequency where I like it, around like 4 gigahertz. It's 18.7 millimeters. So this is part of the preparatory work that you'll have to do, is understanding what kind of system you want to design. And in this case, for alpha-wave resonance, around 4 gigahertz, turns out that if you do the calculation, it will be like a bit shy of 20 millimeter. So that will be my width, my length, sorry. My width, I will pick something like, oh, I need to check the width. So C width, So that's the copper width. For now, I'll put it to, I can't remember by head the value I need to check. I'll put it to 1.4 millimeter, and then I'll check later if this is a proper one. Now I need to position it. I want it to be at the center, so I will center it. And this is CW divided by 2. And now this is on the top plane, so I will keep 0 for the Z direction. Right? So now this is my half-wave resonator, right? So this is this thing that will be resonant only when I send a signal at 4 gigahertz. So when I send a 4 gigahertz signal, the signal will be able to couple to this resonator and go out the other port. Otherwise, this device will actually pass no signal through and through. That's the first one. The second one, the second box, I will just start from the same one. So that's my CL. I will do another variable. So CL will be just the port where I connect my microwave, the strip line where I connect my microwave. I will make it 10 millimeter, for example. This is not super crucial. And now this is where designing gets a bit more tedious. Is here I need to figure out exactly how I place this thing. So I want this thing to be parallel to my resonator and on one side. So I will fiddle a little bit around. I need this to be offset by the width times 2. Yeah. No, times 2, times 3 halves, right? So now they're touching each other. So this is not something I want, because now I want to control how much this line onto which I will have my microwave connector. I want to control how much this line is coupling to my resonator. Again, this is how did I copy the component of the second? I'll do that again a second time and I'll go slower. I should have thought about adding a software so you can see my mouse action when I'm working on the screen. I didn't think of doing that. Sorry. I'll try to be more careful about explaining exactly what I'm doing. So here an important part, this is more the physics of the device. So this new sliver of copper that I drew here, what I'll use it for is I'll connect SMA connector, a typical microwave connector that we'll be using in the lab, for example. I will connect it to this new line that will couple to this resonator, right? So now an important part is I need to control this coupling, right? This can't be touching. If it's got touching, it's a galvanic contact. So the signal will just go through independently of the frequency. So you need to have a gap. You need to have a capacitance between the two to be able to have like a something that will rely on the resonance of the central part. So what I'll do for that is I'll add a new variable in my position here. So I'll add C gap, for example, C gap. And for now, I will put to 200 micrometer. Now, wrong sign. So now you can see that this thing that I will use to connect my microwave is slightly offset from my resonator. I also want to have something a bit further out from the resonator so that I don't have a prime with my connector. So I will add 1 millimeter there, 2 millimeter actually. Okay, so this is the first strip onto which I will have my connector. So regarding the question I had from Mila, what I did to duplicate that, to copy that, you have to click on the box, not on the create box thing where you have the properties of your system, but on the box you select it. Once you have selected it, the shortcut is Control C. You can also probably have it here, yeah. So copy, and then you just paste. And now I didn't have to, redo my box and the thickness and all those things. In this case, I don't want to copy this one. I want to copy this guy. So the box 4 that I just did. Let me rename those guys. So you can, at any time, you can click on one of your box and you can rename them. You'll see it's fairly practical as your design becomes more complicated. So it's easier to navigate. So input strip 1. Careful that you cannot have a space, so you can use underscore dash whatever you want, but not a space in those names. And then what I do is I'll copy my strip. So you can, two things you can do. You can either copy the strip or you can duplicate it. So there's two ways to proceed. So one way will be I copy the strip, then I will have to modify the position, not the dimension, but the position of the strip to be able to have it the other way around. So the position where I want to have the strip, I use the draw tool to show you. I would like to have the strip around here, right? So this is where I want to have the strip. Again, that was just to show you the position. So I could either copy and then go in there and figure out what I need to change. So this is probably going to be positive now. So this is the other way around. Of course, this is wrong because there is one thickness too much. And for this, I probably need to go positive also. Oh, come on. And it's going to be too far down. So I need to subtract CL. Okay, so that's one way to do it, right? So you could either do it like this, or the other thing you could do, another thing you can do. So when you're drawing, you can select any of the component on your device, and you can go onto the draw here. You have those things. For people who don't have access to this, it might be on view, visibility. I can hide the strip here. So you go to view, visibility, hide or show selection, active view show. And if I want to hide it again, active view, hide selection, active view. So the reason I hid it is the other way you can do that, instead of copying and then going into the parameters again, one thing you can do is you can duplicate. So this is in edit. So sorry, right click, edit, duplicate, and then you can rotate around an axis. The good thing is that now this axis by definition will be around the center position by default. So then because my system is symmetrical compared to my center axis, if I do around axis and I ask for 180-degree rotation, then ta-da, I get my duplicated box that's down there. Right. So that would be another way to do it. And you can also verify that if now you change the parameters, everything will move accordingly, right? So both the top part and the bottom part will move accordingly. You can check that by clicking on your HFSS design here on the top left corner, sorry, into your project manager. So if you click on HFSS design, in the properties, you have all your parameters, right? So the reason why we coded all those things with parameters is not if now I say, oh, no, I want a 35-millimeter box. That's it. I have a 35-millimeter box, right? So if you code your project like this, it will be super handy to vary all the parameters and to explore a little bit the parameters for your device, right? So for example, my gap is 200 micron, and we can verify that if I change the gap, all of them move. I can go a bit more crazy just so that we see that a bit better. So you see that those two guys are moving when I change my gap value. For the value here, you can always write for micrometer or for millimeter, so you don't have to change the unit. It will change the unit automatically, right? Okay, so that's another way to proceed. Turns out that I forgot something when I did all of that. So what I'll do is I'll cancel all those actions. I'll destroy this strip. Okay. One thing I should have done before is I need to have a round part. So my connector will be a round connector, and here on the top part, it's still a rectangle. So I want to fix that, and I want to make sure that I have a round part on the top. So I'll use a cylinder. I want to go in there, place it roughly properly. So that's my cylinder. Again, as usual, we need to do the same thing. So height will be TCU. So that's the thickness of my my system. Now I'm starting to forget my variable, so I will get this here. This is CW for the width of my strips. So this will be CW divided by 2. That should be the proper. My height should be, my position should be at 0. And there, I need to figure this one out. So I'll just go onto this guy and check the formula I have, and I shouldn't have to modify it too much. Maybe with CL, let's see. Yeah, so I need to change this. I have one. Okay. So now I have also my cylinder. So I have this cylinder and this strip. So that composes my system. I have an issue with the thickness, I think. TCU, that's all right. Feels like oh no, they're the same height. Okay, good. So now what I can do is this should be one component. So what I'll do is so another aspect of designing. So here so far I used, independent elements. So a strip, a rectangle, a box, a cylinder, etc. So one thing you can do is you can use Boolean operation to actually subtract, add, or have intersection between your different components. So here I'll take my cylinder and my strap. And this is something I want to make a new, like a whole device. So you can go in here for me on the draw thingy, it's already appearing here, sorry. This is I unite them. So I click unite. I'm pretty sure you could find that all on the way there. Let me check. I never used this part here. I guess you'll have to figure out on your own software where this shows up. But the Boolean operation should be there. Oh no, maybe it's like this actually. Yeah, you can right click and then you can yeah, exactly. So you can select your two system, the two things you want to do a Boolean operation on, right click, go on edit, and then go on Boolean, and then go on unite. Okay, so that way you'll be able to find this even if you don't have access to this top part. So now I already did this. I can redo the trick I used before. So now this new overall strip, so I'll call it strip 1. This new strip, what I'll do is I'll take it and then I can edit, duplicate around axis Z, 180-degree rotation, and now that's it. I have two strips, right? So there is many tricks like this to simplify your life when you design something. It's always good to, if your system has a high degree of symmetry, it's always good to try to keep this degree of symmetry in the way you pick your referential. So then that way you can simplify a lot of the action you have to take to design your system, right? So now I have my two strips. I have my half-wave resonator. Now I need to build my connectors, right? Because now if you see my device, I need to attribute that. So my half-wave resonator is copper. Yeah. Someone speaking? Okay, I thought someone was speaking. I color my everything that's copper. I'll color it color copper. It's going to be easier for you to navigate your design if you do that afterwards. So this is all copper. Funnily enough, I need to manually oh yeah, sorry, it's here. So the one that's created by the duplication and the rotation is still in vacuum. So I need to say this is copper and color it copper. So now that's how my device looks. A complete back copper plane. On the top, I have two strips, this and this, onto which I will have my connectors and my resonator. Right? Feels like time is flying much faster than I anticipated. So the next step is to actually build the connector, right? So the connector, typically what would happen with this sort of device, you will have actually the connector going through your substrate. That way the pins are more resilient to stress when you handle your system rather than just soldering a pin on the top here. So I'll cheat a little bit. I need to check my final design that I had here because I do not remember the dimension of my connectors. So that's the design we want to make, right? So that's what we started doing on the front plane. And what we'll do now is we'll see how we build those connectors. And I'm doing this because for the better of me, I cannot remember the size of those connectors. And they are 4.5 millimeters. So they're 0.9 millimeter. So the first thing I'll do now is I want to have a pin that goes from those guys all the way through the substrate on the other side, because the other side is where I would have my microwave connectors, right? So same as usual, You can do that from the back if you want. Well, it doesn't change much actually. I'm going to do it from here. Oh. Okay. So that will be my connector. Obviously, it's very wrong in terms of dimensions. 2mm. I put it -2. Now it's on the good side. And for the position, I will use this again. So my strip, I will retrieve, oh no, rather the cylinder. So I'm going onto the cylinder that I had created to make this piece here. So I can retrieve my relative position for this thing instead of having to think again about how this goes. Now I need to check if I'm good. Yes, so you see now this new cylinder is properly placed and is sticking out of my FF4 substrates. It's a bit too short to my taste. I like my pin to go a bit further out. So it's going to be easier to connect. Now my pin is going 3mm out. Okay. So this will be.
Hi, Dr. Juan. Sorry to interrupt, but there's someone in the chat who is just wanting a reminder about what device we're designing.
Oh yeah, sorry. Wow, your sound was super loud. You startled me. So the design with the device we're designing is a filter, right? So the idea is that in pretty much everything we're doing, we're handling microwave signals, right? So sometimes you want to send a signal at a very specific frequency, and you might have noise at different other frequencies. So one thing that a device that might be interesting for you is having a filter that will allow you to only send this very specific frequency and filter out anything else that you might have on a line. There could be noise that you might not control from the environment or anything else. The way we do that is we actually use something that's useful for superconducting circuit in general. Is we use this rod here, the central metal rod is of a certain length. So you will have a resonance. You can think of it as a guitar string, right? So a guitar string, depending on the length of the guitar string, you'll have a frequency that's very specific, right? The fundamental mode is this kind of bending of this guitar string. And that would be the same thing here. So you'll have one mode, that the first mode that you have here for this strip of metal is the fundamental mode, and that's at 4-ish gigahertz for this design. And this is the micro frequency at which you'll have a maximum of electric field at each side. So this is kind of a wavy motion of the electric field like this. And the idea is that now we have two strips. So on this one, I started building the connector from the back. So my microwave will be connected on this strip. Okay. Thanks to this resonance, this resonator here, if I have a signal that's exactly at the resonance of this thing, it will start to excite the resonance on this central one. And because this one has a maximum field here and there, it means that this resonance will allow me to pass the microwave signal that's going onto there, onto this resonance, and onto the second strip, right? So the idea is the following. I have two connectors. I use a resonance in the middle. If my signal is resonant with this resonance, so if the length is related to the frequency I'm sending, then my signal will actually go through this resonance and then back out onto the other port, right? So this is a typical resonant filter in the microwave that will allow you to get a signal through at one very specific frequency. Of course, you have harmonics, so you have 4 gigahertz, 8 gigahertz, etc. So you have to be careful about that, but that will be one way to filter your signal. Is that a bit clear?
That's great, thank you. Someone else is wondering if we could potentially increase the font size just because it's a little hard to read.
Yeah, this is a good question. I'm gonna try my best. It's probably related to resolution of the screen. So let's see. This is kind of crappy for me now. Okay, is it better? Should be better, right? Yeah, on my screen at least it's better.
Yeah, that looks a little better. Thank you.
Yeah, sorry, I didn't think of that earlier. Let me try to reorganize a little bit so I don't lose too much for the navigator. Okay, so now this is the bit of the design that's a bit more cumbersome, because what we're trying to do is we're trying to model properly how my connection pin will look like, right? So we need to go through the substrate, we need to go through the ground plane, and we need to make sure that we don't have any intersection that would make the whole device not work. For example, if now I just to say, oh, this cylinder is my copper. I'll call it connector. That's my microwave connector. Well, let me call it code. No, sorry. Wrong one. Where is it? What did I do? Okay, no, I had lost it. I don't know how I did that. So copper, and I don't know. And I call that connector. So that's my connector. I'll color it like I did with all of them. And this is copper. So now you see the problem is that not only in this section in the middle here, I have both a dielectric, the FF4, and copper. So those two elements are within each other. So this is kind of a bit of a conflict for the program because it wouldn't know how to handle that. But the other issue is that this copper pin is obviously connected to the copper plate on the back, right? So this is not something that would work. There will be a short between the lead and the ground plane, right? So this is why building this connector is it's a bit lengthy. So I will show you some of it. I won't have the time to go through all the steps to build the two connectors properly. Yeah, unfortunately, I thought that in an hour that would be sufficient, but apparently not. So now I have my connector. So the next thing is I want to have a dielectric kind of casing for this connector because a microwave connector is composed of an outer shield, which is the ground plane, and an inner pin. And in between, you have an dielectric, which is isolating, and it's typically Teflon, right? So what I'll do is now I have my pin. So I use this pin. I'll duplicate it. This will be another material. This will be Teflon, which is the typical dielectric materials in microwave cables. And typical cable is called SMA. I see there's a question. This file, I can share this file if you want. Oh God, man, I'm trying to get to the question. I can share this file if you want, but this is just a very general introduction for the people who are interested in going into the stream with the superconducting qubits. I will go more into the details about like very specific things for superconducting circuits, and I will share with you all the files that I'm building. So you have a starting point for handling and familiarize yourself with HFSS. But I can also share this file too. Lost my train of thought. That's my connector. Oh yeah, sorry. And that's the SMA. So my SMA is a bit bigger. So it's 1.5 millimeter diameter. The color is the SMA color. No, sorry. I will take the same color as the FF4. It's a dielectric also. So now this is my dielectric. I don't need this dielectric to go into the substrate. So what I'll do is I'll remove the thickness of the substrate. No, wrong way. Ah, yes, I know. Okay. One thing, this is something I always forget, and I forgot again. If you have a variable that's defined in your project and a value that you use for an offset or something that you hard-coded, you have to be very careful to always specify the unit of this hard-coded value, because here it assumes that 3 is not in millimeter, but 3 is in meter. So it's adding my thickness of my box, which is in millimeter, 1.6 millimeter, to like 3 meters. So you need to add the unit minus 3 millimeter plus TB. Okay, so now it's good, but now the position is wrong. I want this guy to start at minus TB. Okay, so that's my pin. Okay, so at least that's part of my pin. So now I have the dielectric. I have the central pin. Now I need the outer connector. So for the outer connector, what I'll do is, and that will be what I will end on with, and I will show you the way you design a qubit so that you see a little bit of both designing a microwave component and designing a qubit for this morning. So this Teflon SMA chunk, what I'll do is I'll duplicate it because I want to make the outer connector. So what I do is I copy it and I paste it again. This is now not my SMA, but that's my outer connector. And it's not Teflon, it's going to be copper. now I have this outer connector that's supposedly copper, but the issue is it's also a solid chunk of metal. So what I'll do is I'll take this outer connector. For the radius, I will add, so millimeter, and I will add the thickness of the copper. So I want this thing to be slightly bigger than the Teflon chunk that I just made. So now it's slightly bigger. And because now it's bigger, what I can do is I can use the SMA Teflon chunk that I made and subtract it to this massive piece of copper, which is 1.5 millimeter plus the thickness of copper for the rest of my PCB. And the way we do that is you can select the outer connector. So always select first the thing you want to subtract from. So I want to subtract from the outer connector. I want to subtract the SMA, right? So now I can do that. And there is something interesting is that, so you go edit, duplicate, oh no, sorry, not duplicate, Boolean, subtract. But now when I subtract, if I don't do anything special, I will remove the SMA chunk from the copper and the SMA chunk will disappear. So here you need to clone the object, meaning that it will use the SMA to remove this volume from the outer connector object, but it will still keep the SMA. So now if I do this, what I have is my connector, outer connector now is this kind of thin layer of copper around my SMA Teflon chunk. Okay, so that's one way you will design a connector. The next thing that we need to do is you can realize here that on the bottom here, and I'm really bad at navigating with the mouse, on the bottom here, I still have the ground plane, right? So this is not open, it's completely closed. So the other thing I need to do is I need to take the SMA, sorry, the ground plane, which is, I didn't name the ground plane, oh, my mistake. That's the ground plane, let's name it. Ground. So what I'll do is I'll remove the SMA chuck from the ground. So again, ground is the part I want to remove something from, and then I select the SMA, and what I'll do, edit, Boolean, subtract, and again, I need to clone so that I don't lose my SMA plastic chunk. And for some reason it didn't work, and I really have no idea why. See, this is why I don't like to do things live on the computer. So normally what you should have done is removing from the ground plane, removing a disk here so that there will be no ground on this inner part of the cylinder. And I'm actually not sure why it's not working. It might be related to the way this is done. This is plus T. I think that there is no intersection between my SMA and my. There was no intersection between my SMA Teflon part and my ground plane, so that's probably the reason why I couldn't subtract it. So now I'll try again. So I select my ground plane, my SMA Teflon chunk, and then edit, Boolean, subtract, clone, and now it worked. So now I have something that is hollowed out on my ground plane. And you can see that here I went a bit too fast because I didn't have enough segments on my SMA chuck. So you see that this is the discretization here in the model is quite bad. And so I need to be careful about that. I'll go back on the cylinder that I used for the subtraction, and I change it for 40 segments. And this is the nice thing about Boolean operation is that if I change one of the component of my Boolean operation, it will actually propagate in my model, right? And here it's cloned, so it means that it will work for everything I did. So whether it's for the Boolean operation on the ground plane or the outer connector, it would actually do the same for both, right? So now we would have something that's almost done. We would need to do the second connector, but that you can always like, take the outer connector, SMA, and do edit, duplicate around axis, 180 degree. And that's it, you'll have the second one. So this is pretty handy. You don't have to work twice for the two connectors. You just need to make one and get it back and duplicate it with the rotation. I'll take a little bit of time before I run out of time. I want to have enough time for questions. The next thing that's very important is that in this model, I just started to build the physics, the physical aspect of the system, so the model of the system. I haven't specified at all how am I going to drive this system. So there's two important things to consider now. The first thing is I need to build a box so that all the radiation that might be generated by my microwave in my device, they don't reflect back onto my device, because that might be artificial coming from the model. So this is one of the things that's always hard in finite element type simulation. You always need to be careful of understanding your system so that radiation don't necessarily go out, or if they can't, if this is encased in a box where you have reflection, or if it's encased in a box where you don't have reflection, or it's a very large box, what you can do is you make a small box for your simulation to be easier, and you make sure that all the radiation that actually go through your box and that disappear from the code, right? So you don't have reflection and these sort of things. So what I do is I build a box. I'll probably copy this again. So that's going to be my air box or vacuum box. It's vacuum. I don't care about the color. I will make it invisible anyways. And I want that to be a bit bigger. So I will have this. That's good. That's good. And I want to have this 5mm. And here, one thing I need to be careful about is I need to be careful that the box start really at my connector. So I really want my connector to be at the end of my simulation region, because the way I excite it is with a waveguide port, and the waveguide port has to be at the limit of your simulation box, right? So I need to be careful with the position. So this is 5mm, and I need to go to minus TB minus, was it 2? I think it was 2. I need to double check that. No, it's not right. So I need to check my SMA. My SMA was 3mm plus TB minus TCU. Okay. So that's the height of my SMA chunk, and I need to move my box so that I'm at something similar. So this was 3 minus plus. Did it? Did it? Okay, so now I'm pretty sure this is at the limit. Yeah, exactly. This is at the limit. So now this is my box. So now this is where the tricky bits for HFSS are starting. This box is a perfect radiation absorber, right? So what you can do, there's different way of specifying that. The way I'll show you is you can select the box that you want to change the boundary condition of. And now you can go in the project manager and you right click on boundaries, assign, and this is radiation. Okay. Radiation 1, you can give them name, and you'll see that now if I go in boundaries, I see this radiation 1 box, and it shows this kind of weird design. Not sure about the reason for this choice, but it means that this is a radiation box, right? What I typically do in general after is I hide this, because I don't find it super practical to have it in my face all the time. So now I have the radiation box. The next step is how do I excite my system? So now I only have one port, but it's fine. I'll show it with this one port. So what I can do is I want to select this region here. This is where I will have my connector. This is where I would have my coax cable, and this is where my microwave signal is going to go in, right? So I want to use this and define that as my wave port, right? So one thing you can do is if you press F, I don't know how to find it on the top thingy here. So F is to select an object, a face of an object, so 2D object. So if I select F, what I can do is I can select this ring. Oh, I realized I forgot something. So now you can see that the thing I forgot is I selected this face and there is no ring in the middle. So the connector is not separate from the SMA check. And the reason why is because my connector here, the central pin, is not removed as a Boolean operation from my SMA plastic Teflon thingy. So now the problem I have is in this region, I have both the connector and the SMA Teflon chunk. So what I need to do is I need to take my SMA, take my connector, because I want to remove from the SMA the connector, and then edit, boolean, subtract, clone. And now I have a hole in my SMA chuck. So my chuck is just a Teflon between the inner connector and the outer connector, so the ground plane of my microwave cable. And now what I can do is I can again do this F to select the face and select this face of my SMA chuck. And this is where I will connect my wave port. So once I have this connected, I can go in boundaries, assign. Sorry, it's not here, it's on there directly. So again, I connect this. So you can right click on this face that I just selected, and then you will assign excitation. Oh yeah, I clicked on boundary, that's fine. You go to port model wave port, or the same thing, you can select here and go on excitation, assign port model wave port. Yeah, thanks for the reminder, Clarissa. So this is the wave port, and there is one thing that's super important for the wave port is to define how the electric potential is going to be drawn. So here what you do is you send the signal in the inner connector, so the connector itself, the pin in the center, and the outer part is the ground plane. So that's how your field will be oriented. So once you do this model wave port in the integration line, remember, that's really important, you need to go to new line and then define this as being the inner part being my connector. So that's where the voltage, the current will flow. And this is the outer connector. So you have this line that's defined like this. Then you can next, do not renormalize. You don't have to change those parameters. And that's your first port. Okay. So now you define your first port. There's something very wrong with this model. I didn't remember seeing that before. Why is it sticking out so much? Okay, I did something wrong at some point, and I really have no idea when this happened. Because that's the first time I see my SMA thingy sticking out so much. Oh, no, that's my wave port. Okay, no, that's the wave port that's sticking. We can check. If I delete my wave port, yeah, that's my wave port that's sticking. So that should not happen. I guess this is because my box is not flush with the connector. So here, this is one of the typical mistake. Maybe this was the thickness layer, the thickness correction I applied that was wrong. So let's try again. And then if it doesn't work, I'll show you the result on the file I did this morning that was working. So the face I select, citation, assign, port, model wave port, new line from the inner connector to the outer connector. Next. Done. Okay, perfect. It didn't ask me for the thickness of the wave port, which means that my wave port is on my computational border, which is the thing that you like to do. So now we would be almost done. The last step for you, once you get there, would be to go to HFSS and do a validation check, because there is for sure some conflict in my model. So if I do validation, see 3D model, there is some conflict. You can go on the message manager, and the SMA and box 1 are intersecting, and the box 1 and connector are intersecting. So now I have a problem, and this is that my connector here is intersecting with the box of the FF4 because I forgot to do a subtraction from the box of the connector. I'll do that right now. From the box to the connector, Boolean, subtract, done. Now if I do a validation check, I should have one fewer error. Now I have an error between my SMA and my box 1 intersection. So my SMA is intersecting with my box. So what I'll do is box SMA Boolean subtract clone. And I can check again. No more issues with the 3D model. The last thing I have to do is I need to define my analysis. So now you can go in the project manager, right click, add solution setup, automatic. And this is where you will ask the program to do a frequency sweep between the frequency you like to check, right? So I said my frequency should be at 4 gigahertz. So we'll do 4 to 10, for example. So now it's 4 to 10. There is something about, autosolver, high speed, high accuracy. You have to play with that, depends on your model. Now everything should be fine. And my validation check goes through. Once this is done, the thing you have to do is go in your analysis and right click and say analysis all. And this is a bit long, depending on your model, could run slow. Oh yeah, you need to save. Before you can even do that, you need to save your project. Otherwise, you won't be able to store the results. Now we will solve it. This might have a bug because I didn't duplicate the port to have 2 ports. But what I can do in the meantime is I can show you what I got with this guy, which I built the same way. The second port is doing this duplicate rotation around the z-axis. And then what I'll get is this thing. So result, you do the analysis. Then in the result, you create terminal solution, rectangular plots. And you ask to have S11, S12. S11 is if you send the signal into the 1 port, what signal is reflected into the 1 port? And then S21 is if you send signal into the 1 port, what is transmitted into the 2 port. So in this case, I select 11 and 21. New report. And I ran that this morning. Hopefully it doesn't just panic and stop working. It's calculating the other one in the background, so it's probably a bit too much for him at the moment. Oh yeah, okay, it plotted it, but so now I have the 2 simulation I did at the same time. So maybe let me remove one of them, so it's going to be easier to read. And that's what you'll get. So if you see for the transmission, I get 2 order of magnitude reduction here, and when I'm in resonance at 4.1 and then 8.42, then I have 2 resonance, and that's when my signal is actually going through my device. So it took me a lot longer than expected. I didn't make that many mistakes. It's just that, well, I took the time to explain as well as I could. I'll be happy to take some question. And of course, the second session that's more dedicated for circuit, I'll go more into the details of a very specific circuit, so transmission line and qubit. I'll be happy to take question now. That was so clear. I think everyone's starving and they're looking forward for the lunch break. What kind of boundary do we define? So the boundary I defined in this example is just the box that's around the device. So one way to think of it is in the absence of this kind of weird looking box here, what you'll have is the software will only calculate what's happening in the component that you actually have onto your model, right? So here, let me hide this thing. Can I? Was it? It's here. So So if I don't have this vacuum box here, what the software will try and do is it will try to model everything that exists into your modeler, right? So the FF4 substrate, the copper piece and whatnot, but nothing around it, right? It doesn't know anything around it, right? So you need to build a box that's a bit bigger around it. Otherwise, it can only calculate what's into your model. And the issue would be the radiation has nowhere to go, right? So for example, your microwave will go into your strip and then it will radiate. I mean, it would like to radiate, but if you don't have a box around it, the calculation software won't have any more dimension to explore, right? So you need to build a bigger box, which is this vacuum box, which is around your device, but you don't want this box to be a source of reflection. You don't want the microwave to hit this box and then be reflected and hit back the device, right? Because that will change dramatically the way your system behaves. So depending on your system, you might want to have a radiation box or just a box that's copper because your device is imprisoned in the big copper box. It really depends on your device, right? Do we need to consider manufacturing tolerances when doing Boolean subtraction? This is a very good question. Unfortunately, to my knowledge, there is no tolerance whatsoever in the model here. You'll have to balance that with the discretization. So here, one thing I didn't show, when you do simulation, the software will actually mesh your physical system, and then the mesh size will be done automatically in this case. So something related to tolerance, manufacturing tolerance, will also be somehow in your model. If your mesh is too coarse, the result might be completely wrong. You could be very, very wrong, actually. So you have to be careful on the mesh. And then the other question that's related more to your design itself. If you have some stringent manufacturing tolerance, let's say the fabrication you have access to is not very precise, you might want to use the parameters that we used here. So those parameters here in the property window, what I can also do is I can build a solution, an analysis where I scan some of those parameters. So one thing you could do if you're really worried about your manufacturing tolerance, you could take something where you think the tolerance might be a problem and you can slightly vary its width and do that programmatically with those properties, and then actually run the code for different width and then check how the performance of your system might change with manufacturing tolerance. So that would be a way to explore what's the balance, well, not the balance, but the interplay between manufacturing tolerance and your design and the performance of your system, right? So for microfabrication and nanofabrication, this is clearly an issue. You have to be careful that if something was not 55 nanometer, but it was 53 nanometer, it could change the performance quite a fair bit. How do we force a mesh size in a particular area? Also, we will get the final version of this file. Yeah, I can send you the final version of this file, no worries. It's not particularly interesting file for superconducting chip, but it's a good way to learn. So for the mesh here, you see there is a mesh. The one thing you can do, and I don't do that often, but I could, for example, take a connector. Once I have the connector, I could click on mesh, assign mesh selection on mesh, length based, and then I want to have a 7 micron mesh. Right? So if I understand correctly, the mesh system of HFSS, and it might be one of the more tricky aspects of HFSS, it means that on the connector now, I force the system to do a 7 micron length mesh at most. Right? It might do it smaller, but the biggest it will do is 7 micron. If you have a question, you can post them in the chat. I see it's like 2 past noon. So you can post them in the chat. I will do my best to answer them. And anyway, I'll see you again in an hour only, right?
Thank you very much. That was a wonderful talk. I would like to announce that we are now at our 1 hour lunch break. So this Zoom call will remain active for the hour. So feel free to just come back at 1 p.m. or a little bit before if you want to make sure that you're not going to miss anything. And feel free to populate the Discord, trying to form teams, networking. Myself and other members of the team will be active. So let us know if you have any questions. And we're looking forward to seeing you all again in 1 hour. Thank you very much, Dr. Juan.
Thank you.
Hello, everyone. Just a couple more minutes before we start. I want to give everyone some time to make their way back into the Zoom call after our
Okay.
Okay, we got about 10 more participants back, and I think they will slowly start trickling in. I hope everyone had a great lunch and everybody is working on getting their teams formed. I would like to welcome back Dr. Juan for the second part of the second workshop. So whenever you're ready, feel free to take it away.
Yeah, perfect. Thank you very much. Welcome back, everyone. So what I thought of doing for this part, so this will delve a bit more into the details of designing a superconducting device, so really qubits system and microwave system that we're using for transplant qubit device, right? So to do that, I really wanted to go back on the theory. I know that Charles covered most of it, if not all, but I really want to make sure that we speak the same language. Because designing this sort of device is not extremely complicated, but you have to be careful about the parameters that you're trying to reach. And if you don't have a general understanding of the underlying physics, you can actually make mistakes and end up with parameters that will actually end up with a device that's not functional, right? So I will just share a few slides going through a little bit about the dispersive regime and what's important to consider before I go into the HFSS simulation of this sort of device, right? So I'll start with this, which is something I really like. This idea that in theory theory and practice are the same. In practice, they are not. So this is really my starting point in general for this sort of discussion about the theory. And I also wanted to show this picture about if no one saw that before in the press. This is an IBM quantum computer, or rather quantum computer processing unit. So what you see on the back here, this whole thing here is the cryogenic fridge that allows you to maintain the chip that's here. So you have this huge infrastructure just to get this one chip at very low temperature and being able to operate the superconducting device at low temperature. And one of the difficulties, all the cabling that you see, this is actually really hard to put in place, and it's a complicated system. But the chip itself, this is the size of the chip, and that's an eagle. I think an eagle was a few 100 qubits, so the chip itself is very small. All the rest makes it much very complicated. I don't know how to get rid of that. I have the Zoom window box right onto my screen. It's bothering me. Okay, good. So the one thing I wanted to go back onto was really this idea of, this is a much longer presentation. I will skip a lot of the parts that I don't need to address now. Again, This is really to make sure that we all speak the same language. We do have a qubit because we go from a harmonic potential, we add a junction, so we have something that's harmonic, and then we can address this one transition here. The screen sharing thing is on top of my, okay, anyway. We can address this one transition very precisely. And that really helps you having something that behaves as a qubit. So that's really the starting point. The other important part is the fact that this is not, this is something that required a lot of work, right? So, sorry, just like my tools are superimposed with the sharing thingy from Zoom. It's a bit hard to navigate. It's an ongoing story. First qubit 2000. Now we're a bit further out on this graph, but the point is that you see that the lifetime of the qubit has really increased steadily. And the reason why I mentioned that is the lifetime you measure for your qubit is not only related to the qubit. The design of your chip really also has a big impact on that. And then that's one of the motivation of the dispersive readout, right? Because the starting point is, as Charles mentioned, if you just have this sort of system, what happens in this case is if the qubit is too strongly coupled to the resonator, so again, that's the resonator, that's very similar to what we designed earlier today before the lunch break. If the qubit is too strongly coupled to that, what you end up with is this Hamiltonian where you have the resonator, okay? And then you have the qubit. And then on top of that, you have this coupling J or G, depending on the field you're coming from. In general, is J for superconducting secret, and it's sigma plus A plus sigma A dagger. And if you're not familiar with this sort of thing, this just means that thanks to this interaction, is H bar G, which is related to the fact that the qubit now within close proximity with the resonator, you can have this exchange. So you can create an excitation in the qubit and absorb an excitation from the resonator and vice versa. But what I really want to come back on this, and I really want to insist on this, this is not something you want, because if you have this exchange, it means that as soon as you send photon in your resonator to know what's happening to your qubit, the issue is that if you only stay to this level, then those photons from the resonator will actually change the state of the qubit, right? So this is really where you have to be very careful. And that's why we talk about this famous dispersive readout, which is the case where delta, which is the detuning, let me check my notes, which is the detuning between, never know the sign, qubit minus resonator frequency, you want this to be much bigger than G. And this is super important. So if you take this challenge, you really will have to be careful. The first thing you'll have to be careful about is this thing, right? This approximation, because if you're not in this regime where the detuning, so how far the qubit and the resonator are in terms of frequency, is not much bigger than the coupling rate, then the issue will be that you can have this exchange. So the photons from the resonator can go to the qubit and vice versa. So you will really impact the state of the qubit. If now you can fulfill this condition, so the dispersive condition, then what happens is that your Hamiltonian becomes this thing. You'll have H bar omega resonator plus chi, which is this dispersive shift times eta A plus my qubit. Oh, it's a Z, sorry. Now, the big difference is the transformation we've done, and I will not do the calculation, it's a bit too lengthy. The transformation we've done is that now we have this frequency of the resonator that's not only omega r, the resonance frequency, but you have a term that depends directly on the state of the qubit. So this thing here, sigma z, if it's in the ground state, sigma z will give you -1. If it's in the excited state, sigma z will give you +1, right? So if now the qubit is in the ground state, the resonance frequency of the resonator will be a certain value. If it's in the excited state, it will be in another value. And the very important thing to keep in mind is there is no exchange of energy in this case, right? The photon cannot go from the resonator to the qubits, nor the excitation on the qubit cannot go into the resonator. That's what we call this regime dispersive, because it dispersively shifts the cavity frequency depending on the state of the qubit. So it's a state-dependent frequency shift for the resonator. And this is important because if now you ask yourself the question, I want to build a superconducting computer, I want to build a quantum computer, it doesn't have to be a superconducting computer. What you want to do is you want to use those qubits to do your calculation. And at some point you want to measure them, you want to act on them, but you want all those things, especially the measurement, you don't want the measurement to influence the state of the qubit. So if you have your computation, tons of qubits, and then at the end you read the state of the qubit, if just the fact of you reading the state of the qubit changes the state of the qubit, then the answer that you're having is not the answer of your computation, but it's something that's related to the fact that you really didn't do your measurement properly, right? So really, really important being in the dispersive regime, right? So what does it look like? It looks like this. This is how the dispersive, I lost my pen. This is how the dispersive regime looks like. This will be the cavity frequency. For in this case, the shift is different. It's a negative shift instead of positive shift. You see the excited state, the ground state here. Cavity shifts for cavity frequency for the excited state of the qubit, cavity frequency for the ground state of the qubit, right? And the reason why I wanted to mention this bit also is you have to be very careful about your cavity also, your resonator, right? Because what you see here in dashed line is the actual temporal trajectory of the number of photon or the photon state of the resonator over time. So as you put more photon, initially you don't have any photon in the resonator, so you don't have any information in the resonator. And then this photon number will change depending on the qubit state, so excited in one case, ground state in the other case. And this change will be more or less fast depending on the parameters of your resonator. So this is another aspect that you'll have to consider. If you want to be able to read out your resonator quickly, you need to have a very large line width for your resonator, right? A large line width of your resonator means that you can change the photon number in your resonator quickly, and then you can read out the frequency of the resonator and the qubit frequency, right? So this is also something to consider. And there is this other graphic that's a bit more interesting. And this is related to what I just commented. So depending on this ratio here, so I remind you, we had this dispersive shift. So the dispersive part of the Hamiltonian, which was h bar omega r. I don't know why my pen is so thick on the screen. Chi sigma z erg. So this chi here is this guy. So that's the dispersive shift. Oh, I didn't give you the expression. I should give you the expression of the chi. Chi, because you'll have to be able to calculate it, is g squared, the coupling of the qubit to the resonator, divided by the detuning. Okay, that's the value of the dispersive shift. So here what you see is if you compare the frequency, the dispersive shift to the cavity line width. So kappa is the cavity line width. Let me write it somewhere for you. That's basically this. That's the width of the cavity that also fixes the speed at which the cavity can change in terms of photon number. So when you compare this, you realize that if you have a cavity that's extremely fast, so a kappa that's very broad, the issue of a kappa, I hope you see that if you have a very big kappa, the issue is that instead of having something that's sharp like this, you have something that's so big that then it's really hard to make the difference between the two states, right? And you can take it to the extreme where kappa is super, super, super large. And then in this case, what you'd end up with, can I do that? No, I can't easily erase. I don't know why. I can't find the eraser. Is it the eraser? Yeah, that's the eraser. You can go to the extreme where now your kappa is so big that, come on, so big that you don't see anything, right? It's the same state, basically, whether you're excited. And that's this point here. And the other point is related to how fast the photon number can change. So you could say, oh, but now I want to have a very small kappa. If I have a very small kappa, then I can have something that's super sharp here, super easy to distinguish. The problem is that a super small kappa means that your cavity takes a very, very, very long time for the photon number to build up in the cavity. And that translates in having a very bad signal to noise ratio because you need to measure for a long time. So you acquire more noise and you go back to this region here where the signal is not that good. So another thing important for you to consider is there is this optimum, and that's typically at 2 chi over kappa, roughly around 1. I can give you, I think I have the exact value noted somewhere in my notes. Just give me a sec. But in general, like chi has to be of the order of kappa. You know, it's not a super strict value. If you operate in this range in general, like you'll have something that's quite good. I don't have it noted in my note. It's on the some of the reference that I give you at the end of the document you'll have for this problem. You'll be able to find this information. So kappa of the order of chi is the best regime. Okay, so that's also another important parameter, right? If you want to be able to use your resonator that's coupled to your qubit to efficiently, read the state of your qubit, you need to be in this dispersive regime. So delta, the detuning much bigger than the coupling rate of the qubit to the resonator, but also you need to make sure that your cavity line width is comparable to your dispersive shift. Otherwise, you're not going to have the most optimum readout. Okay. Last thing I wanted to mention, and it's still related to the same thing, is this idea about what's the impact of the resonator. So what I mentioned so far is the fact that if I'm in the dispersive readout regime, then what's happening in the resonator doesn't impact the state of the qubit. There is still a problem. If you imagine now, this is a frequency, and this is basically your cavity response, right? All right, adjust cavity. Now, your cavity response looks something like this, right? If this is something a bit broad, that's your cavity response, and that's kappa. Okay, now you have a qubit. The qubit is at different frequency from the resonator. That's omega r. That's a resonator frequency, and the qubit is somewhere else with a good, big enough detuning so that in the dispersive regime, you could either think of placing it at smaller frequencies or higher frequency. You'll have to ask yourself. You can also do some reading here and there, whether it's better to place the qubit at a lower frequency than the resonator, at a higher frequency than the resonator. Let's say I place my qubit at a lower frequency than the resonator. So that's basically delta here, right? So first of all, again, I repeat, you need to make sure that this delta is much bigger than the coupling range. But now you can also see that the qubit now is somehow in this response of the cavity, meaning that now the qubit, although it's not exactly in resonance with the resonator, it sees a little bit of the what's called the density of state of the resonator, meaning that there is some photons in the resonator that can exist at this frequency. So now this qubit can see a little bit of the resonator. And that's another thing that's super important, and that's called Purcell effect, meaning that if you're not careful enough, if the qubit is not far away enough from the resonator, then the qubit can actually emit the photon into the resonator. So even if you might still be in the dispersive regime, there is still a chance that the qubit will emit the photon to the resonator. And that's this notion of what we call Purcell limited qubit. And the thing is, if you were to measure the lifetime of this qubit in this case, the T1 that you'll measure, the lifetime of the qubit you'll measure, will be actually fixed or limited by the fact that the qubit sees a little bit the resonator and can emit into the resonator. So we'll lose the excitation faster because of its connection to the resonator, right? So that's another thing that you need to consider in your design, whether or not you Purcell limited. So I'll give you some reference where you can calculate the Purcell limits of your device. So you can, knowing all the parameters of the device, the couplings and the kappa of the resonator, you can calculate the T1 limited by the resonator of your qubit. And if you have a very, very good qubit, you need to be super careful about that because you might actually be limited by the Purcell limit induced by your resonator. So there is a trick, and this is something you might want to consider in your design. It's not a requirement, but I mentioned that in the, if you want to delve deeper, that's what's called a Purcell filter. So then for Purcell filter, what you do is that's your readout resonator, but on top of that, you add this additional resonator. And this additional resonator, what it does, it actually is exactly what I mentioned earlier. it's a resonance, so you'll have some frequency that can go through, other frequency that can't go through, and you use that to actually engineer the shape of your device response. And in this case, instead of having this broad cavity response, thanks to the Purcell filter here, you'll have a dip. And this dip here now, this is related to the Purcell filter. Oh, this is super badly written. I hope you understand what I mean. So this here is related to the presence of this, and you can see it in this data here from this article. You have the reference here. This dip here is related to the fact that we added this structure. So now we have a dip that is the resonance of this structure, and that we make sure that this frequency is exactly the same as the qubit. So now the qubit sees even less chance of being able to emit a photon in the resonator, because there's this anti-resonance, so the qubit cannot emit there. So that's a way to control the Purcell filter. And the way you can see that here in this graph is if you had no filter, that would be the lifetime of the qubit you could hope. So it's like, this is only 100 nanoseconds. So this is a pretty bad qubit actually. This is 100 nanosecond. But if you add the Purcell filter, you see that you already gain 1 order of magnitude by having the Purcell filter. So the Purcell filter in some cases can be very, very important to be able to get to the maximum qubit frequency. And just to mention this is something that is not required for this the exercise on the superconducting qubit, the challenge on the superconducting qubit, but you might also want to consider the box into which you actually get your sample. So you will spend a lot of time designing your qubit, your resonator, making sure that all that stuff works, but then you'll have to put that into a box and put that into a fridge. If now the box is not properly designed, you might have a frequency of the box that's close to the frequency of the qubit, and that's really bad. It means that the qubit will be, pushed to actually emit a photon into the box into which you house the device. So you have to be careful in the box that you're using for your system. That's pretty much what I wanted to mention in terms of theory, to make sure that we were talking the same language. Now we'll go back to HFSS and we'll see how we design superconducting device. So I'll take 2 examples. Hopefully I'll be a bit more efficient than this morning. So we'll take the transmission line, because impedance matching is super important. And then we'll take the qubit as an example. So how do we build a superconducting qubit in HFSS to calculate its frequency? That allows me to show you the difference between the 2 different type of ports and the 2 different type of simulations, so full model and eigenmode model. So I'll change computer. Stop sharing this screen if I can manage to do it. This, okay. And now I also see if you have a question. Oh, I just see your comment now. It's been 15 minutes and apparently you can't hear me well. I hope now on my side, the input is actually good. Let me know if the sound is not good for some of the viewers. So, different computer, different screen. Maybe this will work. We're back to HFSS like we were this morning, but now we'll focus on superconducting device. So again, it's also a repeat. So I figured that it would be nice to just repeat some of the things I said this morning. Getting a handle on the new software is always about repetition and practice. So insert HFSS design, otherwise we have absolutely nothing. Oh yes, and I will mention some details that it might have gotten through this morning. So new box, again, either from the thing up there or simply draw box. We'll draw our box. Oh, come on. And 2 things, again, you can just say that's my box. I'll try to be a bit more length. So you either use a text like this, and this is a parameter that's related to this specific design, or you can have a parameter that's more project wide. So if I were to put what is it? It's this symbol, the dollar symbol, the dollar sign symbol. Same thing, you define the length. So let's say that's 2 millimeter. The width, I'll do the same. Box width. let's say 1 millimeter. And the thickness, I don't know why I call that box. It's a sample. I'll stick with box. Thickness. I'll use a typical thickness for the usual substrate that we use for superconducting device, 0.5 millimeters, so 500 micron. That's my box. So now you see that if I click on HFSS design now in the properties, I do not see the variable I put, because now those variable, they're not only related to this project, but if I were to add another project, I could add a second project. Now those variable, they're not linked to only HFSS design 1, but they for the whole project. So they appear in project variables. Okay. So this is a different way to parameterize your system. Either you go for project variables or you go for more local variables in your program. Depends on how complicated your design might get. So that's something you'll have to see for yourself, how you prefer to work. So this is now my box. In this case, this will not be vacuum, and this will be silicon, right? So we use 2 substrates typically for designing superconducting device. In my lab, we're either using silicon or sometimes we use sapphire. Right, so sapphire is very, very low loss. It's a bit harder to work with. So one of the industry standard is silicon. So not any silicon. We typically use high resistivity silicon to make sure there is no remanent dopant that could actually be a problem for the microwave properties. So again, that's my box. For the superconductor, what we'll do in this case, we're not going to use finite thickness. So on the previous example this morning, we put a copper plane that was 35 micron thick. Now we'll put something that's a sheet, right? Not only speeds so the reason why we use a sheet and not a box is because it speeds up the calculation. And for a superconductor, we don't need a volume because we consider this is a perfect electric conductor. So the volume doesn't change anything for the calculation. So we'll make RPC. I think I made a mistake for the box. I forgot something. So for my box, it will be box length divided by 2. I forgot the minus sign. Comma, box width divided by 2, comma, minus sign again. Sorry. And box thick for the thickness. Okay, so now I have the proper position. I'll copy this so I don't have to do the same thing for my rectangle. And that's box length. And that's box width. Okay, so now I have my rectangle that's on the bottom here, of course, because this has to be 0. I have my rectangle. That's now, again, it's a sheet. It's not a 3D structure. It's just a 2D structure. So that's my sheet, and that will be my ground plane, right? So you can look into that a bit more in details in the literature. What we did for the device this morning was a ground plane on the bottom and our device or strip line on the top. Here we'll do what's called a CPW. So it's a coplanar waveguide, meaning that everything is happening on one face of our substrate. So we have the silicon substrate, and on top we have a ground plane, and we'll open a slit into the ground plane and have a line running through it. And that's basically our transmission line. So for now, this sheet will be our a ground plane, and on top of that, now we want to add the transmission line. So you'll see the design of a transmission line is relatively simple. That will be one of the example file that I will provide you with for the challenge related to the superconducting qubit device. So the way we do the sheets, the way we do the transmission line is fairly comparable. So I'll take again my rectangle. I'll copy it and paste it so I don't have to redraw it. But now this time it's not going to be the same width. So I want to have a ground plane, and then in the middle I want to have a sliver of metal, so a sheet that is of a given width. So what I'll call it like CPW width for the size, no, the length is the same. Sorry, this is the box length. It will run the whole box length. And for the width, it will be CPW, so coupler waveguide width. And this, let's say we put, I don't know, 50 micron. I know this is not a good value, but I also want you then afterwards to play with those parameters and to figure out by yourself, like what are the good parameters for this sort of system. And I had forgotten to put it at the proper Y position. So now I have this rectangle and this rectangle, they're on the same spot. So what I'll do is I'll take this, which will be my CPW conductor. I'll call it like this. CPW conductor. I'll copy this one again. And I will call that my CPW gap, because I will use that with a Boolean operation to actually remove some of my ground plane. So this will be my ground. So I have a ground that continues, and that's an issue. So I use the gap to remove some of the ground. And in this case, the width will be CPW width plus 2 times CPW gap. And I need to, so CPW gap, let's say 10 micron. And I also need to fix that minus CPW gap. Normally that should work. So that's my gap. And now again, Boolean operation. I take my ground plane from which I want to subtract something. The something I want to subtract is the gap. Right click, edit, Boolean, subtract. And I subtract the CPW gap from the ground plane. And now I have my ground plane that's open in the middle, and I have my conductor. So that's now my transmission line. So the transmission line, I hope you can see or have an intuition of how it works. This whole plane is set to the ground, so it's at 0 potential, and this will be connected to your microwave cable one way or another via circuit board, via wire bonding. I'll skip those details. It's not very relevant for the design at the moment, but it will be connected to the microwave inner conductor, so where the signal is going. So if you think about what's going to happen physically, on this line, you'll have a current that's flowing at a microwave frequency, so back and forth at the microwave frequency. And then this will generate an electric field. And if you think about how this electric field will be, you'll have field lines going from the central connector all the way to the ground plane and closing into the ground plane. So that's why we call it a CPW, sorry, for coupler waveguide. It's a waveguide of which the electric field somehow mostly stays in a very small region of space. So it's kind of a squished 3D box. It's close to 2D. So the electric field will actually extend from the central conductor to the ground plane, both in the vacuum and also in the dielectric in the silicon under there. So nothing super fancy for now. One thing you can check is that you can check your project parameters and you say, okay, look, now I want to have a much bigger gap, let's say 50 micron. And now I have a much bigger gap. So if you did everything with the parameters, it's very nice because that will allow you to play around with your parameters to be able to match your transmission line, because that will be the next step. Now we're gonna use this very simple model to check for impedance matching. So the idea is the following: all your microwave equipment in a fridge is matched at 50 ohm, meaning that the impedance of all the cables, all the instruments are 50 ohm. And what happens if you take a component that's not 50 ohm is you'll have a very large reflection, right? So you will have a lot of the signal that's reflected. Here we're dealing with fairly small signals, like a few photons, a few microwave photons. You really don't want to lose any of those photons. So you have to be careful of matching things close to 50 ohms, otherwise you'll have reflection. And that's going to be an issue in terms of how you can recover signal from getting information from your qubit. So the next step will be to explore that, and that will be the first step for this challenge for you, is that you'll have to play with those parameters, CPW conductor size and the gap size, to be able to match to 50 ohm. So to be able to address this question, what remains to be done is defining properly those sheet material. So as I said, it's a perfect conductor in our case, but also those famous wave port, right? So how we excite the system and what kind of transmission we read or impedance we read to make sure that we match 50 ohm. And I'll show you two ways with a model wave port and the lumped wave port, which will give you access to slightly different information. So for those two, you see that those sheets are unassigned. They have to be assigned to a material. So where's it? Material? Where's my material? Oh yeah, right. So I select the CPW conductor and the ground plane, and there I right click and I assign boundaries. In this case, it's not a material per se, because we want that to behave as a superconductor, and one of the properties of superconductor is that it has no resistance. So we'll go to assign boundary and then perfect E. So perfect E for perfect electric conductor, right? So it's perfect E1. So now you see in the project manager that you have perfect E showing up there, right? And the conductor and the ground plane now are both perfect E. Okay. So I have my silicon, I have my two perfect E sheets, the CVW conductor and the ground plane. So now what's left to do is our radiation box that I didn't draw yet. Hopla, I'm trying to navigate. So I need to create a radiation box. So I will copy this box again. Now it's not silicon, it's vacuum. And I'll make it bigger. So width and length will be the same, but thickness, I'll make it 2 millimeter. So I need to center it with 1 millimeter. Should work. Yes, that works. So that's my box. It's vacuum. And if you remember, now I select the box. I go to boundary. I say assign, and that's my radiation box. All right. Radiation 1. So now I have my perfect E for my superconducting sheets and my radiation box. The first thing I'll do again is visibility, height selection, active view height. No, sorry, I didn't have what I wanted selected. Right, so I hit my box. So now I need to define my port. So the way I will show that to you, I will do two things. The first thing I will do is I want to do that with the rectangle. That's the wrong direction. Oh. So now you see I didn't show that. So when you draw a 2D shape, by default it will be drawn onto a given plane. So you see that here, whatever I do, every time I try to draw a 2D shape, it's always in the XY plane. Because here on this panel, you can see that there's the grid here, but there's also a plane that's defined that forces a 2D shape to be drawn on this given plane. So here I want to draw it into the ZY plane. So now I selected here the YZ plane in this case. I select again my 2D, and now I can make this rectangle here. Okay, and this rectangle is what I will use for the model. So the lumped wave port, sorry. So that will be my lumped wave port. It's important. This guy has to be at the limit of the computation. And you see that I thought it would be on the face, but it's clearly not. It's someplace ridiculous. So now I need to place it properly. The size of it is not super important. It has to intersect with both my ground plane and my inner conductor, right? If it only touches one, it's going to be an issue. So this guy, oh, sorry, I need to recenter it. So it should be position on Y should be 0. And then position on X should be box length with a minus sign. And I lost it. Where is it? Yes, right. And now in Z, it's the wrong thing. Oh yeah, and I'll do this with 5. So that's going to be minus 0 to 5. Yeah, be careful with the units. Sometimes you can have issues. If you don't specify the unit, you might think you plug that into in meters. So that will be my first port. I copy this. And then that's my second port. Now I have 2 ports. What? Oh yeah, okay, I did a bad job. So 0, 3, so this should be -1, 0, 15. They were not centered on the Y direction because they're referenced to the bottom corner for those sheets. So now those will be the 2 things I use on my side port. So then I can select them. So 2 ways: you can either assign from there, or you can select the rectangle, go into excitation, assign incident port, sorry, model lamp port. That's port 1. And you saw that here I have the port impedance, right? Yeah, I need to specify. The angle is bad. Okay, I need to change my view because I need to specify in which direction I will excite. So again, I select this rectangle, excitation, right click, assign port model lumped port. So again, I specified the impedance here. So what I'm saying is that my device, this transmission line, will be connected to something that's impedance matched at 50 ohm. And then I need to draw a line that will show how am I exciting this. So this is, if you can see from behind, this is my central conductor, and that's my ground plane. So this is how I excite. I do not renormalize. That's my first port. And then I go the other side, and I'm still super bad. I didn't get better during the lunch break and navigating this thing. Up. And I'll do the same thing for the second rectangle and assigned. So either again through excitation, or you can also find it here. I assign excitation port, model lamp port, 50 ohm integration line, and then I go from my inner conductor to my ground plane. Okay, so now I have my 2 ports. I don't like this angle, but whatever. I have my 2 ports and the thingy from, go on. Yeah, that's it. I have the zoom information that was hiding a lot of the buttons. The 2 ports, port 1, port 2, radiation box, perfect conductor for the rest of my system. So now I have everything I need to be able to simulate that system. What exactly is the integration line? Yeah, I don't know. I don't fully understand why they call it the integration line, but it's basically where you apply the current to where the current will flow in terms of ground plane. So I can do it again. Let me remove port 2. I did port 2 and port 1 on this. No, okay. So I remove port 2. So now I have an assigned rectangle. I assign excitation port model and port 50 ohm. And this integration line, basically, this bit here is my inner conductor. So I could connect anywhere in the inner conductor. It's a superconducting device. So my point is that whether I assume that the current is sent here or here, it's the same thing, right? It's a perfect electric conductor. So what I say with this integration line is I will apply the potential difference of the current between this point, and this point. So you have to think of it. Another way to see it maybe is the polarization of your electric field. That will be another way to understand what this integration line means. Okay. So I have my 2 ports and my perfect E, my radiation shield for my device. So now I have everything I need to be able to sorry, I'm not very good at following the question. Thank you, Aya, for answering Tian's question. So now I have everything, so I should be able to get an analysis solution. But here, if you see, this is the panel that we saw earlier today. And then it allows me to scan from any frequency to any frequency. So here, what I want to know is, okay, sorry, I should start with it. So I have a transmission line. Okay, I defined a central conductor width 50 micron and a gap, And actually, depending on the width of this central conductor and the gap, that will fix the impedance of my transmission line. So now the question I want to ask to my model here is this configuration 50 ohm matched, right? So if it's not 50 ohm matched, then I will have a lot of reflection. I have set those ports to be 50 ohm. So now what I want to measure is this S21. So how much signal I will get on port 2 if I send something on port 1. If I'm not matched 50 ohm, a lot of the signal will be reflected, so the transmission will be quite poor, right? So that's the kind of analysis that we want to do. So in analysis here in the project manager, you go to add solution, auto, and then you can check, I will do like, I don't know, 4 to 10 gigahertz. That's the solution that's set. And now I can start the analysis. And oh yes, again, I need to save something. Project 10, I don't know why it's always project 9, whatever. Project 10. Oh, and I forgot to do something. I forgot to do a HFSS check. So let's see if I made a mistake, it will stop running and crash. Ah, been very lucky. I didn't make any mistake. So while it's running, I can answer some question. Otherwise, I will explain what we'll do next. So while you think of question, I can start with that. Was quite much quicker than expected. So the analysis ran. So now in results, you can right click again. So the logic behind HFSS is you set your tree model, you set your boundaries, your ports, and then you set your solution. So the analysis, the kind of analysis you want to do, the frequency over which you want to do this analysis. You can check the number of points, for example, that you want to have in your plots. And once everything is analyzed and calculated, you have to go in results, right click, and then create your result report, right? So you can extract tons of information. We have this whole list of parameters that you can get out. What we'll be interested in is what's called the S parameters. This is otherwise called as the scattering matrix. And it tells you if you send something on port 1 and then you measure on port 1, this will give you this ST11. And then if you send something on port 1 and you measure on port 2. So I want to check the two, so the reflection and the transmission. Click new report, and then I can close. And you can see that my S21 is actually very, very good. And this is because everything is forced to 50 ohm because of my lamp port. So the other thing I can check is the impedance matching, and it's not there. So I'm actually confused about this result. So actually, this is working very well. Worked very well. Made a mistake somewhere because the dimension I picked, I expressly picked wrong dimension here to make sure that I could show you what's a system that's not properly matched. So I will open the CPW exercise that I designed earlier because I'm not sure where I made the mistake. Okay, just hang on with me a second. I'll open the working example. Because the problem I should have here with this system is that my, or maybe I was super lucky and it's perfectly matched 50 ohm, but I doubt that. So my inner conductor is 50 micron, my gap is 50 micron. Typically for this sort of device, you need to have a ratio of like 1/2 roughly. Like, so if that was 50 micron, the gap should be closer to 25 micron, not 50. So that's the example I worked out earlier. So same thing, very similar. My excitation port are a bit bigger, but that doesn't really matter. But you find exactly the same thing. Oh no, yeah, and exactly that was my issue. So this is the this is a wave port. So as we did this morning, and if you do with a wave port, then you have access to the result on here. Let me check. It's the same. Okay, so now I'm very confused. that's a LAN port. Okay. How is it possible? It worked yesterday. Okay, still, I'll proceed. So the idea here is the thing you want to check is those scattering parameters. So the reason why I was looking at, showing you this example, otherwise it's not working exactly as I expected, is those scattering parameter. What I tell you is that if I go back to my model for this example, I have 2 ports. So I had done some many change on this file. So this is port 5 on the back and port 6 on the front. So when you sweep the frequency of excitation in those ports, so this is a model port, if I remember well, wave model port, then what you want to check is how much signal is reflected and how much signal is transmitted, right? So that one of the key things for your transmission line is to make sure that everything you send in your transmission line is not reflected at the port, but properly transmitted and caught by the outside port. So in this case, this is exactly what you like to have, right? So this is 0 dB, meaning that all the intensity you sent into port 5 ended up into port 6, right? So you didn't lose anything. So you have to keep in mind 2 things. There is one thing that's important for that, and that's what I mentioned since the beginning now, is this impedance mismatch. So if it's not 50 ohm matched, then you'll have reflection, but also your substrate is important. Now I use silicon, which is fairly low loss for microwave, but if we were to use a plastic, for example, FF4 is not the best for high frequency microwave, you would have some losses, meaning that this S56 in this case, this transmission through your device might not be at 0 dB, but might be slightly lower because the microwave, part of the microwave is absorbed into the substrate. So it's reflected at the port, but it's because it's absorbed at the substrate. So this sort of design, or at least this sort of test on HFSS can provide you some information about the overall quality of your design and choice of material, right? So for the last thing, and then my plan was to get as much time as possible for question and to explain to you like the overall challenge. I want to show you how you design a qubit because the calculation is slightly different, right? So the way we do the calculation is using the eigenmode solver, meaning that it will actually solve to know the only existing frequency in your design, right? So this should be relatively quick. New design again, new project, new HFSS design. So that's my system, and I'll do a box. I'll be quick this time, so I'll do a -2. What? -2. No, sorry. And this is -1, comma, -1, comma, -05, like we always did. So that will be my substrate. It's not vacuum. It will be silicon, like the previous one. And for the qubits, you have different way of designing it. So that's again my substrate. So for the qubit, I will again place my my top, which is excitation. Where is it? Sorry, not excitation, boundary. It's my perfect E. So that's my ground plane. So now I have my ground plane here. And I'm gonna draw my qubit. So the way you do the qubits is really up to you. So in the example I will take, I will use what people call the XMON. So a qubit is made of 2 main components. Superconducting qubit is made of a capacitance, right? So Charles mentioned that this morning. There is 2 important aspects to the qubit. EC, so the charging energy that's related to the capacitance of the circuit, and the Josephson energy, which is related to the Josephson junction that you use for your nonlinear inductor for your qubit. So those are the 2 key parameters. You'll have to be careful about how you design your qubit because you want this qubit to operate in what's called the transpond regime that Charles mentioned this morning, meaning that EC over EG has to have a certain ratio to be in the transparent regime, right? So you'll have to keep that in mind. Again, this is all synthesized in the PDF. I'll show you like in 5 minutes, so we can discuss the actual challenge a bit more detail. So that's the ground plane. I need to wait for the thingy from Zoom that appear in the middle. Okay, I'll do it here. And well, the example I take is with Xmon. So the capacitance is made out of a cross, right? I can give you more detail. If you have question of why a cross, I would be really happy to answer them. But for now, I will just move with that. So I'll call that like qubits length. And that will be, let's say, 500 micron. And then I will call that qubit width. And that will be, let's say, what did I use before? 50 micron. So that's part of the cross. I need to center it. It's length minus qubit width and 0. Damn it, it's not centered. Why? Ah, yes. So one rectangle, I copy it, paste, and then no, I'm not going to copy it. I'm going to duplicate. Duplicate with a rotation around Z 90 degree. So now I have my cross, right? So that's my cross. So this will be the capacitance of my qubit, okay? What I'll do now is I'll unite them. Oh, this is bothering me. You can't see it, but on the top of my screen, there's a panel, so I can, oh, now it disappeared. Okay, good. So I'll unite them. So now that's my one cross. And what I'll do is I will do something comparable, but to open the ground plane. So I copied again my rectangle, but this time it's gonna be qubit length plus gap. And my gap will be, let's say 50 micron. And the size here in Y, that's gonna be plus 2 times the gap. No, that's also 2 times the gap actually. And that's minus gap, and minus gap. So, okay, that's very big. I'll need to change the value of the gap. It's extremely large. Same thing, edit, duplicate around an axis. So I rotate it. And now I have those two guys that I will unite. And now I have the two things. That's the capacitance pad. And that's the thing I will use as a Boolean to remove from my ground plane. So that's my ground plane. That's the thing I want to remove from it. I subtract. I don't clone. I just want to remove it. And now I do have my full qubit, right? So that's the capacitance and the ground plane. So ground plane capacitance. So this guy also has to be boundary perfect E. So those two are perfect E. And I'm missing one thing. I'm missing the junction, right? So HFSS is not capable of just taking into account a full Josephson junction. So what we do is we actually draw a sheet here, and that sheet will attribute to that sheet a specific inductance. So it's a linear inductance. It's an inductance fixed to a certain value. So you can't you can't really design or create a qubit in HFSS. So that will be something a bit different. It's just a LC circuit, but that here will allow you to know the frequency of your 0 to 1, so G to E transition in your qubit. So this should be qubit width. This should be gap. And then for the position, that's going to be qubit length divided by 2. Missed it. No, it's going to be not this. It's going to be qubit width. Okay, and now for this, it is going to be minus qubit length. Oh, damn it. Qubit length divided by 2. Let's see, and I also need to subtract gap. Yes. So now I have the cross, that's the capacitance of my qubits, the ground plane, and here in the middle is this connection between the qubit cross and the ground plane that's realized by the Josephson junction. So I could give you some more detail about how we build this thing in for real in the lab, but for now, for the purpose of the simulation, the idea is that we'll use that and we'll attribute it a lumped element RLC value. So you can select this, right click, and I will have to, yeah, it's an assigned boundary lumped RLC, right? So it's a RLC lumped element. So in this case, it's just an inductance. You'll have to check for typical values of the inductance for qubits, transplant qubit. I will use 50 nanohenries. And same thing, you need to define the feed line, right? So I will define a feed line like this. I actually don't remember if it has to be from the ground plane to the floated part. We'll check, we'll see if it runs. So we have the lumped RLC, perfect conductor for both the cross of the transmon and the ground plane. The one thing we're missing is the box for the calculation, right? Missed it, I don't know what I did. So this box will be vacuum and we'll have it much bigger. So it's gonna be a, let's say 2 millimeter box and offset by 1 millimeter. So now we have our box around it. Same thing as usual. We don't want to have any reflection. Again, maybe I'm repeating myself, but if you wanted to simulate the fact that your qubit will be in an actual physical box made out of maybe copper, maybe aluminum, maybe niobium, you can also do that. You can also use a box that's made of a material that will be also part of your simulation volume, but it will make your simulation volume bigger, so the calculation will take longer and longer. Still can be it is an interesting exercise, I think. So that's my box. So now I go assign boundary variation. Okay. Again, same thing. I'm gonna hide this guy. No, why can't I hide it? Oh yeah, I misselected it. Visibility, hide selection. Visible. Okay. That's my qubit. So now what I can do is analysis, and it took me a little bit of time this morning to realize the mistake I had made because I was stuck in there. I don't want to do a scan, so this will be a full finite element simulation. This is not what I want to do. What I want to do here is I want to simulate the eigenmode. So I want to know what's the resonant frequency of my device and all the modes of this device. And this is not realized by the default analysis setup in HFSS. So in this case, you need to not directly go to analysis, but before you need to go to HFSS and then solution type. And in solution type, you see that the HFSS is the one that's ticked. That's this finite element approach. You need to select the eigenmode. So eigenmode will only check for capacitance and inductance of the circuit, define the resonant frequency thanks to that. So it's basically, 1 over square root LC, and that will give you just this frequency. So it's much, much, much faster. And that's all we need actually for the qubit analysis. So maximum frequency, you can leave 75 gigahertz. This is a lot. You can also specify the number of passes. So what he'll do is he'll do a simulation, and then he'll change the mesh and see when the eigenmode converge to a stable value, right? So you can put like 10 or 15 or something like this. Now the analysis is done. Validation check, everything's green. So now we can analyze all, and that should be, oh yes, again. I'll have to clean up afterwards because I might have a lot of program in my folder now. Is it running? Yeah, it's running. So yeah, so this is typically fast for the eigenmode resolution. And then I'll take 5 minutes to describe what we are expecting for the challenge related to the qubit coupled to a superconducting resonator dispersively, and I'll take your questions. So again, analysis is done. There is no problem. Why red one was deleted? I did delete it myself. Normal completion of simulation on server. Eigenmode, sorry, create eigenmode parameters, rectangular plot, mode 1. And that's the mode I got. So it's very, very wrong. I took some completely random value for the dimension of the cross for the transpond qubit. Now I designed a qubit at 79 gigahertz, which is extremely not useful because electronic components at 79 gigahertz are not only super expensive, but also rather complicated to correctly connect. They require a lot of instruments. So there, my idea here for you would be that you can actually, either look at some existing paper with a typical dimension for the transpond qubits and the Xman, or you can play around with the parameters to you get familiar with how the capacitance will change depending on the gap size and the size of the cross, and how you can move this mode to be closer to the frequency range that's typically used in superconducting device, which is between 4 and 8 gigahertz. So that's pretty much what I wanted to show with HFSS for superconducting device, both this idea of being able to calculate with the model port or the lumped port for transmission line, for example, on one end, and on the other end, the eigenmode resolution to calculate what's happening with the transpond. So I hope you understand why in this case we do the eigenmode. The issue is that we don't really have a port to connect to, right? So the transpond is somewhere on your chip. It will have a resonant frequency, but it's not like I can connect a cable to the transpond. There is no transmission line. There's nothing connected to the transpond directly. So there is no way I can connect to it. So I cannot do this full HFSS solving to actually see the resonant frequency of the transpond. So I need to do an eigenmode to actually retrieve the resonant frequency of the device that's in my design, right? So that's one of the subtlety of this sort of bit more intricate design containing transmission line, resonator, and qubit in the process. So with that, I will stop with the HFSS. I will share yet my other screen so I can go through with you what we had in mind for the challenge related to the superconducting qubit. Share desktop 1. So this is the PDF I will send you. You will have access to, sorry. And I will also send you some, already pre-made HFSS files. My point is, I'd rather you spend time changing parameter, understanding how the device change in terms of, like couplings and these sort of things, rather than you spending time in designing something in HFSS and fiddling and struggling with the design tool itself. So that's the picture of a device. There is a mechanical system on top of it, but that's what a superconducting 2D chip looks like. This is not one device from my lab, but ours are very similar to that. So the thing you're designing basically is the chip inside, and then you have those launch pad, and those launch pad are wire bonded to the circuit board, and then connected to your micro-F cable and outside of your micro-F box, right? Basically, right? But what you're designing is this inner part. So the objective is for you, and the goal rather, is for you to provide a complete 1 qubit dispersive readout design on a single device, not like qubit here and resonator there, etc., with all the key parameters clearly determined, right? And the way I propose for you to do that and discover and understand better each and every component is to do this thing that we did together. So I'll send you the example file also in parallel, to take this transmission line model and see how the gap between the transmission line and the conductor width impact the Z1, so the Z2, the transmission line impedance, and how much reflection you have. So you'll have to get acquainted with that, get familiarized with that, so you can have a transmission line that has not too much reflection. It doesn't have to be zero reflection. You will never be able to get a Z2 exactly of 50 ohm. That's going to be 50 point something, but let's say if you're within like a few percent of 50 ohm, it's perfectly fine, right? Then the next step is to go a bit like a step beyond, like transmission line with those launchpad, you see that now the ports are not at the edge of the computation, but really where the wire bond will actually be connecting to the launchpad. So that will be the transmission line, wire bonded on one end, and the other hand when the device gets fixed in the lab. And this thing here is the resonator. So very similar to what we did this morning. The line now is folded onto itself, so it doesn't take too much time on the chip. But basically, the resonator is this half-wave resonator. I'm trying to check also on the other screen if I have question. I will provide this file. There is some parameters that are hard-coded, others that you can change. So you can change the gap between the resonator and the transmission line, so that will allow you to see how this changed the coupling strength of the resonator to the transmission line. The other thing that you have to get familiar with is what HFSS will do is you'll solve HFSS. So you'll see this S to 1, as I showed with the example this morning, where you have a dip or a peak at that was for a filter in this case, but that would look very much the same in this case. And the thing you'll have to get familiar with is this tool that's called resonator tool, because you'll have to fit this response, this numerical response, to extract the line width of the resonator. What percentage of error is acceptable for Z2? It's a good question. Like you can get very, very close to 50 ohm in the simulation, but in the fabrication, you'll always have errors. So it's not very useful to push it to super high precision in terms of how close you get to Z2 to 50 ohm. So I would say like a few percent is perfectly acceptable. Anything below 5% is perfectly acceptable. So 5% will be related to a power reflection of a few percent, like 1 or 2%. So, this is something we can definitely work with in the lab for sure. So yeah, so you have to get used to this resonator tool. So yeah, you can extract the data from HFSS, then fit it with resonator tool. So then you can actually measure precisely what's the line width of resonator, right? Then the next step is the transplant qubit. So I'll provide you with a file with the transplant qubit. You can see also here the lumped element representing the inductance of the device. That way you can actually calculate the frequency of the qubit. So my point is that the progression is the following. Here you'll know the coupling of the resonator to the transmission line. So the line width of the resonator will be fixed by this part of the design. Here you'll know the frequency of the qubit. And this is yes.
Sorry,
yes.
we just have a question. Gigi is asking what percentage of error is acceptable for Z2?
Oh yeah, I thought I answered that. So the impedance has to be matched to within a few percent of 50 ohm. Yeah, so let's say below 5% would be perfectly acceptable. Okay. So so this is eigen mode. So the frequency of the qubit. So now there is one thing that's missing, and we didn't have the time to go into details, but you'll have that in the file. Is that you see here? That's the resonator. And now what you want to have is you want to be able to kind of write directly on my PDF. You want to have the qubit. No, apparently I can't. Why? So you want to add the qubit here. So the qubit will be placed at the other side of the resonator, right? So then the next question for you will be, how do you couple your qubit to the resonator? So that here again is the cross of your transplant qubit. And here, this kind of claw-looking structure is the end of the resonator, right? So you'll have the end of the resonator that's around the qubit. So now you'll have a new capacitance. That's the capacitance between the resonator and the qubit. And this is how you calculate the qubit to resonator coupling. And for this, you'll have to extract the capacitance. I should do that. You'll have to extract the capacitance between the qubit and this claw-looking structure that will be part of your resonator, right? I provided some reference at the end of the document, so you will see what to do with this capacitance to be able to calculate the coupling rate, right? So that's the progression I had in mind for you for building your whole device. So the point is, I will provide all of those independent models, but the exercise for you will be to be able to, finalize a full design with on one chip having all those components. It's much easier if you do the calculation and if you refine your calculation for each subcomponent on those smaller devices, your calculation and your simulation will run much faster than if you were to start with a full device from the get-go. That will be a lot longer in this case. I also provided a list of the deliverables somehow that you should be able to provide. So, and it's broken down in subparts. So for the transmission line, I'm expecting that you'll figure out a value for the conductor width and gap width, so that in the 4 to 8 region, you have a good impedance matching. So as the questions before from Gigi, something like few percent away from 50 ohm. Transmission to resonator coupling, you'll have to extract the coupling rate and the Q factor for the resonator. So in coupling Q and general Q, you can look in those notion if you're interested, but the main point is really this. And the parameters that you had to use to achieve this. So the length of the coupler, the distance between the conductor of the transmission line and the resonator, and the presence of a ground plane between the transmission line and the resonator. The coupler itself, you can play around with it. There is many different ways of realizing the coupler itself. There is no good or bad answer. You can just figure out the way that works best for you. For the transmit qubit, of course, the qubit frequency is what we're interested in. But the important part is that you'll have to provide the cross dimension, the dimension of the cross for the qubit, sorry, and the gap, as well as the inductance that use in the lumped element inductance. But the thing that you will really have to verify is that the qubit that you design operates in the transmit regime, right? So the fact that EG over EC is in a certain range of value. Otherwise, you might not have a transmit qubit. You might have something that's closer to a charge qubit, which are a lot more difficult to work with. And finally, the last bit is the qubit resonator coupling. So you'll have to calculate the capacitance between the qubit and the resonator. So this claw-like structure to be able to, from this simulation, you should be able to extract the coupling rate G between the qubit and the resonator. So you'll also have to provide the geometry, right, that you use, the dimension and the gap. So that's for what we're expecting in terms of you being able to solve the challenge. But there is, if you're interested in this, there is many other questions that you can wonder about with your model, right? So for example, you could play with a substrate. What happens if you go from silicon to sapphire, right? What changes, right? This is an interesting question. You can also think about, is it best to have everything on one chip? I can tell you that there is some companies that are building superconducting chip that are not everything on one chip. Some parts are on one chip, other parts on the other chip. You can think about this. Is there something to be gained from having, for example, the resonator on one chip and then the qubit on another chip? Can you gain something out of this, right? You can also think about, while staying 50 ohm match, because the 50 ohm matching, it's a ratio between the gap and the conductor. Once the ratio is fixed, it will be 50 ohm match, but then it could be 10 and 6, it could be 20 and 12, it could be any values, right? You can also play around with your model, seeing if now you keep the same ratio. So if you stay 50 ohm matched, is there something changing when you get something much bigger or much smaller, right? And you can also think about, like, what is better? Is it better to get very, very small? Is it better to get very big? That's something you can think about. You can also think about the physical aspect of the device that you're designing. What happens if the readout qubit coupling is too weak, right? So you can think, if the qubit readout resonator coupling is too weak, does it have an impact on the measurement time, right? Will your measurement be slower or faster? You can think about those sort of question about, your device might still be working, but maybe you need 5 microseconds to read the state of your qubit. The issue is that if your qubit lives for like 20 microseconds, it takes you so long to read its state that its state might have changed because it might have decayed into its ground state, right? So those are important questions. This thing that I mentioned in the short presentation before is this notion of Purcell filter. So this is also, like, if you have time and if you're curious about that, it's a nice extension of the project, right? If you have your qubit, you read out resonator, what does it take to add a Purcell filter? How would you add the Purcell filter, right? So to make sure that your qubit is not Purcell limited. And if you're even braver and you want to go even further, how do you design a chip with 2 qubits, right? That's a simple enough question. And now if you have 2 qubits, can you connect the 2 qubits, right? What is required in your design to be able to do a 2 qubit gate? How can you have coupling between the 2 qubits so you can realize not only 1 qubit gates, but also 2 qubit gates? And finally, another thing is, what would it take to have a flux tunable qubit? So if you want to control the frequency of your qubit with an external magnetic flux, what do you have to do to be able to get that, and what's the impact on the qubit lifetime? So all those are all the questions I thought about that you can, tinker with and use your design to actually look into the result from the simulation. And with that, I also put some two references that are typically the two paper I go back to when I have doubts about equations or formulas or the approximation behind the dispersive Hamiltonian and all the technical details. They're very different. This is very theoretical. This is a bit more engineering approach. And that's all I had planned to cover. And I have a good chunk of time for question. And I will send you this document, of course. And I don't see how I stop my screen sharing. It's perfect. It's here. Any question? If we have time, are you able to briefly explain why the cross shape is required? The cross shape is not required. You need pads to have capacitance, and that's pretty much it. I shouldn't have disconnected my iPad. Maybe I'll reconnect it quickly, so then I can do some drawings also in parallel. So one of the first, the first transmon was not with the X shape. So the first transmon was typically like so up. So don't mind the thing on the side. Just gonna use that as a blank paper. Okay, that's a smaller. This is really bothersome. The zoom thingy is on top of my tools. Anyway, so I showed the cross, okay, and they're very poorly drawn. And then you have the ground plane. I won't draw the whole ground plane, but the important part is you have a connection to the ground plane. That's this junction, right? So the way you can think of this is it's an antenna, right? It's a dipolar antenna, meaning that when you have an excitation in your qubit, what it means is that you'll have maximum field here. So plus minus plus minus, it's oscillating at the microwave frequency, and here, because you have a connection to the ground via the junction, this is where you have maximum current and no electrical field. So that's basically not a full half wave antenna. It's like a quarter wave antenna. The first qubits were looking more like the following. They were looking more like a big pad like this, another big pad like this, and then that's the ground plane. That's the ground plane. That's the superconductor here. And now in the middle, you have a famous junction. The X, the cross on the wire, is the symbol for a resistor junction. Here, what you'll end up with is that this pad will have positive and negative here. That's a half wave resonator. That's a quarter wave resonator on the top with the X. So the half wave resonator will have a positive and negative path. Both are good. Like they both transmon qubits. I initially worked with those guys here. Now in my lab, we're building those guys. There is an argument for those guys because you have only a pad here on the top. It's not like you have a second pad here. You don't have nearly as much electric field in the substrate, and this is where we have most of the microwave losses. So some people argued in the past that the X-mon was a bit better if you wanted to have higher quality transmon. It's very, very dependent on your fabrication. So there is a lot of subtlety there, but as soon as you have one pad connected to the ground via a junction, or two pads connected with each other, floating and connected with each other with a junction, you will be able to build a transmon qubit. A transmon qubit is basically a half or a quarter wave resonator that's very, very strongly nonlinear thanks to the junction. So as you think of question, I can give you a bit of a broad overview of the task at play. Designing a full 1-qubit chip might sound like something simple that a lot of people have already done. There's a lot of interplay between all of the parameters, so you have to be careful on how you choose your resonator frequency, your qubit frequency, because you need to make sure that you're in the dispersive regime, that you're still in a transmon regime. So all those things are interlinked, and that's why it makes it a bit like you have to do things carefully. So that's why I provided this kind of plan for you to progress through the device fabrication with the qubit on one hand, the transmission line, the resonator, so you can build things slowly towards your full device. I had some blobs about the qubit readout, it looks like. Yeah, those are connected chips, basically, like on the circuit board and within the box. Well, I think I was extremely clear. That's impressive. Or maybe like you're all digesting and it was super hard to follow. It's either way.
Thank you very much. I think we have time for a couple more questions if there are any. If you're holding back on because you're worried about time, please feel free to write them in the chat. I think we're just waiting on some technical difficulties of our next presenters, so feel free to ask some more if you have it.
And don't hesitate. This doesn't have to be on the HFSS design. It could be more general question about qubit and superconducting device and circuits. Well, I can mention another thing that you can look into if you're interested. So, and I never showed the picture, the full picture to you, but oh God, I can't reach the. Come on, what is this? Okay. So the full device will look like launchpad, transmission line, launchpad. So the reason why we have a launchpad is the transmission line is quite narrow. So it's very hard to solder a very small wire on such a very small conductor. You can see that here, for example, in this device where this is the transmission line here. That's so small that you can't even see it. And then you have this wider part here that allows you to have enough space for the soldering of your wire bonds. And the idea is that, as I mentioned, the 50 ohm matching is kept for as long as the ratio between the central conductor and the gap is the same. So you can see that here the structure looks like this, right? It's tapered, so meaning that the gap increases as the conductor increases, right? So it looks like this. So that's what a device looks like. So the way you can account for the launchpad if you want in your design. It's not particularly important, but it's something that you might want to consider. So transmission line. Then you have your resonator that looks like this. That's that bit here, that section here. Will come on. I don't want to do that. That's the structure here. That bit is what we call the coupler. That's what will define how much your transmission line is coupled to your resonator. And then the other thing you'll have to add is this claw like structure. What the heck? I didn't know I could do that. This claw-like structure that I will exaggerate, otherwise I will have difficulty designing my qubit. And then the transmon qubit here, cross. A very ugly cross at that. And the junction, and that's my ground plane here. So that's how the device will look like, right? So that's the typical overall device. And again, the exact shape of the resonator, it's up to you. You can make the wiggles different. You can make the coupler different. There's really no constraint there as long as the parameters are good. But the overall device will look something like this. And I will go back. Why are the protrusion on the screws towards the transmission line on that chip? Oh yeah, I'll go back to the chip after. I'll go back to why the transmon is a cross. The nice thing of the cross is that now I can also add a new line here. That's what's called a charge line or control line. That's a line onto which I can send a microwave tone. And this microwave will allow me to drive the qubit directly. So this line is very, very weakly coupled to the qubit. And I can drive very hard to drive the qubit and to actually make flip on the qubit. So those pi/2 pi pulses, so those 1 qubit gates. So this is something you can check. You can add that to your design if you wish. How you add a microwave line that's an open at the end so that you can control the qubit, right? That's one of the reasons why the XMON is interesting, because instead of putting it here, I could put my control line here. And then what I could do is I could here have another resonator. So you see, you can be very creative. You can end up with a super advanced chip. I can have another resonator, and then over there, another qubit, for example. So that way I would have 1 qubit, it's without resonator, it's control line, so I can apply pi pulses, pi/2 pulses, a resonator that couples this qubit to this other qubit, and of course, this guy could have its own micro resonator, transmission line somewhere, etc., etc., etc. So that's how you will build up. So once you know how to do this, you can go ahead and build like some fairly complicated chips with many qubits, some coupled with each other, and basically an IBM chip looks a little bit like this. It's a lot more complicated. They have a lot more qubit connected, but it's a bunch of qubit and resonator. So the question, why are there protrusions on the screw towards the transmission line? Okay, there's 2 questions. I missed one. I will go back to the other one too. About protrusion, maybe you ask about those things, I guess.
Yeah, those things.
Yeah, so if you ask about those things, it's just that the chip itself, you see it here. This is just silicon, high resistivity silicon. It's just put down onto a flat surface of copper. But when you wire bond, you need this to be very, very stable. So you have those kind of washers with a finger, and the finger presses on the chip itself so that the chip wouldn't move. It's purely mechanical, right? Just for fun. The other question was that qubit directly connected to the transmission line with a resonator? Yes. So those qubits are directly connected to a transmission line. It's a device of a good friend of mine. It's direct readout of a qubit. In this case, the qubit will very efficiently de-excite into the transmission line. So it's not good for quantum information because the state of the qubit will leak into the transmission line very quickly. But you can look into some other physics like a collective effect, open quantum system questions. Qubits are very flexible. They're not only good for quantum information, you can do other things. And in my lab, I like to do that too, because that's what I drew here. You can directly measure the qubit frequency, and you can also measure its anharmonicity and its temperature. So I like to add this sort of thing to my device too, even if I don't do open quantum system physics. Because that can give me a lot of information about the quality of my qubits and the temperature of my qubits.
Thank you so much.
Thank you very much.
That was an amazing presentation, and we all appreciated the depth and the answer to all of our questions. I would like to now extend a welcome to Michael Silver, who is an exceptional student from the University of Toronto, who will be presenting our next lecture. If you don't mind, Michael, giving a little bit of an introduction before you start presenting, that'd be great. Thank you.
Let me just set up my slide here. Can I share screen? Yes, I can. Okay, are you guys able to see my screen? Yep. Cool. Awesome. Okay. So what's up, everybody? My name is Michael. I'm a student from UofT. I'm part of the Middleware Systems research group there, and we do some pretty interesting stuff. So the focus of my research group is essentially building networkable quantum computers. And so in collaboration with IonQ, we actually start to build these systems. So as you'll see later in the presentation, trapped ion computers are very, very good at being able to work together. Um, and so we're more easily able to connect them together and then make a larger system using them. So that's kind of the focus of what my research group does, and we do work with IonQ on this type of stuff. So yeah, so today I'll just be giving you guys a very brief theoretical overview of what we do in trapped ion computing, how it actually works, how we trap ions, and how we do quantum computations using that. So let's get started. Before we touch on trapping ions and all this fancy electromagnetics and things like that, I just want to talk about what we actually need to do in order to build a quantum computer and like what we need it to be able to do in order to run our quantum computations. So I'm sure, as you guys have heard many times during the course of the day and probably tomorrow as well, is that we have our regular qubits, right? Which are just classical bits. Sorry, I should say. They're inside your computers and your telephones and basically every like computational electronic you'll use. And those generally use some sort of electricity running through to correspond to zeros or ones. So those are our classical bits. This is how we represent information in regular computers. Now, in quantum computers, of course, as I'm sure you've heard, we use qubits. And essentially what qubits are is that they have a very special property of being able to utilize quantum mechanics and different quantum mechanical principles to essentially represent more information than just zeros and ones, right? So kind of the most important one that I outlined here is a superposition in which a qubit state, instead of just being in a zero or just being in a one, can actually be in a probabilistic combination of both. And so what a quantum computer needs to be able to do is to alter those probabilities. So of course, you can have a 50% chance of zero, 50% chance of one, but the magic of quantum computation in general is that we can actually alter those computations, and that's what we're doing inside our quantum computer. So physically, in trapped ion quantum computers, of course, the name kind of explains it, we use individual atoms as qubits. So we trap these atoms, and I'll show you how we do so in a little bit, and then we shoot lasers at it, essentially, which again, I'll talk about more later. And that's our computations. That's physically what we're doing to perform our quantum, circuit or whatever you may be giving the computer. So a couple different properties we need to have just any quantum computer is that we need to be able to initialize our qubits to a known state. So generally, in a quantum algorithm, you'll start with a zero state. So we need to be able to reliably prepare our qubits so that they all start at that. The next one is obviously to perform our operations. So we need to be able to change the amplitudes and phases of our qubits. Again, that goes back to altering that superposition of qubits and different things like that. We need to be able to couple our qubits. So coupling is essentially being able to create a state of entanglement in between qubits, which means that they can actually interact with each other. And then the last thing is obviously we need to measure our qubits so we actually get an outcome of whatever algorithm we're running. So remember that, this isn't specific to trapped ion quantum computers. Every quantum computer needs to be able to do these very basic things so that we can, actually use it quantumly. Now, some key metrics that we look for in a good quantum computer are one, long coherence time. So they need to be able to remain stable so that we can actually, do our computation and they don't just die immediately. Another thing is we need to have low error rates. So generally, because we're dealing with super small particles and different things like that, they're very prone to noise. And we want to limit that noise so we actually get what we want out of our computation. And then the last thing is we want scalability. So of course, it's really nice if you can trap two ions. Well, what's the point? It's just a 2-qubit system. That doesn't really help you that much. So we want our hardware to be able to be scalable so we can grow it to millions of qubits where we can have like proper use cases as we do in regular computers. Now, I'll talk a little bit about trapping ions in general and why we care about it. So an ion, as most of you may already know if you've taken any high school chemistry, is essentially an atom or a molecule with a net electrical charge, which is usually caused by an unequal number of protons and electrons. So that actually allows us to utilize the electric charge of the ion and we can control it, so it's easier to capture. A key principle of this is obviously electromagnetism, and that's just the study of interactions between charged particles and objects. So if you've ever seen a magnet, if you've ever seen a wire, those are using the principles of electromagnetism. So shout out to all my electrical engineers out there. Trapped ion quantum computing is mainly built around electromagnetism, so you should understand this really, really well. And the good thing about it is that the study of electromagnetics is actually very, very old. So it's hundreds of years old. It was formally established in the 1860s, but of course, there's been many, many experiments even prior to that. And so because it's such an old area of study, we have so much technology that it actually allows us to scale and work on trapped ion quantum computers better, because we have so many things we could use to apply to this. And of course, when you're thinking about quantum, you're thinking about really small particles. And of course, ions work great as qubits, just because, you know, we can trap them easier. They use magnetism, which, you know, like I said, we have a lot of existing technology for already, so we don't have to, you know, completely make up new stuff just to kind of use this technology. Now, just a brief history of you know, humanity trapping ions is that it was kind of formalized in the 1950s and 60s, where Wolfgang Paul, a very famous scientist, you've probably heard of him before, and you'll hear about what he did a little bit later in the presentation, but he invented the kind of conceptual idea of the Paul trap, which is the most basic ion trap, using oscillating electrical fields, and we'll talk about that a bit later. And around the same time, David Welland experimentally demonstrated laser cooling of atoms, which again is very, very important, and we'll talk about that later. And he actually won the 2012 Nobel Prize for that research. In the 1980s, we experimentally shown that we can cool ions to near absolute zero, again, using that laser cooling, which is essentially just, you know, firing a series of lasers and different things at an ion to reduce its temperature down to near absolute zero, which is, of course, colder than outer space, very, very cold, and that allows us to control it better. 1990s are our first kind of quantum logic experiments using these trapped ions. So, of course, like I said, we use lasers for these, and we'll talk about that more later as well. In the 2000s, we demonstrated experimentally our first multi-qubit operations. So that's when, you know, one ion and another ion have some sort of correlation, and we can shoot lasers and different things at them. And it essentially allows us to perform multi-qubit operations as opposed to just firing a laser at one, and it just happens on that one ion. 2010s, you know, a lot of different companies started building up their trapped ion systems. So, of course, IonQ, our gold sponsor, we love them very much. They were one of the first and one of the largest right now to actually build these type of systems. And then in 2020s and beyond, like I said, we want to scale these processors so that they become utility scale, and we can do a lot of different cool things with them. So now I'm going to talk about, you know, how we actually trap these ions, right? So obviously, trapping an atom, just thinking about it from a subjective standpoint, it's a very difficult thing, right? Like, do you think a caveman could trap an ion? Definitely not. But fortunately, we know a lot about electromagnetism now, so we can use those laws to our benefit. So essentially, when you're thinking about a charged particle, right, the best way to trap it, you know, naively thinking about it, would essentially, you know, have it in the middle and then have a ring of electricity around it, right? Or an electrical field or a magnetic field or whatever, right? And so that's kind of what this diagram explains, is that, you know, you have your ion that's at the bottom of an electric potential well. So that means that it needs a lot of energy to move up that well. And if we just don't give it that energy, then it remains trapped there. Now, the issue is that in reality, building that type of well is very, very difficult, right? In static electronics, or electrostatics, as we call it, this is actually impossible. So that essentially means that our electric field and our magnetic field isn't moving. It's staying stationary. And as you can see on the right, if we try to experimentally make something like this, we can actually only trap it in one dimension. So you can see here that we have this sort of saddle shape, where, of course, in one dimension, we have this well shape. And of course, you know, it's very hard for an atom to move up to the left or to the right. But in the other direction, it's actually the top of another well, which means it's very, very hard to control, and it'll go down very easily because it needs very little energy to do so. So, you know, a lot of people in the 1950s were actually thinking about this problem, right? Because it's very difficult, and obviously you can't trap an ion just in one direction because it'll just escape into another one. So what Wolfgang Paul, the scientist that I mentioned earlier, discovered is that what we can do is we can take our experimentally realized well, something that looks like this, and just rotate it very, very, very fast so that even if the ion starts to go down in one direction, the rotation will change such that you know, the well will rotate, and then it'll be in a direction where the ion can't go down that way, right? So we call that dynamic trapping, or RF. RF essentially just stands for radio frequency, so it's a type of electronics and magnetic waves. And essentially we just, yeah, you know, we rotate that well very, very fast, and it creates an effective potential so that our trap essentially looks like this, right? And we call that principle, and you know, traps that are made from that principle, a Paul trap. And so we'll be focusing on Paul traps today because they're the most used in industry, and IonQ uses them. A bunch of other cool trapped ion companies use them as well, and you know, they're the most experimentally realized traps that we have currently. So common trap techniques, obviously we have our 3D Paul trap, and this is actually like an experimental setup of that, and you can see our little ions in the middle here. And essentially what that looks like is you have 4 RF electrode rods. So there's essentially just metal rods that have a fluctuating magnetic field in them, and DC end caps confined in the Z-axis. So these are like these little black caps here. And essentially what this is doing is that these rods have like a charge going through them, and that charge creates an electric field, right? And so, like I said before, you know, we need to create this type of well, right? And so essentially opposite rods will have the same charge. So can you guys see my mouse? Let's see if I can turn on a laser pointer here. Laser pointer. Okay, here we go. So when you have like opposite rods like this one and this one, for example, they'll have the same charge. And so that'll confine it in the one direction like we have here. And then, you know, obviously the other rods will be an opposite charge, and they'll create like this sort of structure. Now, the issue is that, of course, if we have this sort of structure, then the ion will just fall off here or fall off here, right? Because it's at the top of an energy potential, and we don't want that. So again, how we create this sort of structure is just by oscillating the fields, right? So, you know, these pairs of rods will just be oscillating. They'll change. So this rod and this rod will start positive, and then they'll move to negative as these rods move from negative to positive. And then obviously the DC end caps, they're just, they're not changing. They're just consistent charge. And essentially what that's doing is just making sure that they don't like shoot out the other end, because sometimes in electromagnetics, you might have like a perpendicular force, and obviously that's not good. We don't want to make a rail gun or anything. We just want to trap them together. So that's what these are doing. They're just holding them in a line like this. And you can see here that, of course, I wrote ions lined up in a single 1D chain. Experimentally here, it doesn't look like that exactly, but in general, you'll just have a 1x1 line of electrons, or ions, I should say. And then you can, that's basically your entire quantum computer, right? So each of those ions that you'll have in a line in the middle right here will be your qubits. So each one, you know, we can kind of shine a laser through, and we can shoot each one to do our different computations and different things like that. And this will essentially be your entire quantum computer, right? Now, one thing I do have to say is that because you know, ions are very tricky, they're very small particles, and their charge will be affecting the other ions in a line, we actually have to supercool this type of system. So what does that mean? If you've ever seen a picture of a quantum computer, you've likely seen what people call the golden chandelier. And essentially, it's like a big golden structure that kind of looks like a chandelier hanging from the ceiling. And that's essentially just large cryogenics, which cool whatever's inside to very, very, very low temperatures. And we need a similar thing for this type of structure, just because, you know, ions at high temperature mean high energy, and then things get messy from there. And we can also use that laser cooling technique, like I said previously. And yeah, so a lot of experimental labs and everything like that, if you're talking to a researcher at a university, they'll likely be using this type of trap. for quantum computing specifically, just because, you know, it's not super extremely difficult to make. The principles of it are electromagnetic. They're not even quantum. So, you know, it's a well-studied field, like I said. It's not impossible to do, right? And yeah, it's very, you know, kind of the basic trap that you guys will also be dealing with in the hackathon. So we'll be going over our simulation model a little bit later, and it'll look something like this. So just keep that in mind, that the 3D Paul trap is kind of the trap we'll be looking at for this hackathon. Now, another very common trap is the surface electrode trap. And essentially, it takes the same principles as the 3D Paul trap, but it makes it flat onto a chip. So I'll show you guys what that actually looks like a little bit later. This is just a nice diagram that we have. But yeah, essentially, the scientists in the 2010s actually took the principle of the 3D Paul trap and said, okay, but how can we scale this? How can we make it a little bit better? And so what they're doing now is that instead of having, you know, 4 bars and these end caps and different things like that, they flatten it onto a chip. And so these green particles are just like your atoms, and they'll actually be lined up on a radio frequency micro strip. And that's, of course, I'm sure you learned about transmission lines in the previous lecture. It's kind of similar to that, in that, you know, you just have a strip here, and you have your control electronics around it. Those are DC, means that the waves and fields and currents and voltages aren't changing. They're just same. But the RF actually allows for a magnetic field to be generated. And you can see here are like your little lines of the field. And these kind of curling in ones will occur where the ions will get trapped just above it, and they won't kind of go back and forth or shoot out or anything, which is very nice. And then a nice thing about using a chip is that they're very small and they're very scalable, so you can just make a bunch of them and connect them. Very nice for scalability reasons. And yeah, so your confinement essentially comes from your changing RF, you know, generated magnetic field and things like that. And the surface electrode trap is actually what's most used in industry. So 99% of the time, if you're talking to a trapped ion company that like has commercial trapped ion quantum computers, they'll be using something that looks like this. And I'll show you guys what you know, physically it looks like a little bit later. But yeah. And then we have the pending trap, which again is a very popular trap, but there's a bit of a caveat with that. And that is that, you know, it gets out of the trick of having to use RF technology by this kind of ring. So it's essentially like a metallic ring. And instead of just having, you know, an electrode bar like this, it's an electrode ring, and then you have your upper and lower caps. And the whole thing is static, which is very nice. But the problem is that in this type of structure, if you have a line, or like a line this way or whatever, of ions, their charges will affect each other and it'll mess up the whole system. So the pending trap isn't really used as much for quantum computing. It's more used for trapping individual ions so we can study them. So in a lot of particle physics labs and different things like that, instead of using a 3D Paul trap where you're capturing a line of ions, you know, you just capture one in the middle, and then you can do different spectroscopy and antimatter experiments. Very cool stuff. I believe in the Department of Energy in the US, they use a lot of different pending trap geometries to actually do dark matter and antimatter experiments, which are, of course, very cool and kind of out of my jurisdiction. I do quantum computing mostly. But again, very cool nonetheless. The only problem with this, it's hard to use as a computer because, like I said, you can really only capture one ion at a time. So which would mean that you need to use a bunch of these. And then scaling that and making them interact with each other is just a huge pain, not worth it when we have too much better options for it. So yeah, just this, you know, pending trap is cool if you care about trapped ions, but not so much about trapped ion quantum computing. So, you know, how we actually use these as qubits, right? We talked about, you know, physically trapping them, which is very cool because you don't even need to know quantum. All you need to know is, you know, electromagnetism. Very cool. You learned it in your undergrad. Shout out to, again, my electrical engineers out there. But, you know, we actually need to be able to take the physical quantities of our trapped ions and make them quantum. We need to encode, you know, we need to find a way to encode them as quantum information. So how we actually do this is by taking the inherent energies of our ion, and then we just do it that way. So generally in an ion, for any given instance, ions in your body or ions in the atmosphere or whatever, they'll always have an energy state. And so what we do, and the reason we have to supercool these systems, is because when we're dealing with trapped ions as qubits, we'll generally deal with two energy states of an ion, which is why we need a supercooled. So the first one will be your kind of zero state, and that'll be an ion at its like ground state. It doesn't have energy. It's like, if you're thinking about it like a very excited child, they're not vibrating so much. They're just kind of chilling on the couch or whatever. And our one state will be when it's excited, right? So again, if you're thinking about it like a child, he's running around, right? So then, if we accept that those are our states, what we can do then is just manipulate those states using lasers, right? So a laser can either supercool, like I said, or excite an ion, right? So all we need to do to change our amplitudes and to put things into superposition and stuff is just fire some lasers in a certain way at your ion, so that it excites it or it calms it down. And that's what we talk about when we talk about quantum amplitudes. Quantum amplitudes is essentially the probability of an ion to be in like either I call it an internal atomic energy level, but yeah, it's essentially just like either in the 0 or the 1 state. And it's very, very cool because you can get like I said, that superposition of both, and then using a laser, it's very, very easy to alter it, right? So all you have to say is like, okay, excite this a little bit more so that most of the time it's in the 1 state and a little bit of the time it's in the 0 state. And then in terms of quantum phase, if we plot the actual atomic energy state as it's oscillating between the 0 and the 1 state, the quantum phase, which if you've ever done any quantum information, is essentially just the relative timing between the energy states. So yeah, it's essentially like the difference in the x-axis of this and like this, for example. So yeah, very simple if you just plot it out. And again, like imagine firing a supercooling laser would reduce these amplitudes to like closer to the 0 state, and firing an excitable laser will just make it more over here to the 1 state, right? And in terms of quantum operations, how we actually do this is, like I said, we're just applying laser pulses. So to have a universal gate set in quantum computing, which is essentially a very limited amount of gates that you can do every other operation with, all you have to really do is 4 to 5 different operations. So you need to be able to rotate its quantum state, if you plot it geometrically, about an x, a y, or a z axis. And so using laser pulses, this is actually very easy because how we do it is essentially just dependent on the actual laser beam itself. So the duration of how long the laser is hitting for corresponds to the rotation angle, so how much we're rotating about whatever axis. The phase of the laser will dictate its axis of where you're rotating your qubit state on. And then frequency is essentially just which atomic level is excited. So if it's a very low frequency, for example, that means you're raising the amplitude of measuring the 0 state. If it's very high frequency, you're raising the amplitude of measuring the 1 state. Yeah, that's just for a single qubit. So that'd just be, a laser firing on a single ion. Let's say this one on the left, for example, you just have a laser firing over here, and that would be doing your quantum computation, right? Now, multi-qubit things is where stuff gets a little crazy. So there's multiple ways of doing this. And because trapped ions, again, are relatively new technologies, no one has come out and specifically said that like, oh yeah, this is the best way. But I highlighted some of the most like intuitive and kind of best ways that we have right now. So the first one is to just move, our targets into adjacent zones. So for example, again, in this type of system, let's say we want to have this qubit at the left and this qubit at the right. We want them to interact, right? All we would have to do is simply take this ion and magnetically move it all the way to the left over here, right? And then they'll be next to each other, and then we can just shoot, a laser or two, and then hit them both so that they're interacting in some way, right? And that'll be your 2-qubit operation. On the other hand, the issue with that is that, actually moving it, first of all, it takes a lot of time, very, very precise magnetics. And when you have a bunch of ions bunched together, it gets very, very messy. So another way that scientists invented, and is very, very cool, but very, very hard and conceptual. And I hope that, you attempt to understand it, but it's okay if you don't, is that because all of these ions are grouped together, to a degree, their motions are linked to each other, which is, a bit of a hard thing to understand. But, because they're so close and, they're all vibrating a little bit at each point, what you can do is you can actually craft a laser operation such that, you fire it through all the ions and change its phase and its amplitude and different things like that. So it's changed the actual waveform of the laser such that it'll only affect the qubits that you specify. So for example, like I said here, let's say you want to hit this laser, this ion and this ion. What you would do is you would fire a laser through here, and you would craft that laser beam such that its amplitude hitting this qubit would be really high, and this one really high, and then the rest of them, you would try not to affect, right? So again, a very, very difficult concept, but essentially you'll be firing a bunch of lasers. So in your pre-computation, you'll try and figure out like how to make the laser hitting these cancel out, right? So that's why laser engineering is also a very important part of trapped ion quantum computing. You're essentially using them for every operation. And so laser engineers are very much needed for the field. Lastly, measurement. So, how do we actually measure our quantum qubits, right? This is not a very intuitive thing to think about, but it's pretty fun. So essentially what you do is you have a very special laser. It's called a detection laser. And, it does exactly what the name says. You would fire it at the qubit or ion that you want to measure. Let's say, again, this one on the left. I know I'm picking on him a little bit. I apologize to him. But yeah, so you shoot this detection laser at that ion, and a very interesting thing happens. So the laser will either, if it's not excited, it'll just stay dark, right? The laser doesn't have enough energy to hit it and then emit a photon. But if the ion is excited, then what will actually happen is the laser will hit the ion, and the ion will get so excited that it'll output a photon. So essentially, when you're doing your measurement, you're firing a laser at an ion, and then you're measuring to see if any light comes out of it. And if it does, it's in an excited state, which corresponds to a state of 1. And if it doesn't, that means it's not in a very excited state. It's in a ground state. So that means that it stays dark and we get a state of 0. And then here's just an experimental example of that. We use some transistor technology, very fun stuff. If you're a upper year electrical engineer, you'll learn about it a bit more. Yeah, again, very cool. You'll measure if you're using a very, very small camera, see if there's light, and then you'll get an output that way. Yeah, so now just a bit about my personal opinions on ion quantum computing, and take this with a grain of salt. This is, of course, I've tried to keep it as objective as possible, but my personal opinion comes in here. So really good things about trapped ion quantum computing is that, of course, it has the highest fidelity gates amongst all quantum platforms. So when I say gates, I just mean your quantum operations, right? So your lasers firing, and essentially the highest fidelity just means that they're the most correct, they're the least prone to errors, right? So a laser hitting an ion, that's relatively old technology at this point, so we've really ironed out a lot of the kinks in it. Very, very good, right? Now another good thing is that trapping ions, like I said, we're nearing on 80 years of the technology at this point, which means that we're actually able to get them to be trapped for a very, very long time. In the previous presentation and in the morning presentations, you learned about superconducting quantum computing. And the problem with that type is that its coherence times, or the amount of time that your physical circuit can act as a qubit, is very, very short. Trapped ion quantum computing, on the other hand, your trapped ions can last quite a while. So they can last into the seconds, which is very cool. Another cool thing is all-to-all qubit connectivity. So I'm sorry that I keep dissing superconducting quantum computing, because superconducting and trapped ion are very opposite ends of the spectrum when it comes to pros and cons. But because you have this sort of structure where all your ions are lined up and affecting each other and different things like that, when you're doing multi-qubit operations, you can apply them to any qubit, right? Or to any ion. So, you have one on the left here and one on the right here. You just need one operation to affect those versus a superconducting qubits, which, say they're on opposite ends of like your circuit. They can't directly connect. You have to send information through other qubits, and that gets a little bit noisy. And then kind of the last pro is that we have excellent measurement accuracy, again, because we're just using lasers, and this technology has been super developed at this point. And again, the core principles of trapping ions is all electromechanical. So, it's a very developed field. We know a lot about it. If you ever talk to a physics professor, they'll say that the field is done, which essentially means that all the theory behind it is complete. Very cool stuff. Now for the cons, we have slower operation speeds. So, doing these laser pulses and different things like that takes a lot of time. And so, when a lot of people say trapped ions have long coherence times, that actually gets canceled out by the slower operation speed. So the operation speed at which, we fire our laser and it does a thing to the ion is very slow compared to things you would have in superconducting computers and different things like that. So it actually negates the fact that, these trapped ions can last for so long. The ratio of an operation or an operation speed compared to semiconducting versus trapped ion is, they basically cancel out. So even though superconducting qubits can, not last for very long, their operations are very fast. So the kind of ratio is about the same. Another thing is that physically moving these ions, like I said in the previous couple of slides, requires very precise magnetic control, and is very difficult to do. And that's why a lot of people prefer to just do that kind of cross qubit chain single laser instead. Another con is that supercooling is needed. With trapped ions, there is a bit of a caveat, and that's you don't necessarily need it as cold as other quantum systems, which is nice. You need it, it's a single digit Kelvin probably, but some systems you need and like millikelvin, so it's a little bit more doable. And then the last thing is that trapped ion quantum computers are inherently dense, and essentially that means that everything is very close together. And when you're scaling up these systems and you're having like a 200-300 going up to 1,000 qubit trapped ion quantum computer, things get very, very tight and very, very packed, which means that it's harder to do a lot of different things. The wavelengths of lasers and different things like that can get very big at times. And so you don't want things bumping into each other, which is kind of an issue. Past the scalability, of course, we want to build up our quantum computers very well. And so a nice thing about trapped ion quantum computing is that because you're using all these lasers and photonic stuff, it's actually very easy to interface a trapped ion quantum computer with photonic electronics, so that we can actually link a bunch of quantum computers, trapped ion quantum computers together using photonic links, right? So because we're just using lasers, we could just, shoot a laser at an ion, and then that'll give back some like photonic information. Then we can just send that photonic information through like a fiber optic to another trapped ion system, right? So in theory, trapped ion quantum computing is the second best in terms of modular architectures, we call it. So taking a bunch of quantum computers and putting them together, just behind photonics, obviously. And another good thing, obviously, is that we have these surface traps. They're essentially just chips, and chips inherently work very well together. Like I said, also, there's a lot of integrated photonics. And of course, photonics is a very developed field. So as we build this technology even better and better and better, we can actually get to things like quantum memory, where we can, store our quantum information in an optical cavity or something like that. And then, how we're actually doing this right now is that we need to build better lasers, a better vacuum, and better cryogenics. So if you're interested in being a laser engineer or a cryogenic engineer, trapped ion quantum computing is a very nice field for you to do, just because you need this for every single computer, and we need these systems to be better and better and better. So if you ever have the opportunity to pursue some work, an internship, or some research in these fields, I highly recommend it. It's very cool stuff, and it's very applicable as well. So yeah, that's it for me. I just want to point out the different types of traps here. So when I mentioned these like chip architectures, this is essentially, you know, one chip. So this would be one quantum computer. And it's, like I said, that like 2D chip trap. And you can see that we have this like little line, a 1x1 row of, you know, trapped ions, right? It's pretty cool stuff. This would be an example of more of a penning trap. So we can see here that they're kind of surrounded by these like electrodes and different things like that. And in the middle, if you can see, it's very, very small. We have one single trapped ion. And, you know, this is an experimental setup, likely a dark matter experiment. This is the crystal chandelier I was mentioned before. So these are all cryogenics, just to cool the system down because we needed to. And then this one is kind of a larger scale trapped ion quantum computer. And this is from Oxford Photonics, I believe. And they do some very cool stuff with trapped ion to photonic links and kind of interfacing those systems. And yeah, if you have any more questions, just let me know. Again, I'm helping out with the hackathon, so I'll always be in the Discord. You can just at me, shoot me a message, DM me, whatever, with any of your questions you may need. Thank you all. And I'm open to questions now if anyone has any. I can't see the chat, by the way, so I'm going to stop sharing just so I can see the chat, and then we can go from there. How are the ions isolated? What do you mean isolated? Like, how do we do a single operation on a single ion? Well, we just hit it very precisely with the laser. So we have it in a line. Here, let me share screen again. So we have, oops. So again, I can't see the chat, but I hope I can answer your question well. So we have these in a line here. And, you know, the ions are spaced far apart enough that we can hit each individually with a laser. So like, let's say we're trying to hit this one, we would just like kind of go from the side and hit it, and it wouldn't affect anything else, right? So like you don't need to like move this over here and then do a thing and then move it back. We can just directly hit it with a laser. Here's a question. Hey, I'm wondering what new difficulties arise when trapping ions in 2 dimensions versus 1 dimension. 2-dimension traps, I assume you mean the 3D trap versus the 2D trap. Yes. So I would say that the biggest issue with the chip trap is that, you know, you can't have the ions in the chip, right? Because it's 2D. You need to have them risen a little bit above with something like this. And if your RF, you know, your RF engineering and your microstrips isn't very, very precise enough to the point where you get like this generated magnetic field, they'll just like come off, which is very, very annoying, obviously, versus this, where as long as your like charges and your fluctuations are, you know, decent, then they'll be trapped. So I would say that's the biggest difficulty. Why the pole trap is 3D? Well, the actual ions are still like in a line, but the trap itself is 3D as opposed to a chip, which is flat. Yeah, we just call it the 3D pole trap. You could call this a 2D pole trap just because it's a flat chip versus you know, 3D system. It's kind of like you can think about this like a prison. This, well, I don't have a good comparison for this, but yeah, this is kind of like we're locking them in jail, and this one is like we're pulling them towards the ground. Let's see what else. At the beginning, you talked about trapped ion qubits work really well together. What does that mean and why? So I might have misspoke. Trapped ion quantum computers work really well together, and that's because, like I said, we can very easily interface them with like photonic links, so that we can have, you know, 2 quantum computers, 2 trapped ion quantum computers, and then like a fiber optic cable in the middle. And it's very easy for trapped ion quantum computers to interface with that fiber optic versus, you know, a superconducting system, different things like that. That was to Prithvi. Yes. I hope that answered your question. Is there another laser than used for the laser cooling process to slow ions down? Yes, generally. So your laser cooling process is generally different than your like actual computation process. I'm not a laser engineer, so I don't want to get into specifics so I don't confuse anybody. But yeah, generally, like I have in this diagram here, your qubit control lasers will be one specific type, and your laser cooling will be another type. Can you explain how a laser can be used to cool an atom? Okay. This is very this is getting into laser physics, which is not my forte, but I will do my best. So I wish I had a good diagram for it. Laser cooling in general is a bit of a tricky thing, and there's many different ways to do it. I guess I'll use this diagram. And essentially what we're doing with laser cooling is that we are relying on thermal relaxation. So if you this is a very top level, high level explanation, but if you shoot a laser in a certain way, naively you would think about a laser hitting an atom, and that that's adding energy to it, right? But if you knock some energy, you can actually like knock some energy out of it, right? So you can see here in this little diagram that this would be like our laser, and then we can see these are when you see squiggly arrows and trapped ions, those are generally photons. And we'll hit it in a certain way such that it'll release energy as opposed to adding energy to it. And like I said, that generally releases in the forms of photons, which are light. And then that'll usually relax the ion in a certain way. And of course, when we're doing laser cooling, we're also using cryogenics as well. So yeah, so we're cooling it, physically using the cryogenics, but also kind of knocking the energy out of it, and to bring it down to a lower energy state. I hope that answered your question. It's a very high level explanation. Again, laser cooling isn't really my specialty. Yeah. How do the ions stay equally spaced from one another in the trap and not collide in the Z direction? So generally, their charges will, well, okay, this is kind of a twofold answer, but usually we'll focus on this, not so much this, just because this has the wave lines. But generally we'll kind of format our control waves in a way where they'll kind of, we'll have a few waves contributing in a well to each ion. So we'll have kind of this structure for each ion, rather than just having your row obviously like all across here or whatever, because that doesn't work, right? So we're actually in this diagram is a little bit confusing because it looks like we're only confining it in this direction, but we actually are in this direction as well. Just a bit of a misleading diagram, which is my bad. Rebecca, I hope that answered your question. Let me know. How are 0 and 1 seen as equals? Is 1 like storing energy? What happens if there's a 2 state? So generally, we atoms generally have multiple energy levels, but in most cases, our energy levels aren't equipotential, so they're not like of equal distance to each other. So usually the lasers that we're shooting at these don't have enough energy to raise it to like a 2 state, for example. It's usually just 1 or knocking the energy back down to 0. And again, I don't know if I mentioned this, but we use different lasers for exciting and de-exciting. So yeah, so it's a lot of control electronics stuff that we're using in that. Yeah, and again, just remember that the 0 state is generally like a non-excited ion versus a 1 state, which is a very excited ion. And even if There's very, very slight imprecisions in like bringing it up to the one state. Generally, your control electronics will just read it as like excited or not excited, even if there's like a tiny energy difference. Mac, I hope that answers your question. Yeah, I mean, again, I'll be in the Discord, so feel free to shoot me a DM or anything. If you're curious about our research, I can send you some more resources there, or if you're interested in doing, you know, further readings and different things like that, I'll be happy to send some papers out to anyone that's interested. And I'll be around. You know, I'm also helping with the hackathon. So, what is my Discord name? That is a great question. I believe it's msilv160. I will change my name on the Discord to my actual name, which is Michael Silver. So just look for a Michael, look for a Silver, and I'll be there. Yes.
I just have a question. So here's the thing. So in like the trapped ion computing, what happens like if like some like ion got like too much energy and got into like the 2 state? What will happen?
So like I said before, generally,
I like in quite fully remember what you said. That's the thing.
Yeah. So generally, like these distances won't be the same. So like 0 to 1 will be, you know, say for the diagram 1 centimeter, then 1 to 2 will generally be like a lot more than 1 centimeter. And so the stuff that we're doing to the atom generally won't have enough energy to raise it up to that second level. And also our control electronics usually account for shooting something that's in an excited energy state. So generally in like, you know, your classical control, if it's being seen that, you know, an atom is in an excited state and we're shooting, you know, we're doing an X operation, which is just, you know, raising or lowering it, then it'll just automatically shoot like a cooling one instead of re-exciting it to an X level. Does that answer your question?
It answers my question. So yeah, even though it looks like it's intended that 0 and 1 should be equals, but I don't feel like they are equals because 1 is actually closer to the next highest energy state. So there seems to be like some level of asymmetry.
Of symmetry between what?
Basically like 0 and 1. Oh, I kind of remember. Is it like kind of like low voltage and high voltage for a classical system?
I don't know if there's an exact classical kind of transfer kind of thing we can compare it to. Maybe. Yeah, I don't know. I don't know. Maybe you could DM me and we could talk further about it because I don't really understand the analogy that you're trying to make.
Okay. But like but you did like answer my question concerning why the energy levels are used as trapped ion qubits.
Okay, cool. Yeah, anyway, that's it for me. Again, I'll be around. Just shoot me a DM if you're more interested. And yeah, thank you everyone for coming to my talk. I'll talk to you all in a bit in the future talk.
Thank you, Michael. Thank you, Michael. That was wonderful. I would now like to introduce a professor from our very own McMaster University, Dr. Welland, and he is joining us today to give a talk on how to use COMSOL. So if you wouldn't mind giving a brief introduction about yourself before you start, and then the hour is yours. Thank you very much.
Aha, I was on mute. There we go. Can
You're
you
good
guys
now.
see my screen?
Yes.
Professor can't figure out the mute button. All right. So, well, welcome. My name is Mike Welland. I'm a professor at McMaster University. Just started at McMaster about a year ago now. I was at Canadian Nuclear Labs before then. I think I've been using COMSOL now for 20 odd years or so. So it's definitely, it's been around the block. If anybody's wondering the original origin of COMSOL, it started off as a module under MATLAB that then, I'm sorry, I should talk a little bit about myself first. So what I do is mostly computational material science. It's all over nuclear, of course, because our experiments are very expensive and a little bit dangerous with, there are a lot of safety precautions and things like that. So the computational modeling really kind of like kicks in. And, can we experiment in one set of conditions and then project out, 20, 30 years out into the future and figure out if those reactor components are still going to hold up. So in order to do that, we need kind of the computational material science to prove that safety case and, verify that we're able to understand what's going on and how the material behaves. So COMSOL actually started off with as a module in MATLAB, originally called FemLab. And then FemLab got more and more popular. Everybody started to use it. So then they spun off into COMSOL, which is now in, I think 6.3 is the latest one. There have been a lot of changes, but if you are familiar with MATLAB, you would probably you'll probably recognize a few of the syntax and kind of the way it's built and things like that. But I mean that divergence was about 15 years ago at this point. So at this point they are pretty isolated. So a little bit about COMSOL. I'm just gonna switch over to the general chat here. Yeah, here we go. So a little bit about COMSOL. Sorry, a little bit about finite element method. I'm gonna paste in a link to, here we go. That is a playlist on for the 2CM4 computational multiphysics that I teach. I started teaching it last year and I recorded a bunch of YouTube videos for it to help people get into it. So if you follow that link, it should bring you over to the channel. And then there are a few different playlists. The first one is going to be kind of the introduction to COMSOL. Feel free to look through the other ones if you like. It'll go into different applications: heat and mass transport, solid mechanics, elastomechanics, electrostatics, magnetics, eigen decompositions, and all of that fun stuff. So feel free to go in that. If you're curious about the finite element method itself, I'm going to be a little bit cautious. I am going to send you a link to the textbook that we use in numerical methods for engineering. That is the finite element methods section. The computational multiphysics is actually taught as a second-year course, and then numerical methods is taught as a third-year course, which sounds a little bit backwards, and we might actually change that in the future. But the nice thing about using a tool like COMSOL is that it's done all the hard math for you. The finite element method is very sophisticated. It's very fully featured. There's a lot of mathematical theory that goes into it, but it does get fairly formidable. So the finite element method, when we discuss it in numerical methods, is right at the end of the year after we've been talking about all sorts of other things: numerical error, function spaces, root finders, optimization algorithm, partition schemes, et cetera, et cetera, et cetera. So the nice thing about using COMSOL is that it's packaged all that, it's made it all uniform, and it's hidden that from you, which allows you to focus on kind of the big picture. So if you click on the link and you think, oh my goodness, like what have I gotten myself into here? Don't worry. COMSOL is going to hide all of that. And generally speaking, I worked with people at CNL for 10 years who were using COMSOL and never got into the mathematics behind it that actually underpin it. So that's really good. COMSOL itself is industrial grade software. We've used it at CNL. We still use it at McMaster. Ontario Power Generation uses it. All the big companies, GE, all the big manufacturing companies use it. It is a modern software tool. It is very, very powerful. It was designed after Ansys. So I think at this point, you've also been exposed to the Ansys lesson too. In my perspective on things, Ansys is a little bit more geared towards very specific applications. So there's Ansys for elastics, elastomechanics. So anything to do with strain, stresses, structural mechanics, there's an Ansys module that is very, very competent for that. For quantum, there's an Ansys module that is very, very focused on that one. COMSOL took kind of a different approach. They instead focused on the multiphysics part. So what's actually happening underneath is, by and large, all of COMSOL's numerics underneath things are the same. And all you've done is you've just taken them and applied them to heat transport, electrostatics, eigenvalue problems, elastostatics, particle tracing, et cetera, et cetera, et cetera. It's a lot more general, so that you can couple the physics. You can pull things different in, so you can do heat and electrostatics at the same time on the same platform. Ansys has started off a bit more siloed, and now they've moved like that. COMSOL starts on a similar base and spreads out like that. That's my perspective on how the two differ. Let's see. Okay. If you open up COMSOL, I'm going to show you guys a few things here. One of the ways that I learned COMSOL back in the day was going under, I think it's under File and Application Library. And when you click this thing, it's going to bring up a whole host of different example modules that you're going to be able to load. So if you search here and you're looking for I don't know, say you want corrosion, right? You can click on that. You can click down here. If you click on any of these, they're going to have like a description of the system that it's working in. You double click on that and it launches the entire working module. And if I think there was actually even an ion trap here too. Oh, no, it needs to rebuild it. Okay, so not an ion trap, but there is, there's a different kind of ion trap. There's quadrupole mass filter for mass spectroscopy. You can pull up these, and I think the license that you probably have, if it's the one that I'm thinking of, it's fully featured. So it has all of this stuff in there. By all means, click into that, like play around. There's documentation here that you can go into, and you can kind of learn by example, which is really nice. If you don't find what you're looking for, click over on Application Gallery, and that's going to give you the web version of it. And now you can search for basically anything. There are over 1,000 different modules on here. Let's look up quantum. Here you go. You want to do quantum dots, you want to do solar cells, you want to do resonance, you want to do quantum dots in a uniform magnetic field. All of these modules you're able to download, run on your model, on your own computer, tweak and see how it behaves. And that's a really, really effective way to learn how to do this stuff. Okay, that being said, let's get into what on earth this is actually doing. So finite element method, COMSOL uses something called finite element analysis, finite element method. And the idea is that we're solving partial differential equations. If that doesn't mean anything to you, that's perfectly okay. What we're doing is we're solving things that they're very natural. As far as we're aware, the rules of the universe are written in differential equations. What that means is that it's going to link the rate of change of something to that something. So kind of the quintessential example is population growth, right? The number of babies, right? The number of people in the new generation is proportional to the number of people that there are, right? Very simple idea. But what happens is that as you have more people on the planet, in your system, in your town, whatever, you're going to have more babies. Those babies are going to have more babies, and you're going to get kind of this exponential growth, right? That exponential is the solution to kind of the canonical differential equation. We get more complex. In COMSOL, it solves those differential equations, but it does so over space instead of time. Population growth is usually over time, right? Doesn't really matter. It's all the same as far as COMSOL is concerned because it's focusing on kind of the general mathematics underneath. Let's see. Finite element method will find the approximate solution to these things. Typically, the way that you would learn it is you would work out like kind of analytical functions. So you would say that your population is an exponential, e to the power of something times time. And that's just going to take off like that. In very specific cases, and honestly, very few cases, can you actually find an analytical solution? I just realized you can see all the Halloween candy that I'm still hiding from my kids up on top of the bookshelf there. Ignore the Halloween candy. I don't have any to share through the computer. So what COMSOL is going to do is it's going to solve things like heat transport. For example, heat transport is near and dear to my heart. Thank you, Clarissa. Right? Quantum fields are going to be expressed in the language of partial differential equations. What they're going to look like is something like this. This funny upside down triangle is called nabla. Del, it's the gradient. Doesn't really matter. In this case, it's actually the divergence. What this is saying is that you have, this is for temperature. So what happens is that you have temperature that is over some object, say this book, right? And you have a high temperature over here, you have a low temperature over here. Heat is going to flow downhill. That's what heat does, right? This Q is your heat flux, and it has this constant. This constant is called thermoconductivity. Grad T is just the downhill slope. That's all you need to know about differential equations, honestly. And then the next part is the change in temperature at a point is related to how much heat is flowing into it and how much heat is flowing out to it. And the difference between in and out is your accumulation of heat. Honestly, it's that simple, right? If you've ever been in a classroom, the number of students in your classroom is the number coming in through the door minus the number going out through the door. It's that easy, right? And through COMSOL's ability to generalize these things, you can kind of actually use this and get to learn about like different things. Be aware that because we're solving things analytically, you can get very, very computationally intensive. So I'm going to show you when exactly that happens. And what to watch out for. In 2D, you're pretty much okay. 2 dimensions, you're pretty much okay. As soon as you get into 3D, you can get into a lot of problems really quickly. I'm just going to show you down here. A 6.3 now lists your memory usage down here. What I would recommend you do is before you go into 3 dimensions, and I'll try and push you in the right direction to do this. Know how much RAM your computer has, okay? And watch very carefully this number while you're solving things. Or if you want, the other thing you can do is go up to your task manager. You know, if you're using Windows here, sort by name. Where's COMSOL gone? Here's COMSOL, right? Right now, it's already using 1.5 gigs of memory. My memory is already at 81%. My laptop doesn't have a lot of memory. If this gets too high, and by too high, I mean in the 90s, right? You might want to close everything else that you're running just to free up that RAM, especially if you're on Windows. Windows tends to, like any Chrome is notorious for like gobbling down RAM, right? If that number gets too high, and you max out your physical memory on your computer, it's going to do something called paging. What that does is it starts writing blocks of memory to your hard disk. And the problem is that that's about 1,000 times slower than just operating on your physical RAM. When that happens, your computer will brick. It will not respond. Your mouse will not be moving. If you've ever had that time when like all of a sudden your fan is going on, you hear that click, 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 if you have the old school disk drives, right? And you can't, that click, click, click is the memory being written to your hard drive, by the way. All of a sudden you can't do anything. And honestly, when it gets to that point, you might just have to force shut down to release it. So my advice to you is going to be start with really simple models. And what that's going to mean is a coarse mesh. I'll show you what meshing is. Once you have a solution and you understand how big that model needs, watch your memory consumption before you refine your mesh and you get to a better solution and a better approximation. And if that number starts to get so high, right click and task. Okay, if you're on a Linux system or you're on a Mac, I think it's kill-9. You know, that's like the emergency unplug that, you know, metaphorically, it's the emergency override kill. Okay. Have that handy when you go into 3D. And for the love of all that is holy, save beforehand, because nothing is worse than having to shut down your computer by force and losing all that information. While we're on that topic, if you do that, if you do have to force kill it, every once in a while when you reload COMSOL, it'll say that that file is locked. What does locked mean? Locked means that if you go into the directory that that file is in, you would have another file with the exact same name and a .lock on the end of it. That would be your file extension. That's a way to make sure that you're not double, like it's an operating system thing. It makes sure that two people aren't changing the file at the same time. Go ahead and delete that, and then you're back to normal. Okay, so if you see a lock file and it's complaining about lock, you can save a copy if you want, or just delete the lock file and you're fine. In 2D, generally speaking, you won't have to worry about this. In 3D, be careful. Okay, that's my that's my advice to you guys. Okay, so now we can actually talk about what on earth this is doing. When we're doing partial differential equations, what we want to know is the solution to a differential equation like this over our entire block. So this is going to be a rectangular grid here. This is an example if you do want to follow it along. It's
Sorry,
under...
Dr. Welland, we have a question from someone in the chat. They're asking, what is COMSOL written in? And does it run entirely on the CPU, or can it make use of GPU acceleration?
COMSOL is, that's a great question. Mr. Dandelion. All right. I have absolutely I have no idea what COMSOL is written in. The big number crunching computational engines underneath, COMSOL kind of sits on top and calls these numerical solving routines underneath it. Those things are probably written in Fortran, to be entirely frank. And I don't mean Fortran 97, 93. I don't mean Fortran 77. I mean Fortran. Like, these things are old, but they work and they're as efficient as you get. I wouldn't be surprised if modules are integrated into assembly even. The top level of COMSOL, if you look into the .mph files, I think it's actually XML. So it's actually even human readable. Underneath that, I would imagine it's some kind of like Java, and then on and on down. GPU acceleration, no, is the short answer. Linear systems, because I don't have a good way to explain this without going into numerical methods. Because of what you have to do to solve these things, you can't distribute them very well between different computers, between different cores, between different, I forget what GPUs call them, operational units, or anything like that. You have to solve them together all at once, and that generally means that GPUs don't work very well on it. The best analogy that I can give is sometimes you would have a problem and you can easily farm it out to, if you're working on a group project. Some group projects are easy to divide amongst your members. You do one, you do one, you do the other one. We'll meet in 2 weeks and we'll get all the information together and then we'll write the report. Right? That is good for GPUs because GPUs kind of like to shotgun things. Computer graphics are great for that because each ray is independent. They don't overlap. There are other projects where you constantly have to be talking to each other. And if you're constantly talking to each other, then you can't distribute it. You can't work on it for a week and come back afterwards. You have to work on it together. And unfortunately for us, linear systems and a lot of these cases that COMSOL is specifically built for, these multiphysics systems, require that constant communication, which means CPUs. There are some counterexamples. I think the particle tracing module, the neural net training module, which is all built into COMSOL, but is frankly a little bit advanced, I think do have GPU acceleration, but don't count on it with this. Okay.
I see. Thank you.
Yes, thanks. It's a good question. Thank you for the question.
Actually, I had one more question. So,
Sure.
I actually didn't have enough space to download all the application libraries. So, is there a way that I can download specific ones?
Yes.
From...
Yes.
Yeah.
So there should be an option when you when you're installing the software, there should be an option to only download, I think, the list of applications and not the files themselves.
Yeah. And
Right?
like after I already download, is there a way to like update that or?
Yes. When you go into the application library and it's just this blue empty circle,
Yeah.
what that means is that it's there, but if you actually go to open it, it's got to download a local version.
I see.
Yeah.
Okay. Because for me, I have like nothing there since I didn't download any app libraries.
Yes, yes,
Not
yes.
even the blue empty circle.
Oh,
Yeah.
I would definitely download at least the application library just because that'll give you that list. Otherwise, you can also just go on the web link here and you can just download the stuff straight from there.
Okay. So
Yeah. If you're running low on space, by the way, it gives you this option: open a local compact file or a full file with the solution, which is a lot bigger. That's like a quarter of a gig, right? What happens is you're going to build up your model in COMSOL, and then you're going to hit calculate, and it's actually going to calculate that solution. That solution is the big hefty thing, right? But so when you just download the local compact file, what that is, it's just the instructions. And then you would hit compute and it would actually find that solution for you. But if you're running low on disk space, then you probably don't want to do that.
I see.
Yeah.
And is it possible for me to like download the stuff from the application gallery, like the
yes,
quadruple mass?
I think if you go there, it's a website here. You can actually just go to that one. And then when you click on one of these options, I think you can just download the file directly. This is the MPH files. They're the multiphysics files.
I see.
Yeah.
And for the example we're doing right now, what should I search to find what I have to download?
Oh, I have no idea. Talk to Michael and the organizers about that.
Okay.
Yeah, I think they're going to give you some ammunition. I'm just pointing out a way to find more information.
All right, sounds good. Thank you.
Okay, excellent. Okay, here we go. Cylinder conduction. Cancel that. So the module that are the example that I'm going to show you is actually from here, and it's cylinder conduction. So what you can do if you like, just open up your application gallery, go to cylinder, like search for cylinder conduction. I'll type it in here. And you double click on it. And what it's going to do is it's going to open up an example file for you.
Sorry, Dr. Welland, we actually have another question.
Oh, sure.
Prithvi is asking, how is FEM different than DFT?
You mean density functional theory?
I assume so.
Yeah. DFT is looking at the electronic structure around nuclei. So DFT is very useful for molecules in particular. So okay, DFT is looking at the electronic density. And what you want to know is the electron density around your nuclei, which is your density functionals. DFT, density functional theory. It is, as far as I'm aware, I've never actually done DFT myself, but I've worked with professionals that do. It is essentially solving Schrodinger's equation for the electrons. The problem is that you don't want to ever have to track individual electrons. First of all, because I'm talking to a quantum cloud, I can say this. Quantum crowd. It is an electron cloud, right? That an individual position of an electron doesn't really mean very much because it exists in the superposition in this cloud. So instead of looking at individual electrons, whatever that does mean, what they're looking at is the density of electrons at points in space. The problem is, so you could actually do this in COMSOL, and I think there is actually an application library example, I want to say, of the hydrogen atom. So you can do that. It can solve Schrodinger's equation. I think there is an example of the hydrogen atom, and we actually took it up into CM4 last year. Feel free to look at that. Schrodinger's equation is a partial differential equation, but even just getting the hydrogen example is very difficult, is very computationally intensive. So instead of solving Schrodinger, they solve approximations to Schrodinger. And by making careful approximations, you can make a related problem, which is easier to solve and still gives you good information. DFT is really good, especially for molecules or like free floating molecules. For crystal structures where you have like longer range periodicity, it's not so useful. But that's a lot more optimized for that in particular. What should I search to get cylinder conduction? Well, here, let me show you here. Okay, File, Application Libraries. Okay, I'm just going to refresh that. Cylinder underscore conduction. And it's going to come under heat transfer module, tutorials, and cylinder conduction. I see shell conduction from the website.
Yeah, because I don't
Yeah.
see anything for like anything in my app libraries because I didn't download any. So I'm like trying to find
Oh,
it
I
from
see. I
website.
see.
Yeah.
Okay. I don't want to delay things. If anybody wants to, so just to keep moving forward, somebody, if you want to save this to a file and maybe you can email it to Mr. Dandelion, or I don't know if there's a share space, then you can just download that local copy and open it like that. That might be the easiest way.
All right. Thank you.
Okay, excellent. Keep them coming. Any questions that you have during the meantime, by all means, ask them. Okay. What on earth are we actually doing with finite element method? When you have where do we go here? I'll come back to what exactly I'm doing here in a second. Okay, so we have this differential equation. We want to solve it over this block. This block is actually it's actually a piece of a pipe that's revolved around the outside, but because we're using symmetry, we're just seeing that cross section. What we want to know is your temperature profile in that entire block. The problem is that your temperature profile is probably something complex. So instead of solving for that profile, what we're going to do is we're going to divide up our space into these little triangles. Why are we doing triangles? Because triangles are easy to space fill. For a rectangle, that's not really such an achievement because even squares will work. But you can imagine these complicated shapes, curves in particular, sharp, narrow corners, everything. Triangles will always fill those spots, whereas like rectangles, it starts to get really complicated. Okay, so what we're going to do is we've broken space up into these little triangles, right? They're called elements, and we have a finite number of them. Finite element method. What we're going to do is we're going to approximate our function, temperature in this case, right? Electrostatic field, whatever you want. COMSOL doesn't care, right? We're going to approximate it on these little elements using a very simple function. Typically, that's going to be a polynomial. Right? So some kind of quadratic surface, you could use a flat surface. COMSOL likes to have quadratic surfaces. I'm not going to go into the reason why that is. And then what it's going to do is it's going to say that element here, let me show you guys an example. So we're going to have a solution that looks on one of these triangles, and COMSOL is going to say the temperature at this point has to be the same as the temperature on the other element, which is also the same as the temperature over here and over here and over here, right? So we have this continuity that's called C0 continuity, and we have some idea of slope continuity. We do not have slope continuity, okay? When you look at this, you're going to find a solution. Let me see if I just have a solution. I'll just show you guys firsthand. No, that's smooth anyway. Don't believe that. Yeah, I wouldn't believe that. I think it's smoothing here. I don't have an easy way to show you what that actually looks like. But if you look at it and it doesn't look smooth, it looks kind of faceted, like a video game, right? Like it's using similar techniques. I'm just going to say really quickly, because COMSOL is very fully featured, it's almost too good. It has a whole host of things that you're not going to need to use. Like, for example, if you just go on here and you start looking at this and you think, oh my God, okay, discretization, quadratic Lagrange, dependent variable is kind of obvious, right? Equation form, frozen rotor, like, right? Don't worry about it. COMSOL has all these different features, but it's actually very good at finding the defaults. It is also doing hidden things for you. That solution is not going to be smooth and continuous. It does have like an inbuilt blur because it wants you to have like a nice picture so that you share it around and say, wow, what a great job COMSOL is doing. So just be a little bit aware of that one. Okay. Let's see. Also be aware we are finding a particular solution that is an approximate, right? We are not finding the real solution. Because we're in a numerical method, if you did want to find the exact analytical solution, you would need an infinite number of elements, right? That would be the infinite element method, otherwise known as continuity, right? If you divide up a line into infinitely small points, then you have continuity, you have continuous spacetime. We are not doing it that way. Let's see. Okay. If there aren't any other questions, I'm going to dive in and I'm going to kind of walk you guys through what all these different things mean. You know what? I'm not going to pause for questions because I think I'm already behind. Any questions, just chuck them into the chat and I'll try and keep my eye on it. I see Mr. Dandelion found the example. Good. Okay. So COMSOL is I would say an object-oriented language. Probably if you guys are doing something like a quantum mechanics hackathon, you've done some computer science, so you know what object-oriented means. That was one of the big jumps. I think that happened with COMSOL 5, that they kind of moved into this modularized form, but just keep that in mind. Does COMSOL support Linux? Yes, it does support Linux. Yeah, there's actually nothing else I have to say about that. Yes, it does support Linux. I also run COMSOL on Linux personally. No major differences. Sometimes with the graphic acceleration, you have to worry about it when you're viewing your results, especially if you try and do, the animations. Animations in COMSOL on Linux suck. They don't work. I have no idea why. If you're stuck in Linux and you have to do something, what you can do is output your movie as a series of images, and then you give it to one of these like websites that take a whole pile of PNGs and assemble it into an AVI. I think FFmpeg will do it too. There are a whole host of things. That's the only way I managed to get it working to generate your animations. And everybody loves animations because they look awesome and COMSOL looks beautiful. But otherwise, yes, it works. It should work fine without any big problems. Okay. So COMSOL is object-oriented. When you go up to, I'm just taking a peek at my notes here. The first thing you're going to see underneath your file name here is going to be your global definitions. Okay. COMSOL is really kind of built with the expansion in mind into something like an engine, a car engine, right? So when you're doing a car engine or a car, you're going to have certain things, like think about it as an object-oriented approach, right? You would have an object which is a car, and within your car, you're going to have wheels. Your wheels are components. Oh, hi, Prof. You're good on time if you want to go into the next time frame a bit, since the talk will be short. Okay, no problem. Okay. Okay, so global definitions are going to be something that relies on your car, right? What relies on your car? The age, the ambient temperature, the number of people in it, the weight of the vehicle or something like that. Underneath your global object are your components, your tires, your engine, right? There are 4 instances of your tires, right? There are components of your engine. There are the seats, everything else like that. So you've got your global definitions, right? And these are going to apply everywhere to your entire thing. And then underneath, you're going to have components. And your components are going to be the things that hold on to the physics, for example. Your car doesn't have physics. Your tires have physics. They have the air inside. They have the elasticity on the outside. They have your heat balance as you get warmer and colder, right? that's where all the physics sits in your components. Global definitions, you might say something like the wheel size, for example, if you want to be able to mix and match different wheels, things like that. So what that means practically is that whatever you put into, you know what, I'm going to come back to that one. I'm going to skip ahead a little bit. What was I going to say? Yes, most of my COMSOL models over the last 20 years have only had a single component. Okay, you don't need to have different components. It's kind of one of these options that's good for like the human side, the readability and the upkeep side, but COMSOL doesn't care. If you want to have it in one component, if you want to have 15 components, it's up to the user. It's all about like software architecture at that point, right? This is model architecture is what you're doing with that one. So don't worry about that one. I just want to show you guys a little bit about what this is so that if you're, you know, if it's like 3 o'clock in the morning and you're giving it an expression and the variable isn't evaluating and you're pulling your hair out, what's going on? This is what's going on. Okay. So parameters are where you define your variables, essentially, right? Parameters are usually fixed. Whereas if you right click, get used to your right click button, by the way, COMSOL loves using the context menus. If you go down to variables here, then you have like your expressions that actually depend on other things. Okay. And there's a caveat to that one. Let me start off with parameters. So parameters are like your constants, essentially, right? So what you would do, I hope you guys, can somebody just let me know if you can actually read this, like, is it too small to come through on Zoom, or somebody give me a thumbs up if you can actually read this. I can read it. No, it's fine to read. Excellent. Good. Oh, there's a lot of thumbs up. Fantastic. I've never felt so popular. Thank you, guys. Okay. Okay. So what you want to do is you want to give it a name. It's a name, right? You want to do an expression, and you could say something like 10. And one really nice thing, you know what, I'll come back to that one in a second. You want to give it a number, which is your constant value. You can write your description. You can write whatever you want. Whatever I want, right? Doesn't mean anything. COMSOL doesn't care what's here. That's strictly for you. Something that COMSOL does that is very, very useful, I cannot stress how useful this is it will track your units for you. I'm not sure how much you're going to be mixing, matching your units, but how you would do that is you would put that into square brackets. So you could say 10 square brackets centimeters, and now when you hit enter, it's going to automatically convert it into your base units, right? In this case is meters. If you want to use other units, because I'm not sure how many people are from the US right now, right? Say you're not used to centimeters, you're used to inches. The code for inches is IN. You hit enter and it automatically converts it. Hallelujah. You don't have to worry about that. COMSOL is smart enough to do that. Love it. You can call other constants, other parameters from within like your next line there, right? So if you want to do B and you want to say A plus 1 centimeter, you hit enter and it does all that conversion for you. Okay. Super, super useful. I'm not sure what foot would be. I don't know if that would do it. Yes. Okay. Foot is just FT. Is COMSOL case sensitive? Let's find out. Yes, it is. One really nice thing about COMSOL that I really love is it makes it very, very easy to try things. And it'll just come up with like an error. It'll flash you out something. If something's not working or it's taking so long, just clicky, save. Always save multiple versions, right? Timestamp them, however you want to manage them. Save. But try it, see if it works. If it doesn't work, move on to the next thing. Okay. I do want to show you what's going to happen if you try and say A, which is in units of length, with 1 second, S. First of all, your value doesn't have the right units anymore, right? Because we're trying to add meters to seconds. What is 1 meter plus 1 second? Doesn't make any sense. I'm not sure if you'll be able to see, but it actually comes up with a little super faint yellow underline, a little squiggly underneath. And if you hover over it, it's going to say inconsistent units. What that means is that you're trying to add length to time, something like that. Super useful. Keep an eye on that, and it will tell you by itself if you mix something up. In engineering, we would call that dimensional analysis. In practical, actually getting something done at the last minute, it's just the saving grace, because otherwise the units will get you. Some of these units are in dynes per millisecond Kelvin or Rankine or something else obscure. COMSOL will handle all of that for you. It's really, really useful for that. Okay. Let's see. If you wanted to do, I'm going to delete these guys. Okay. If you wanted to do a variable here and you want to say, let's try h, and this is equal to x times 2. Okay. First of all, oh, it doesn't know what x is. Yeah. Okay. I was thinking Cartesian coordinates, which are x and y. This model is cylindrically symmetric. So instead of x and y, it has r and z. Okay, so what you would actually need to do is something like that. R, it already knows that R is in meters. So when you do R times 2, it already knows that you're going to be in meters. If you wanted to do something like, see, I couldn't remember if it was star or hat. Turns out it's hat, so that's how you write power, right? Just to go over that, just for you guys to use. If you've ever run like star, right, to have a power, it's immediately going to throw up now a red squiggle. It's a syntax error. What's going on, right? So you just go back and you just do that guy instead. Lo and behold, it gets it, and it even makes the unit right. If you try to do that in the parameter, it would not be able to. It doesn't know what R is. And that's because your parameters are constants. They don't know anything else about it. All they know are the other constants. I don't think they even know about time. Variables knows about times. They are your dynamic expressions. You can imagine, if you're more into computer science, you can imagine how the interpreter is working underneath, whether or not this is an expression that has to be evaluated at runtime, or it can be compiled, blah, 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 right? That's kind of the useful part here. Okay. And it's even giving me an issue. H is a reserved name. So I don't know if you saw that yellow squiggle under there. It doesn't like it because H actually means something in COMSOL parlance. I don't actually remember offhand. It's probably something to do with step size. Okay. This is a temperature calculation. So let's try and put in J is equal to T times 3. It comes up with a yellow squiggle and says, I don't know what T is, right? Very common. This is because your physics lives in your component, right? Think about your scope. Think about your modularization. Temperature exists in your component. So if you try and call temperature out here on your global part, it won't know what you're talking about. So let's go into our components. These are, you can dig into this. To be honest, I would just set it when you're creating a new module and don't touch it after that. This is one of these things, like, it gives you enough rope that you're going to get tied up in, and then you're just going to have to like destroy your model and start new and just like manually transfer everything over. By the way, if you get like super stuck into a rabbit hole, you can't figure out what's going on. Sometimes it's easier just to create a new model, copy and paste, and then you'll understand bit by bit, rather than like trying to go in and figure things out. It's just because it can get kind of deep with the redundancy of these things and things like that. Okay. Under your components, you also have definitions. What kind of definitions do you have? My thing is too low here. Hold on. When you right click on it, you could do things like variables. Okay. Going back to full screen here. Your variables operate exactly the same, but now, because we've put in physics, I'll show you how to put in physics afterwards, right? Your physics is defining your temperature. So now we can say something like T times 2. It knows the temperature is in Kelvin, right? And now it knows about it. It's aware of that. That's your scoping sensitivity. Everything in here is also aware of everything there, right? There's the, what would that be? Inheritance structure between those two objects. And that's good. Okay. What else would you have to put in here? Depending on how sophisticated you want to be, There are other options here. I would be very careful going into all of these things because it's a lot. There are a lot of different things. Some of the nice things that you might want to use are your different functions. If you have data and you want to interpolate, you right click, you go to functions, and you give it interpolation. And you tell it T2, 5, T3, 7. And if you plot, it doesn't know about J. Oh, whatever. Yeah, okay. I defined something twice. It's what happens when I try and go too quickly. Still doesn't know about J. What are you talking about? Okay. Throw it through an error and you have to dig back into that. Okay. Now I can plot. Now it's doing an interpolation. Say I wanted to do 5 and 9. Say I want to do a different type of interpolation. Instead of linear, I want to use piecewise cubic, right? Now I can do interpolation. I'm not sure if you guys are going to need that, but that's where you would find it if you do. Okay. What else do I have under parameters here? Yeah. Okay. Let's actually do something. First thing you have to do when you want to actually do something is, I'm just going to delete this just so it doesn't get in my way later again. Delete. All you have to do is, sorry, I should have broken that down a little bit more. If you create something and you want to mess around and you want to change things, right click on it. You can duplicate. That's an object, right? Again, it's object oriented. So you're building up this structure. What things can you do? You can duplicate it. You can copy, you can paste, you can rename it, you can delete it. You can also disable. Okay, disable is really useful if you want to check something, you want to turn it off, but you still want to keep it just in case you want to put it back later. Okay. Generally speaking, though, you want to keep a clean house, which means you want to delete things when you can. Geometry in COMSOL is super, super powerful. It works basically the same as any other kind of CAD software, computer-assisted design. I forget what the term for this, constructive geometry something, I don't know. Right click on geometry, you can define things like rectangle, right? This guy developed a rectangle here. He made a point, click, he actually made 2 points, right? So this is a point creative object, and then you give it the coordinates of 2 different points. Another thing that you can do, I'll just show you guys this thing quickly. If you want to do something like make a circle, build selected is build everything up to the point that you're currently on. Okay, that circle is way too big. Build all is build everything in that sequence. This circle is too big. Let's make that radius 0.1. Build selected, right? What you could do, right click on geometry, go to, let's say difference, right? And then you're going to do this kind of like algebraic manipulation of these geometries. Object to add, you want the square. Object to subtract. See how this guy is kind of turned on right now? When it's turned on and that green light, that's what you would be clicking. Okay, so whatever I click, that's where that selection is going to go. I don't want that. What I want to do is object subtract. So I turn on this selection, and now I click on this, and now it puts it in the right place. Okay, that's a little bit annoying until you realize what's going on there. Hit build all object. I've subtracted that circle from that rectangle, and now I've got this funny shape. Okay, that's how that one's built. It's very useful for that sort of thing. That's actually a remarkably powerful feature, ability to use that. Let's see, build all. You could put your parameters, only your parameters that you've defined up here in here. So if you remember, I defined A as 10 inches. I can use A here, and it'll make something 10 inches across. Okay. Very useful if you want to kind of like build that up parametrically, if you want to keep track and you want to keep all your variables in one place, if you want to make 2 objects that require the same, unit underneath, something like that, you can do it that way, and that's very useful. Okay. I will show you why they're defining 2 points here. You might think that that's a little bit redundant. what's going to happen is that we're going to define this edge here to be different from these two edges down here. Materials. Materials are super, super useful. When we define our physics is going to need to know things about the system, right? One of those things might be for heat transport, it's all about thermal conductivity. For diffusion, it's all about your diffusivity. For electrostatics, it's all about your electric permeability. Materials are a great way that COMSOL has taken all that data, all those material properties, and served it up to you in a very nice, accessible format that you don't have to worry about. Hallelujah. Right-click on materials. Add material from library. And it's going to open up one of the most useful features of COMSOL. You could search for anything you want here, copper. Hit enter, search. The first time you run that, you can tell that I updated recently. It's got to rebuild the library. It goes through. And now you've got not just one copper, but all the different types of coppers that exist in industry, all of your alloys, all of your different options. Are you talking about the liquid? Which temperature range are you talking about? Which testing, ISO characterization? Look how many different coppers there are here, right? It just goes on and on and on. You can choose which one you want. You can pop it in, and if that doesn't turn into the right one, you delete it. Let me show you. Add material from library. Copper, right? You can right click, add to component 1. I think you just double click on it, and now it's created, and look at all these beautiful material properties. It's automatically populated. Thermal conductivity, thermal expansion, heat capacity, density, tangent coefficient of thermal diffusivity, thermal strain, Young's modulus. All of that is right there. So you got the wrong one. Right click, delete or disable. Go down to one of these other ones, USNC, whatever. Double click, and now you've got a completely different material. Hallelujah. Very, very useful. Okay. One of the things I think that your model is going to be doing electrostatics. Remember, okay, this is my tip of advice for you guys. When you're doing electrostatics, the electric fields also exist in the surrounding air. Not just in the object that you're trying to do something in, but also in the air around it. Which means you need to model air. Okay, this is aircraft. Obviously, you don't want aircraft. You probably want the built-in ones here are probably your most useful ones. When you double click and you add air here, all of a sudden it's going to have things like electric conductivity, right? Thermal conductivity, speed of sound if you want to do anything with that. Parameter of nonlinearity, I think that's a thermodynamic coefficient. You probably won't need that one. It has free space, vacuum, right? Why on earth would you need vacuum? Well, guess what? Electric fields exist in a vacuum. You click that guy, and it has all of your electric permeability in it. If you want to take it out of vacuum and you want to put it into air, click, click, everything else stays the same. Super, super useful. So again, you right click, when in doubt in COMSOL, right click. Chances are you're going to get your options. Okay, I did materials. Next, physics. When you are creating your model, let me see if I can just create a new one here. Okay. When you're building your model, if you're building it from scratch, from blank, it kind of takes you through a bit of a wizard, and you'll be able to select what kind of physics you want to include. I launched that thing to show you guys, and now I'm not going to bother anymore. Okay. When it does that, it's going to pre-populate a bunch of stuff. But one of those things that it's going to do is also the type of physics that you want to do here. So in this case, this is heat transport. If you want to add more, or you selected the wrong one, right click on components, add physics. It's going to open up another list here and say you want diffusion. drift diffusion, sure. Double click, and now you have a different type of physics, which is in your component, right? So the reason why they do that by component is because if you were doing, again, back to the car, if you're doing tires, you have air pressure. If you have an engine component that's a solid, you don't have fluid dynamics in there. You don't have air in there. So why would you bother modeling that? That's why they do it like that. Same thing here. There's disable, there's delete. There's a whole bunch of other options. I have no idea what drift diffusion is actually. So I'm going to skip that one. I'm just going to go back to heat transport. Heat transport, when you do this, it's going to collapse a bunch of things. Just click on the chevron and it'll show you things like the equation. At least you can make sure that you're doing the right physics. Any other type of like general reference temperature here, wouldn't worry about the discretization. The dependent variable, if you don't know what dependent variable is, what time you're selecting physics, you've got bigger problems, to be entirely honest. It's here, but this is also the variable name that you can reference back in your expressions, in your definitions there. Okay. If you right click on your type of physics, it's going to give you all the different things that it could do. And it's going to be divided up by dimensionality. So solid, fluid, these are thermal conductivity. What it's doing is it's just adding different terms to your equations. If you have a heat source, right? So you might have a charge source, for example, you would right click on that and go for your source. Your initial value is also, you see how this is filled in? It's because it's applying to the entire 2D option, the entire 2D domain. There are different ones. Feel free to poke around in this thing. You might get into issues with material properties there, but generally speaking, you're pretty good. So again, when you see the filled in thing, it's because you're doing the entire object. It's pretty trivial. It's pretty self-explanatory for 3D too. When you go on there, you can take a peek at the equation if you really want. Otherwise, thermal conductivity. In this case, because it's built already, it's user defined as that. Otherwise, I'll just show you. I should have just kept this. Let's put back in copper. Clickety-click. Right? Close this guy up again. You could say from material. And from material means it's going to read back into that material. If it has thermal conductivity, then it's going to pull that out and use that. Super, super useful. Note the units. Right? This is how you write units. It's echoed down here. If you don't have that, it's probably going to get upset at me. Let me just try and hack that. Sometimes you have to click over to a different one. Yep, there's that yellow line because it's angry at me. Okay. Let's see. Because of the system, we're not, oops, too many things. We're not interested in density, so we've set 0 density. We've set 0 heat capacity. Don't worry about that one unless this is our actual thing. Okay. These guys, you see how this is just the line? These are your boundary conditions. What that means is that your differential equation is defined both on your domain, but also on the outer edges of the thing. What your boundary conditions are these line elements. So when you click onto here, again, notice that this is selected. I can decide which boundaries. Let me see if I can zoom in here. See these blue ones here? These are the edges that I'm currently working with. And I'm going to say that they are insulative. I don't want everything to be insulative. I want the outer surface to be at 273.15 Kelvin. Okay. And I'm going to give this middle part here a heat flux. I'm going to be pushing heat into the system. These are going to insulate, and these are at a fixed temperature. So you're cooling something, and it's in contact with a heat bath or something like that. What was I going to say about that one? Be aware that COMSOL is sequential. It is modular, but it's also sequential. The things down here happen after the ones up here. So this says thermal insulation everywhere, but when you go and look at it, it says that it's overwritten. What is it overwritten by? It's overwritten by these guys. So if something is overwritten, you might have to go down here. Say you have something that doesn't look right, right click and disable it. And now when you go back up here, now it's all the way across because you've disabled that overriding thing here. Okay. And you can give it any other information you hear. It's a lot of information. Don't worry about it, right? All the videos are pre-recorded. I think this one, I'm not sure if this video is also being recorded, but the YouTube channel has everything broken down. I did try and like kind of break it down into be a bit digestible, but honestly, like open up one of the model files, start poking around, start disabling things, and it'll become pretty clear pretty easily. There are a lot of Linux users on here, so I like to say that COMSOL is the Windows of finite element method. Right? Anybody can pick up by design, anybody can pick up COMSOL and start to do cool stuff that looks beautiful, right? There are the research grade options that are more like DFT, that's more like the Linux, right? Like it takes a while, you feel good about it, but it takes a lot of work to actually get anything useful coming out on the other side. I use Linux too, right? Yeah, okay, on to mesh. Let's see. Meshing is when you're actually like dividing up your space into those little triangles. All you have to do is, generally speaking, right click on here. You don't even have to right click. Just go to build all. Click. Bam. Magic. There are entire software packages dedicated to meshing things. Meshing is a terribly, terribly complicated algorithm. COMSOL has mercifully boiled all that down into build all. Fantastic. What size element do you want? Extremely coarse. Boom. Right? Now it's super coarse. You could have extremely fine. Yuck. Did you see how that took a little while before it was able to calculate that? The finer you go, right? Think about your surface. If you have an extremely coarse model, let's see if this is just going to work. Live demonstration. I hate live demonstrations. I'm going to skip ahead. I'm going to show you guys what I did in a second. Solve, 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 chunk, chunk, chunk. Okay. And this guy, I wish I remembered how to turn off smoothing here. Give me 1 second to try and figure this one out. I don't think I'm going to be able to do it. Not in a timely fashion. Quality. Here we go. Smoothing. Wah, wah. None. Let's see what the solution actually looks like. No refinement. Shazam. That's our actual model. That's our actual analytical model. Why does it look like that? Because your mesh underneath looks like those triangles. Remember I said that we're just fitting like a simple polynomial, a simple quadratic onto those triangles. That's why it looks like that. Without that refinement, right? COMSOL's hiding things from you. What you see is not what you're really getting. It's smoothing. It's generally speaking good to do, and it makes things look nice, but this is your actual solution. Okay. You saw how long that took to run. That wasn't preloaded. That was actually the real run. Now we're going to use a smaller mesh. I'm going to go back here. I'm going to compute. Watch my progress bar. Chunk, 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 chunk. See, the RAM started to creep up. And now when I look into my solution, you can still see the facets. I can see a triangle over here, but it's much better. If I wanted, I could go for extremely fine. I'll show you what I'm doing with the compute in a second. You see those teeny tiny triangles. Now watch how long that's taking to get there. I had even more RAM consumed, but now my solution looks better. When you are doing this in 3D, when you're cutting your triangle in half by size, you're bisecting it, you're actually multiplying the total number of tetrahedra, 3D triangle equivalent, exponentially. This is the magic. If you are doing 3D, mark my word, if you remember nothing else, remember this part. Start off with as coarse as you can. Make sure the thing runs. Then go back and start bringing that down and making it more and more fine. Watch your RAM. When it goes too high, force kill. Save before. Okay, that saved me no number of times. Okay, if you want to be more clever, because you can be more clever, right-click on mesh, and you could do something like size. Okay, and what I'm going to do is I'm going to apply this for a boundary. And I'm going to say it's this boundary because all my heat was coming in here. So why am I meshing it all the same? I'm going to mesh this extremely fine. Oops. What's this complaining about? No option. Yeah, okay. Right click, free triangles, build all, and now look at this. It is refining it better wherever you need it. 3D, very, very useful. Put your mesh elements where you need it. FEM is great because it allows you to do that. I'm going to leave that like that. Okay. Second last one, study. Study is where you actually do things. Study is where you're actually computing it, but COMSOL actually kind of hides the button that you actually have to press. I suspect you guys aren't going to have to worry about this one too much because when you're selecting your physics, it's going to automatically populate this sort of thing. If you really wanted to dig into it, the type of study that you do is something like time-dependent versus stationary, right? If you're worried about things over time, then you would want time-dependent, then you have to step through time. If you're just doing something steady state, electrostatics are usually steady state, not necessarily, right? You could have quasi-statics, but generally speaking, it's that. You would want that. I don't know if you guys are going to get into eigenfunction analysis. If you do, that is a different type of study. You don't have to change your physics. The physics is the same, but the study is different, which means the way you're solving it is different. If you get really curious, you can dig into what all these nodes are doing. Be careful because that gets into, like, honestly, undergrad, high undergrad level or graduate level things. If you're selecting electrostatics, again, another nice thing about COMSOL is it'll pre-populate these things for you. So electrostatics likes to use something called multi-grid methods, which are super, super efficient if you do them right. Good news, COMSOL does it right automatically. Don't worry about that. I would be careful digging into this node. When you're actually ready to do something, it's this teeny tiny button up here, compute. Right beside blah, 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 compute. Or you can right click on it and go to compute. That's when all of a sudden your file size goes from a few kilobytes to like half a gigabyte because you've calculated all this information and now you've got your actual solution. Okay, save before you do that, especially in 3D. I don't know how many times I have to say that one. Okay. When you do that, it will automatically, and again, COMSOL will automatically populate some of these results for you. Is this a thing? Oh, that's neat. I never knew I did that. Okay. It'll automatically populate some plots for you based on the type of physics. If not, then you just have to clicky over here. Let's see. The types of results are grouped by dimension. So when you go, if you want to change something like this, think about what dimension you want to be in and go for that. So if you want to create a new one, go to results, 3D plot group, 2D, 1D, right? It's already populated. And if you look at the icon over here, right, this is a flat square, you're in 2D. This one is a 3D cube, which means you are in 3D, right? That's simple. If you wanted to do something like 1D plot group, it would be here, and now you can do things that are only going to give you a one-dimensional thing. Again, there's disable, there's duplicate, whatever you want. Underneath that, that's when you have to do things like creating a surface. Okay, and the surface is the colored in one. What expression are you coloring in by? Temperature. Great. Other things that you could do, actually, I'm going to show you it this way. Super useful, and again, kind of hidden. Go up here, and there's this drop-down menu that's replace expression. This will have all of your pre-built definitions, all of the functions that you made, your interpolation functions, general parameters. Here's A, whatever I want in meters, right? If you go under your things, under your physics, all of a sudden it will give you temperature, right? What is the gradient of the temperature? What is the magnitude of the temperature gradient? What are your components of your gradient? What are your material properties? What is your key capacity? What is your density? All that is in there, and you can even search that. How do you make the mesh change from fine to large using size? I missed the button you clicked. I'll come back to that one and show you in a minute. Remind me if I don't. Make sure that one is everybody. Okay. Where was I going to go with this one? So something nice to look at is, so let me go back a second. What are the other cool things that you could look at? You see your temperature. Say you wanted to see which way the heat was flowing. Right click on this group, explore around here, and there's this nice thing, arrow surfaces. Right? What is an arrow surface? COMSOL has already realized that you're only doing temperature and there's only so many arrows that you could possibly want. So it's given you your expressions already. Hit plot. And now all of a sudden, you get these nice red arrows that are showing you your heat flux. If you wanted a different one, go down here, right, to your replace expression. Heat transport, and okay, there's no velocity. If there was velocity, you could do that. Okay, there aren't actually any other ones because there's only so many vectoral quantities you could actually put in here. When you're getting into electrostatics, though, there are going to be a lot of different ones. So the nice thing is, again, up here, hit that button. You can even search for something there, and it's all pre-populated for you. Another nice thing you might want to use, right-click on the surface itself, and you could do a height expression. Now, all of a sudden, you see this thing in 3D. It's still considered a 2D plot. You haven't changed that, but now you've gotten this nice view, which honestly can be helpful. Okay, I'm going to disable that one. I'm running over time, so I'm gonna keep going here. When you go into the 3-dimensional plots, this looks beautiful. It looks very useful. Everybody loves to include these in reports. Please beware, because this is actually less informative than your 2D plot. Your 2D plot makes it super easy. I can throw down a grid on this. I can see exactly where my temperature lines are. This looks pretty, doesn't actually help me. It's actually just redundant. It actually actively doesn't help me, because this is all the data, and everything over here is just wrapped around. That's all it is. Looks beautiful. Is it useful? Is it not? I don't know. Some of the other things you might want for electrostatics, for example, is stuff like isosurfaces. Isosurfaces are lines of constant temperature. In this case, sorry, not lines, surfaces. And, right, this I could actually see like this being a useful 3-dimensional plot. Okay. You also have iso contours. A lot of this stuff is pre-populated. If you're doing time dependent or anything like that, you might want to use an animation. Click on that, right? I'll just let you poke around there, and then you get a bunch of stuff. If you're on Linux, I would suggest you probably want the image like this. And then what it's going to do is it's going to plot out a whole list of images that you put into FFmpeg or something like that. Okay. Let's see. That was, yeah. Plotting in COMSOL is very powerful, and they like to upsell their features. Don't get carried away, because a lot of the times the advanced features aren't actually useful for you. Just something I just want to show you. Actually, I should show you guys on this one. Say you're back here. Say you generate an image. COMSOL likes to separate the creation of the thing from the execution of the thing. And the reason it's doing that is because the execution can take a whole lot of time. So, for example, I said, make me a list of images here. It added this thing to an export. And you might go looking for these images, but it hasn't done anything yet because you haven't pressed export. When you export, now it'll say, okay, where do you want to save these things, right? The reason it's doing that is that you can save before you break your computer because you've run out of RAM again. Okay. There was a question about the mesh, and then I'm actually done with that. So if there are any other questions, feel free to start popping them into the chat. What I did with that one, so it started off with delete. Just can I just reset this? I think there's a reset. You know what? I'm just gonna show you guys one of the best features in here. File, revert to saved. Revert to saved will nuke everything and bring it back to whatever saved version you originally had. Super, super handy. Super convenient. Okay. Originally, it was just mesh. Mesh, it'll know what to do. If you want to change something about the size, right-click, add a size feature. You can see there are a lot of different ones. It gives you enough rope to tie yourself up in. Okay, I want to do this. I want to make it at a geometric entity. Let's actually put it at the points. Which points? This point and this point, and I want this to be extremely fine. If you just hit build all at this point, it's going to say, I don't know what to do. It's because it's not, COMSOL is smart in great ways and it's not so smart in other ways. It doesn't know that you want to build a triangular mesh. So you have to go over here, go up here and say, build a free triangular mesh. You could try a quad mesh if you want. I'll show you what the difference is, right? Build all, and now it's building a triangular mesh. If you want, you could delete that. And if you really wanted, you could also build a free quad mesh. Quads are a fancy way to say squares, right? Quadrilaterals. And now it gives a shape that is refined, but you see you've got some gobbledygook. Why do you have that gobbledygook? Because triangles are more flexible and more space filling than quads. Quads are actually more efficient for finite element method. There are reasons for that, but it's honestly, triangles are probably the way to go. Any other questions? Does adding material to the component just allow you to specify parameters for it, or does it automatically assign to the geometry in that component? The geometry doesn't know anything. The geometry is just a rectangle. And what you're doing on that rectangle is something completely separate. And what that thing is that you're doing on the rectangle is your physics. And you can have multiple different physics. You can have your physics applying to one rectangle and not the one beside it, one boundary and not the one adjacent to it. But the physics needs to know something about that material. So you could pop in those different material properties by hand. That's actually what it's done here, user defined, or give it to material, get it from the COMSOL material library, and then you just pull it directly. So the material doesn't really belong to the geometry or even the component. A component could have several materials. You could have, well, here, I'll just show you guys. Why say when I can demonstrate, right? I'm going to, let's put in another square. You know what, I'm going to do it this way. Duplicate. And I'm going to put this guy, I'm going to keep the corner the same. I'm going to make this, look, divided by 4. Divided by 4. You can put math expressions in here. Build all objects, and now I've got this itty bitty one here. Okay, I'm going to leave that. And now I'm going to make a material. Add material from library, copper. Grind. Where's my built-ins? My built-ins are all the way down here, aren't they? Yeah. Okay. So I'm going to just say copper is only this outer square. And now I'm going to add another material, which is, I'm just going to go here, beryllium copper. Why not? I don't like beryllium copper. Let's do built-ins alumina. Okay. Now I'm putting alumina over here. Now what I have, and yes, I do have the thermal conductivity. Okay, so now I have 2 materials. I also have 2 domains here. I'm going to change my material properties in solid conduction to from user defined, and I'm going to make it material defined. I'm going to keep these guys so you can mix and match. And now when I right click on study and I go to compute, never do live demos, kids. Oh my God, it actually worked, right? This guy is going to now have, this is going to be copper over here and alumina over here, right? Just by clicking those things. If you want, now you're playing around, I'm just going to disable this guy. I'm going to put copper back here, click, right click, compute, and now I've done everything all copper. So you can really mix and match and play around with that. That changed a little bit. That's alumina, which is the oxide version, not aluminum. So it would have much lower thermal conductivity there. Yeah. How did you hide the 3D volume to reveal the rainbow colored isosurface? You're welcome, Johnny. I did not. Oh, yes, I did. Okay, I disabled it. I didn't hide it, I disabled it. So right click on here, go to ISO surfaces, plot, and you don't see anything because your volume plot is covering it up. Right click, disable. Now you see it. Or you get fancy. You throw in volume, and down here, I think is it quality? Nope. Right click, transparency. And now I can make it look see-through. Isn't that awesome? Don't you want to do that for your report? Don't you want to show that in your presentation? Don't. It's useless. Look at this thing. What is the value of this color? Yes, it looks cool, right? But it all looks purple. You can't see any of the colors here. They're all in the ISO surface anyway. Use it. It looks cool. Just bear in mind that this, honestly, I would probably take a mark off for that if I was marking it. So anybody going into 2CM4 next year, don't do that. Right? Just show like the temperature profile here is a lot more descriptive. Okay, it does look badass. Yeah. Welcome to COMSOL. COMSOL is fantastic for selling itself. Everything is rainbow colored. There are research articles written on why COMSOL's color choices are bad. Not joking. Look it up. It's Peer Review is a competitor and they like sponsored this or something. It does look good. When you have animations, you can do things. You can rotate this thing around. You give it a time-dependent parameter for rotation. You put in an animation, it's rotating. The transparency is going in and out. Your ISO surfaces are going like that. It looks really cool. And somebody who actually tries to read it is completely like dumbfounded because you can't get any information off it. It is only used as an illustration. It's used to sell things. If you want to sell things, great. There's a field of study, CFD. Normally, you would call it computational fluid dynamics. A lot of people in engineering will call it colorful directors because you make very colorful things. It looks great. You get lots of money for your next research project, and anybody who actually tries to read your data or interpret it, is kind of dumbfounded by it. Any other questions? I think I'm like 15 minutes over now. Okay, one more tip of advice. COMSOL is ingested, whatever you call it, with the major AI engines. So I like Gemini personally, but I think ChatGPT too. I think actually 6.3, there are options when you install it to actually have ChatGPT built into it, which is kind of neat because then it's already like pre-trained on the user manual and everything like that. If you do get lost, like one of these chats, one of these Geminis, I haven't actually played around with the inbuilt version. Like it'll probably help you get like where your problem is. I haven't tried uploading an MPH file directly and having it analyze it. You could try it. Any other questions? Otherwise, I think I need to hand it back and make dinner for my children.
Hey, so it kind of reminds me of have you saw a 3D pie graph? And what's your opinion on that?
3D pie graph. How do you mean?
That
like
thing.
Hey, what about it? What about it?
That like you have like a pie, except like it's like it's like 3D and it's built like a pizza pie, and then like it's misleading.
It is. Yes. Yes, it is. That's exactly it. It's very misleading. First of all, people might think that you actually solved a 3D case here, and you didn't. It's 2D that's been extruded and revolved around like that, which is misleading. It doesn't contain any more information, and it's harder to read, right? So, use the right tool for the job. Okay, here's my general advice. Use the right tool for the job. If you're putting this into a scientific article and you want other people to be able to like read it and understand it or something, you use the 2D graph, you use the right color scheme, you put on your ISO contours, this and this and this. If you're using it to try and get money from the upper echelons, you're using it to sell, it does look cool.
It looks badass.
Yes, it does.
May I share my screen to see uh like a chart that I'm referring to? Because I cannot share my screen.
I can stop sharing.
Okay. So here's the thing.
Yeah.
But
But like the application library is full of this stuff. So you'll be able to see like all kinds of different examples and things. Use the right tool for the job.
Use the right tools. Okay.
Yeah.
So Mike, may I share my screen now?
Sure, but I don't think I can give you permission. I think that's on the organizers.
I think there.
Yes, one moment.
You can also just send in the chat the name of the file that you're looking at.
Okay, sure. I'll just do that. Okay,
Yeah.
I'll do 3.
Just keep things moving along. But yeah, I mean there are lots of nice, nifty visualization things. COMSOL gives you so much rope that you can find yourself tangled in it pretty tight.
Okay, sorry about that.
No. Yeah.
I think I have like an alternative way to share what exactly I'm meaning because it's just too common. That's the thing. It's too common, but
no problem. Anybody else with
okay,
questions
so
while we're sharing it?
I don't know how to.
Just send it in the chat, man. or on your Discord channel.
I have to send an image. That's the thing.
Okay, then I go through your Discord. Hey, anybody else have any questions? Okay. Then Clarissa, maybe I hand it back to you.
Yes, amazing. Thank you so much, Dr. Welland. That was wonderful. And just regarding the last question, in the interest of time, and I think the limitations on the Zoom chat, if you wouldn't mind just putting your question either in the Discord channel, and maybe we could forward it to Dr. Welland if he would be so willing to take a look. But if that would be all right, because I think we are moving on to our last speaker of the day, which we're handing it back to Michael Silver from UofT. So thank you so much, Dr. Welland. That was a wonderful presentation.
Thank you very much for the invitation. Good luck, everybody.
Thank you.
Bye.
All right, and we can hand it back over to Michael whenever he is ready.
Can you guys hear me okay?
Yep, you're good.
Okay, cool. Let me share my screen. Give me a thumbs up if you guys can see my screen okay. Or put it in the chat. We see it? Okay, cool. Okay, so this is gonna be your guys' first look at a trapped ion challenge in COMSOL. So many things Dr. Welland said is things I was planning on saying. So we'll keep this very short just because I'll just walk you guys through, you know, the structure and everything, what you guys will actually be doing and what your goal is. And I think Dr. Welland gave you guys enough good tips that I don't have to at this point. So like I said before in my previous lecture, we're going to be building a 3D Paul trap. Now, one thing I do want to say is that we are providing you guys this file. You're also able to use the one that's from COMSOL, which will be in the report that is linked tomorrow. It'll be in the challenge document details and everything. So this model that I have right now, it'll be like the one that's given to you. But by any means, we encourage you to build up if you want to explore other geometries that aren't a 3D Paul trap, for example. Go right ahead. We want you guys to just make as good a trap as possible. And I'll talk about how we actually do that. So right now, you know, we have a 3D trap right here. And obviously, it's not looking quite like a trap. It's just a sphere, right? And unfortunately, in COMSOL, we kind of have a limitation of, in terms of specifically doing our trapped ion stuff, we have to actually give it a vacuum kind of environment. Oops. We have to give it a vacuum environment around the actual trap itself, which is, you know, a bit unfortunate, but what can you do?
So let's just, we're gonna, sorry, yeah. So this sphere right now is just a vacuum. But what we're gonna do is hide it so that I can show you guys what's going on underneath, if this will cooperate with me. You know what? We'll actually start with parameters. So essentially in the file that we'll be giving you, this is just an example file. So we have, just a general list of parameters that you might see. But they'll be kind of grouped into two main categories. And these are editable parameters that we want you guys to go in and change and mess around with to try and get the best trap possible. So on one hand, we have geometry parameters. So you could see, if I bring this out a little bit, there's like rod radius, rod length, end caps, and all that stuff. And then there'll also be, on the other hand, electronic parameters. So that'll be, your voltage, your RF voltage, your DC voltage, your end cap voltage, and all that type of stuff. And then there'll be some basic values here. But what we're going to want you guys to do is go in, and there'll be two different parameter files under global definitions. There'll be one that will be editable and one that you do not change. So there's some parameters that you have to keep the same, such as these here. So, ytterbium 171, for example, it is an element on the periodic table, and it's a specific ion of regular ytterbium, and it's the most used ion that we actually use in trapped ion computing, just because it's very stable, different things like that. And of course, we need a couple of those values of it, so that we actually like have our trapping a real ion. Now the thing is that obviously the mass of ytterbium 171, unless you're doing some crazy particle physics to it, won't change. So things like that will be in like the non-editable parameters section, but everything else, it'll make it very clear. We'll have descriptions of all of the parameters and different things like that, just so you guys know what's going where, what's doing what. And so what we want you guys to do is we'll go over to our geometry over here. We'll build everything. Let me just see if I can change the viewing of it. Just bear with me for 1 second so I can. Okay, my apologies. The viewing is not quite working just yet. Let me just. Okay, bear with me for 1 second. My computer's acting up a little bit, so I'm gonna close the model and I'll reopen it, and then hopefully it'll work a little bit better. So I'm gonna stop sharing for now, and we'll reopen it. So the file will be sent out on Sunday evening when all the challenges are released. It'll be this file, a link to the one on COMSOL itself, and then the challenge kind of description. So it'll say what you need to do. It'll say what you need to optimize for, all that type of stuff. Let me just pull up the model. Here we go. Okay. Let me just show this one again. Okay, so like I said, sorry for the delay. We have this, vacuum sphere, and inside it is our actual model itself. So let me just move that. Here we go. So, hopefully this looks a little bit familiar to you guys. It actually looks like the ion trap we talked about. So you can see here, we have our kind of 4 different electrode bars. And remember that these are changing between positive and negative charges just to get that kind of axial confinement. And then, of course, we also have these end caps, which prevent the ions from shooting out in either way. All of these, the parameter sizes and everything like that are given in the editable parameters file that we will send to you guys. And then you can go in and change them. Obviously stick to reasonable sizes. A end rod size of 1 kilometer is not very feasible and not very good at the very least. So let's stick to just reasonable sizes within millimeters, different things like that will hopefully be reasonable for you guys. And then you guys will also be able to edit your electronic parameters as well. So that'll be, the voltage maximum and minimums of your end rods, and of course your end caps as well, different things like that. One thing I do want to mention, and as Dr. Welland said, is that we'll be dealing with the electrostatics module. So like we said before, electrostatics is essentially the study of electromagnetics, stationary, so nothing is changing, nothing is moving. We're just looking at everything as it is. There will be 2 rods that will have a negative charge assigned to them and 2 rods that have a positive charge assigned to them. And of course, that is enough to create a little bit of confinement for your atoms. Now, in terms of materials, obviously most things are air. Your electrodes are copper, just because copper is very common in COMSOL. It's not very computationally heavy, and it's a conducting material that can be used as an electrode. And the rest of it is vacuum as we need. So yeah, again, you have this sort of 4 rods, your end caps. Here's your union of everything and your exterior vacuum. Now, there is one thing called an interior vacuum, and that's this little line here. It essentially represents the line that your ions should be on. Please do not change that. All of this will also be in the challenge file, as changing that will change the kind of zone that you're measuring and may mess up some of your generated parameters. I won't tell you exactly what parameters we're optimizing for, but I will give you guys a little bit of visualization to get a gist of what makes a good ion trap. So let's run our study. Hopefully this is familiar to you because you just did it about a half an hour ago. Unfortunately, the file is a little bit large. I'm running on a Surface Pro, so not the greatest laptop. Oops. One thing I should mention is that you need to run with the vacuum sphere in mind, because if you don't have this, then there won't be vacuum in the trap and it'll just generate things for the rods and everything gets messed up. So when you're computing, you're doing your compute, you're running your study and everything like that, you have to have the sphere. Make sure you can see the sphere. I just hit it so I can show you guys the actual trap itself inside it. And I'm running on a Surface Pro, not the greatest laptop for this, but in general, it should be fine. Like, it just took a couple seconds, which is okay. So what we see here is actually the electric potential that's being generated. So if we kind of rotate around, here's kind of a cut version of our vacuum environment, just so we can have a nice look at it. So the most convenient view that you can get a lot of information from is the top view. So you just click on this little button here. It shows you from the XY axis. And essentially, you can kind of tell. So here's your different rods. And then the actual colors correspond to your electric potential, right? Like the graph title says. So you can see here that 2 of your rods have a negative electric potential. 2 of them have a positive electric potential, just like how a normal ion trap would be, right? So in our previous lecture, we had talked about, these changing potentials that kind of keep the atom confined. And you can visualize that using this kind of visualization here that we have set up for you guys. And then another one that we have set up is, we'll let it load a little bit. Electric field norm, essentially pseudo potential. So that's basically a visualization of that well that I had in my previous presentation. So, we can see here that we want our ion, which in this case will be right in the middle. And if we zoom out a little bit and give it one of these views, we can see that, we have our, 4 bars, and they're generating, this electric potential. I apologize for my slow laptop. And yeah, anyway, this is just a very convenient view, top down. And we can see that, according to, our little legend on the left, the potential in the middle of the trap, so in the middle of all the 4 bars, is very, very, very small. That's where our ions will be. And then as you go, towards the bars and outwards, it gets very, very high, which means that, of course, your ion will have a very, very hard time moving from the center to outside the trap, which is what we want, right? We want our trap to actually trap the ion, like it says in the name. Right, so generally the end caps won't be visualized just because in the grand scheme of things, they're not that useful. You can see here from the side perspective that they kind of have a more significant kind of high pseudo potential at the tops and bottoms, which obviously is nice because we don't want atoms shooting out. But in general, for a trap like this, you can see here that there's a high pseudo potential here, high pseudo potential here, but we don't want it coming down that much here, just because here's where our atoms will be lined up, right? We don't want potential pushing here, then all our atoms are crowded, then they start hitting each other, then bad things happen. So yeah, but these are just some nice visualizations we gave you guys. And here's also another interesting one. It's just a more kind of exploratory graph of pseudo potential. Again, you can kind of see through the layers. And again, like it should be pretty consistent throughout the graph, right? Like you don't want like in the middle to be like super, super high and then like just a little bit of above it to be super, super low, right? Because we want somewhat equal confinement between the entire lines of atoms that you would have in the middle here. Yeah, so those are kind of the 3 visualizations we gave you. But like Dr. Welland said, on the MATLAB website, and obviously there's so many resources online, if you create your own visuals that you're really, really proud of, you think they really display a really good trapped ion or like, parameters or whatever, then we encourage you to use those, include them in your presentations that you guys will do. And I'll talk a little bit more about that. But yeah, we want you guys to take it as far as you can. One thing I do want to say is that in our initial presentation, I said we're going to focus on a 3D Paul trap. Now, you don't have to for the sake of this hackathon. We talked about a penning trap, which I'll pull up here. Are you guys able to see my browser? Give me a yes or no in the chat.
No. I don't see it.
No? Okay, let me pull that up. I'm hoping you guys can see it now.
Yep.
Cool. Okay, penning trap. Let's see. So again, we talked about the Paul trap, but we're giving you the option to use whatever geometry you want. It's just that Paul traps are the most useful and kind of the simplest to think about. But if you want to design a penning trap and you think you can get better parameters using that, then be my guest. Essentially, at the end of the day, the geometry for this is actually even more simple because all you need is a ring and 2 end caps as opposed to 4 rods and 2 end caps and all that jazz. So if you think you can get better parameters using a pen trap, then by all means go ahead. If you're a really, really, really ambitious student, then you could be a rebel and try and make one of these, right? So like I said before, the flat ion traps, something like this, they're totally doable in COMSOL as well. If you want to and you feel like you're up to a challenge, absolutely go ahead and make something like this. It'll definitely add to your presentation. One thing I do want to say is that if you decide to pursue a crazy route like that, we won't be able to provide that much support just because you know, you're dealing with some unknown geometries and different things like that that we don't necessarily maybe can't help you with, right? So the help we'll be able to provide you is more limited than just using the provided geometries. But again, it would really add to your presentation if you're able to like actually complete like a flat trap like this. It'd be really, really cool. But yeah, so let's say you're a first or second year ECE student, you have a little bit of knowledge in you know, electromagnetism and things like that. Then we encourage you to play around with this, see how good you can make your trap. And you might ask, you know, how good can we make our trap? You know, how can we tell that it's a good trap, right? So the way we'll be judging, and this will be released in the initial, you know, challenge document and everything, is that we will give a list of different parameters that you're optimizing for. I'm not going to say them here because I don't want people to get a head start. That's a little bit cheating. But one thing I would encourage you guys to think about is, you know, what actually makes a good trap, right? So that could be things like the difference in pseudo potential. So like how, oops, let's look at this graph actually. So how big of a difference we can get between, you know, our electric field in the middle versus our electric field in this kind of ring structure here, right? Because obviously the bigger the difference there is, the more well trapped the ion is. Another thing would be things like radial symmetry. So how well the kind of pseudo potential is in line with the rest of the trap, right? Because if like this is really lined up well, but then this is kind of, you know, off kilter, maybe off to the left or the right a little bit, then that's not good, right? Because then your ions won't be in a line, your photonics will get messed up, all that type of stuff. We don't want that. Another thing is power estimate. So we're giving you guys editable you know, power, voltage, and electronic parameters. And ideally, you know, in an ion trap, you want to be as efficient as possible with the power and electricity that you're using. So another kind of point or criteria would be minimizing these parameters. I say minimizing, but if you put them too low, then you're not going to get an effective pseudo potential. So just keep that in mind. There's always a trade-off with all these parameters. And you just want to make sure that you can kind of find the best for each scoreable metric possible. And yeah, so again, the two main things that you're changing are your geometries. So that could be either editing these, you know, all these different shapes and whatever, or making your own, right? So you can use a pending trap with a ring, you can make a flat electrode trap, different things like that, or you know, you can make something completely different. Maybe you would decide to make a completely new geometry, which would be very cool. And as long as you can justify it and it works, you know, kudos to you. That'll be definitely taken into consideration. And then the second is obviously like these electronic parameters. So like voltage of your RF, voltage of your DC, voltage of your end cap, different things like that. And again, if these parameters don't make sense to you, there will be descriptions of all of them and what they do in the final file that you receive, as well as in the initial challenge document. The only thing I ask is that we have set up exports of these variables so that you're really easily able to like see them in a table. And you know, that please don't mess with that just because it makes scoring for us a lot harder. Essentially what we're going to ask you to do to submit is you'll submit the entire MPH file, and along with that will be the export table of all the parameters that we're looking for. Keep in mind that if you decide to cheat and you know, just write random values that you think are good in the table, we'll be able to tell based on the model itself. So please don't do that. Please make our lives easier in judging and just make a really good trap. Please don't just put in random values. That would not be nice. And yeah, I mean, that's essentially it. We're just, you know, designing an ion trap, or maybe optimizing it if you know, you don't think you'll be able to design one from scratch. And yeah, just going from there, kind of optimizing for these different parameters, which will be outlined for you. And yeah, I mean, the Dr. Welland very detailed went over, you know, the different types of mesh and whatever. Generally, if you feel like playing around with them, that's fine. One thing I do want to say is that the more you play around with different difficult things like that, the less we'll be able to help you. Another thing that he talked about is changing your solvers and your study parameters. Again, these are like very tricky, difficult things. So if you go in and you really feel like you want to mess with these, like it's fine, but we may not be able to help you. If you break something, you may have to start over from the original file. So just be wary when you're dealing with kind of trickier things like that and not just messing around with geometries and parameters. And also keep in mind, because this will completely break your thing, is if you do not have this exterior vacuum, your figures and your everything like that will break. So keep that in mind as well. If you decide to increase your rod lengths, for example, and they go past the vacuum, again, things will break. So you can edit your vacuum, put it as like big of a radius as you want. Just make sure that your entire trap is contained within it. And then last thing is, if you're intent on making a completely new file, you don't want to work off the one we gave you or the COMSOL one, you want to make a surface trap, for example, we ask that you borrow parameters from this file. So they will be under definitions. I'm not going to show them just because there's some stuff that might be relevant to the challenge. I don't want to give anything away. But under component, in definitions, there will be equations for variables of which we're judging for. So please, you know, copy that over. Make sure you're using them in a new file. I please ask, make our life easy, that you don't change too many parameters and things like that, just so debugging isn't a headache. You can actually edit them, of course, but please don't go in and add a bunch of new ones that do different things and everything like that, just because that will make you know, scoring and judging and likely your model as well not work very well. So does anyone have any questions for me? I didn't have the chat open, which is my apologies. Yeah, I mean, no questions. I mean, the idea of the challenge is very, very simple. You know, you're just playing around trying to build as best a trap as possible. And remember, it is an electrostatics. So in terms of, you know, electronic optimizations, there isn't an extreme amount you can do. But again, in terms of geometries, let's search up some unique trapped ion geometries. Trapped. So like, again, there's like the penning, the flat, and the 3D pole. There's also some cool stuff like this. You can use some interesting transistor technologies. And another thing is that if you decide to use a file from online, you found, you know, a COMSOL file from somewhere, please cite it in your report, just so we know, because if you just submit a pre-made file, that's not very nice. Again, you can see, like, here's kind of what a flat trap might look like. And again, yeah, I mean, it'll be pretty difficult to just search up a new trap geometry, just because they don't really exist. But if you do come up with a new one, kudos to you, and that'll definitely affect your scoring and how you do and different things like that. Yeah, I mean, that's pretty much it for the challenge. It's pretty straightforward. It can get as complicated as you want or as easy as you want. It's just a matter of like editing, you know, some of these parameters if you feel like, or you can make a whole new ion trap, which is really cool. But yeah, again, there's a lot of different things you could change. We will label each one that we ask you don't change. So just keep that in mind. Please don't change things that we don't tell you to. We aren't trying to create new particles in here. We're just trying to trap some ones that we already know.
All right. You guys haven't seen me yet. My name's Will. I'm also helping organize this hackathon. Clarissa had to go. So I'm here just to end off here. If there's no more questions from Michael, that's all we have for today. So we went over the trapped ion challenge and the superconducting challenge and all the background you guys might need for that. And tomorrow we'll jump into some silicon photonic stuff, some quantum key distribution, and focus on that that third challenge. So that stuff should be a lot of fun. That's all we have for today. So if you guys want to stick around, if you guys have any questions for me, one of the organizers, you can stick around and do that. If not, we'll let you guys go a little bit early today. So have a good night, everybody.
Thanks. I had one question. How early would the recording be posted?
That is a good question. I don't know if I can put a time on when the recording will be posted. Hopefully sometime tonight.
All right.
Keep an eye on the Discord. We'll post it, at least an update on the Discord as to how you'll be able to access it.
All right. Thank you.
Okay. Yeah, no worries. Yeah, no worry, guys. I'm seeing thank you from a lot of people. Tomorrow's gonna be just as fun, if not better, I hope. All right. If there's no more questions from anybody, or if you guys do have questions, you can head over to the Discord. We'll be active on that all night. But I'm just gonna end the call here. So thank you guys for coming out.